At this time, you may adjust your audio to a comfortable listening level. We will begin at the schedule. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. At this time, you may adjust your audio to a comfortable listening level. Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. We will begin at the scheduled start time. Thank you for your patience. Welcome to. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. Welcome to the NASA Exploration Science Forum. Thank you for your patience. Welcome to the NASA Exploration Science Forum. Thank you for your patience. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the We will begin at the scheduled start time. Thank you for your patience. To a comfortable listening level. We will begin at the scheduled start time. NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. Thank you for your patience. To a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to Welcome to the NASA Expo Time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the schedule. You may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience.
Good morning, everyone, or good afternoon, or good evening, wherever you are in the world. I know that we were joined yesterday from a lot of people all around the world. What a day yesterday! I hope you enjoyed it as much as I did. I was particularly
This
enjoying
meeting is
the
being
administrator,
recorded.
but then also all the excellent talks. And I also hope you enjoyed the poster session. We're keenly interested in feedback on that. It's quite a bit different from other poster sessions that you've no doubt seen before. So I'm excited to start with another day. I wanted to make just a couple of announcements here. First of all, with regards to the posters, we didn't give adequate credit to Ashkan Najad and Maria Elias, who were really the brains and the brawn behind the posters. And so if you had a good session yesterday with that, please give the credit to them. They did a lot of work on that. Then I also wanted to say when the parallels start, there's been a talk withdrawal. Anna Galliano has withdrawn, and so we're going to be starting with the second talk in that session. So with that, I would like to introduce the first speaker today. And this first speaker is a longtime friend and the chief scientist at NASA, Dr. Jim Green. He was previously the chief of the Planetary Science Division, and before that was a heliophysicist at Goddard Space Flight Center. So Jim, take it away. Jim, we are not hearing you right now.
All right, Greg, how about now?
Yeah, there we go.
Can you hear me now? All right,
yeah,
all right,
gotcha.
Very good. All right, thank you very much. Indeed, what I'd like to do this morning is, and this afternoon and evening for those, is talk about time early moon when the moon may have had a significant magnetosphere. Next slide, please. And to begin that, what we want to do is be able to start with the giant impact hypothesis for the origin of the moon. And this, of course, is our leading theory, where an object about the size of Mars, soon after the proto-Earth and that Mars-sized object were formed, impacted and then reaccreted into two major objects. One, of course, is the Earth we have today. And outside the Roche limit is where indeed the moon forms. Next slide, please. Now, the Roche limit is only a few Earth radii away from where the moon forms. And so over time, we know that as the moon moves away from the Earth, based on tidal dissipation that occurs, it has this varying distance. So at approximately 4 billion years ago, the moon is approximately 20 Earth radii away. And then, of course, today, the moon is at 60 Earth radii away from the Earth today. So that evolution is extremely important in this early period. Next slide, please. Well, a significant amount of work has occurred analyzing the Apollo samples, and this is for remnant magnetic field measurements. What's been teased out of the samples over the last several years in particular is that the moon's magnetic field was significant, particularly early on in its history. Of course, with the samples, we can date them and we make these sensitive measurements, and you can split over time what has been an intrinsic field from other effects that occur during this major impact history of the moon. And so, for instance, the most recent paper by Magani et al. Has put many observations together. This figure is adapted from that particular paper, showing the region in white where the magnetic field measurements that have been coming from these Apollo samples over time. The inference these authors have come up with is that, therefore, the moon must have had a global intrinsic dynamo field early on in its history, for several 100 million years, and then rapidly dies over time. Next slide, please. Of course, one of the big discussion points at this time relative to the analysis of those samples is, well, what is sustaining that magnetic field? And there are a number of ideas and theories about that, but although that's not the part that I want to dwell on in this particular paper, I want to begin with the concept that the moon, therefore, had an active dynamo for, although a limited period of time, and created, indeed, its own magnetosphere. So what we have done is we've done some basic modeling of the early moon magnetosphere based on those Apollo observations, and created a magnetic topology of not only the moon, but also knowing the Earth's magnetosphere in its history, have put these together relative to their positions. Next slide, please. Now, the modeling that we've accomplished has been done with some basic assumptions. These assumptions are where the magnetic dipoles of the moon and the Earth were anti-aligned, and we've also done that with the dipoles aligned. And so here are the basic topology results. Indeed, when the moon is at this early phase of it's moving away from the Earth, so it's approximately 18 to 20 Earth radii away when we see the maximum magnetic field that the moon is generating. And of course, we use the basic dipole of planetary science as the main component of that field to model. We have no other reason to believe we can tease out any higher multiple moments. So this is a first order analysis, of course. And so what we see in panel A is when the moon is ahead of the Earth, so this would be the moon in position on the day side, solar wind coming in from the left, of course, sweeping and interacting with these magnetic fields. And for dipole anti-aligned, we see a significant reconnection. In fact, it is a permanent feature providing strong coupling between these planetary bodies. Now, what we also see is closed field lines that come from the planet and then go back to the planet. Those will begin at Earth to fill up with evaporated ionospheric material. That region is what we know today, the plasmasphere. And during this time period, the extent of the plasmasphere would be significant because, indeed, the connection of the moon in this example provides many more of these closed field lines. Now, in addition to that, at higher latitudes, the field lines then reconnect the field lines of the moon and the Earth over in the polar regions. And this, of course, provides a significant opportunity for the exchange of low energy ionized plasma along these field lines, typically emanating from the Earth to the moon, but indeed it could go the other way. When the moon is on the day side, then we also see in panel A that it provides significant protection against the solar wind, and that's of significance because many of the early theories on the evolution of the Earth during these time periods, we want to be able to maintain its atmosphere. Now, in panel B, we see, once again, dipoles anti-aligned, but in this case, the moon is on the night side of the Earth. Once again, strong reconnection, strong coupling is going on, and the same processes that I discussed with panel A is certainly going on in panel B. Next slide, please. Now, we can also examine this with dipoles anti-aligned, and there's no reason to think that, as we know, the Earth's magnetic field flips, the sun's magnetic field flips. We're assuming planetary magnetic fields beyond the Earth also go through a process of flipping. And so configurations that are the end members, the dipole anti-aligned, here's the other end member, the dipole aligned. Once again, solar wind sweeping these magnetospheres coming from the left. And what we see now, once again, is the moon on the day side, this would be in panel A, presents a significant barrier or protective barrier against the solar wind for the Earth. And we see indeed many more closed field lines with a lot of evaporated plasma. The plasma sphere must be much larger during these time periods. In panel B, we also indeed see the significant enhancement in the Earth's magnetic field. Density of the field lines indicate also the intensity of the field. And so you see where these field lines bunch up, those are regions of intense magnetic field. But indeed, even in this night position, evaporated plasma from the Earth would indeed move from the Earth's polar cap into the lunar polar cap region, even under the conditions of dipole aligned. Next slide, please. Well, what else is happening during this time period is that the early lunar magnetosphere is also in the time period of the late heavy bombardment. And of course, that means then the magmatic filling of these huge impact regions that end up creating the Mare regions on the moon. Now, Needham and others have proposed that during this time period, there's a significant amount of outgassing that's going on that would produce a tenuous lunar atmosphere of perhaps 10 millibar or so. Now, what's interesting, of course, when you combine the eras of the magnetic field along with the era of magnetic filling and tenuous lunar atmosphere, that means the lunar atmosphere must also be protected during this time period by the lunar magnetosphere. Also, that strong coupling of the Earth's magnetosphere, as we saw, those magnetic field lines also will bunch up and also support holding on for longer periods of time the lunar atmosphere. Now, since the lunar magnetosphere lasted for only a few 100 million years, the atmosphere of the moon must quickly dissipate. But there's no doubt that it would leave its mark in volatiles on the surface. Next slide, please. So what must be happening then is being deposited in these permanently shadowed regions is a combination of volatiles from cometary asteroidal material, lunar atmosphere, Earth atmosphere, and the current lunar water cycle we know today. Now, this stratigraphy wouldn't be so nice because of the micrometeor impacts, but some notional idea needs to be looked at. Next slide, please. So, in conclusion, the early Earth-Moon magnetosphere topology has been modeled. We use the giant impact hypothesis using dipole magnetic fields aligned and anti-aligned. And due to the weak but significant lunar magnetosphere, when it's only about 20 Earth radii away from the Earth, they're very coupled and they work together to protect the early atmospheres of both the Earth and the Moon. During the times when the magnetospheres had opposite polarity, magnetic reconnection would create a pathway for the atmosphere of the early Earth to be implanted into the lunar soils. And so for the Artemis program, we want cores. Significant cores in these permanently shadowed regions will be critical for us to be able to untangle this early evolution of the Earth's volatile, testing our model assumptions. Thank you.
Thank you, Jim. Wow, those are some pretty provocative ideas, and I think I can speak for the community and say that we cannot wait to get those cores. So that's fascinating. So let me, I neglected to introduce my session co-chair, who is, she was able to step in because the other one could not do it, but Licia Yeo is the co-chair, and I believe that she has a question for you, Jim. So Licia, please.
Hi, everyone. That was a really interesting talk. Jim, can I call you that?
Please,
Yeah.
that's what I prefer.
So you mentioned that you're looking for cores from the permanently shadowed region. Why is that preferable to cores from just anywhere?
So indeed, there's been a fair amount of research about analyzing the regolith and finding nitrogen, N plus and even N2, and the concept is that must have Earth origin. So that's not just in the permanently shadowed regions. Indeed, that's from samples we brought back in the mid-latitudes. So the concept is, how did that get implanted? Well, there's been quite a bit of discussion on how that would be, and in reality, if this mechanism is working, it would be trivial to be able to implant that, because indeed that these field lines provide a ready pathway for Earth atmosphere to be implanted on the moon at all latitudes.
Interesting. Thank you. We'll take one more question here, and it's from Yvonne Pendleton in the chat. Great talk, Jim. Can you help me understand how Mars lost its B field about 4 billion years ago and the moon kept its intact so long?
So in terms of the moon has an advantage in the sense that even though it's very small, it also is close to the Earth, and these tidal forces are really pushing on the interior and heating the interior of the moon. During the impacts, if we think about the late heavy bombardment, huge impacts going on, and then magma subsequently coming in, changing the mass distribution, that produces tidal forces that have to jerk the moon around to eventually what we see today, where the mass concentrations indeed are on this size. That keeps the core active. You have to dissipate that energy somewhere. And so I think that's an element of how the moon has maintained its magnetic field for several 100 million years. Mars, on the other hand, obviously didn't have other bodies, other things that helped generate it. It had even, the huge impacts disrupting it. It cooled quickly, perhaps. But indeed, it lost its field perhaps about the same time, at about 4,000 or 4 billion years ago.
Great. Thank you so much, Jim.
My pleasure.
Jim, thank you. Thanks for an excellent talk. Great way to kick off our second day at the forum. We need to move on now to our second talk, which will be given by Jack Burns. Jack is a professor at the University of Colorado, was one of the original investigators with the NASA Lunar Science Institute, and is an investigator currently with Survey. And he's going to be talking about transformative astrophysics from the far side of the moon. Jack, please go ahead.
Yeah, thank you, Greg. Can you hear me and see my slides?
Yes.
Great.
Yes, on both. Great,
thanks. I'm disappointed this morning that we're not all together in person, because, of course, originally we were supposed to be in Boulder, Colorado. But I am looking forward to next year being all together once again in person. That'll be a lot of fun. So today what I'm going to do is talk about the far side of the moon. And the far side is a unique location in the inner solar system that enables transformative science. The far side, of course, is the location of the oldest, deepest impact basin in the inner solar system, the South Pole Aegean Basin. But in addition, it's unique in that it is radio quiet at frequencies below the FM band. It's the only place in the inner solar system that enables transformative astrophysics to be able to observe early epochs of the universe that are not accessible any other way, as well as to also look at issues of habitability of exoplanets. So we've known, going back all the way actually before the Apollo program, at scientific conferences, there was discussions of arrays of radio telescopes on the far side of the moon. But what was lacking up until relatively recently is what I like to call a killer app. That is a scientific application with compelling astrophysics, decadal level astrophysics that uniquely requires low frequency observations from the lunar far side. In recent years, two very strong science cases have emerged. One is that early universe, the dark ages, as I mentioned before, and cosmic dawn that I'll be talking a little bit about. And the other case has to do with exoplanets. And here's a nice tie-in to what Jim was talking about. This is magnetospheres and space environments for exoplanets. So let me start off with one of two missions that I'm going to describe. These are mission concept studies funded by NASA over the last year that describe some of this science. Administrator Bridenstine gave a very nice shout out yesterday to this first mission, Dapper, which is a small sat that we plan to place in low lunar orbit. It will operate at radio frequencies in the low band between roughly 17 and 35 megahertz, and also be able to go up to as high a frequency as 100 megahertz. This particular satellite will open up investigations of the early universe. So on the left-hand side, what you see is basically the science case for Dapper. This is a cartoon picture of the evolution of the universe from the Big Bang to today, is logarithmic in time. Our first picture of the early universe is the CMB, the cosmic microwave background, about 4/10 of a million years after the Big Bang. And this is a time period where the universe has expanded and cooled. So the first atoms formed, electrons and protons came together to form neutral hydrogen. In fact, the baryonic content of the early universe at this time in the intergalactic medium is dominated by neutral hydrogen. But there's no stars. This is why it's called the Dark Ages. And basically that means there's no astrophysics. So this is the ideal playground for us to really test rigorously the standard models of cosmology and look for deviations. About 500 million years later, the first stars turn on. Models indicate these will be very massive. They will emit Lyman alpha ultraviolet light and begin to ionize the intergalactic medium. That process continues until the entire intergalactic medium is reionized about 1 billion years later. These are nice ideas. They make sense. They're consistent. The problem is there's absolutely no data to test it. Neither the Hubble Space Telescope nor the James Webb Space Telescope can penetrate to these very large distances. But there is one way to be able to probe this epoch in the early universe, and that's again using the neutral hydrogen and the hyperfine transition of neutral hydrogen that comes from the 21 centimeter line. It's because of the redshift, the expanding universe, that wavelength is greatly elongated, that we actually observe, and the frequency is compressed to below 100 megahertz or so. But it is available. So that's what I'm going to be talking about. Obviously, this early universe has generated a lot of attention in the scientific community. 3 Nobel Prizes in cosmology in just the last 15 years. So a lot of core basic physics to be found here. So Dapper, the basic mission, as I alluded to a moment ago, is such that the satellite's going to be placed in the radio quiet cone. That is, when it is in that cone as part of its orbit, it will be taking data on the early universe. The antennas are very simple cross dipole antennas. We have almost no spatial resolution, but we do have good spectral resolution. So the deliverable from this mission will be a spectrum. Think of this as power in the radio receiver versus frequency. And what we're looking at are component spectral signatures for the early universe. The spacecraft is a very small one, 8/10 of a meter in the longest dimension. It's spinning, and we deploy these long dipoles for the low band part of the experiment, and it has this large peanut-shaped antenna beam. Once again, the deliverable is the spectrum. Here you see the results from a detailed end-to-end simulation that we've done that includes all of the various noise components, statistical plus systematic uncertainties associated with the sky, the foreground, and the instrument. And as you can see in the spectrum, there are two large troughs, one associated with the dark ages at low frequencies. And as I mentioned, this is a playground for cosmology. So the standard cosmology model makes a very specific prediction of the characteristics of this trough. Any deviation from that is going to indicate new physics and exotic physics, possibly physics related to non-gravitational interaction between dark matter and baryons. And then the cosmic dawn trough is going to tell us when the first stars turned on and what their characteristics are. I'm going through a lot of this very rapidly. Let me point out a number of talks and posters by members of my team and colleagues that are listed here over the next day or two. All right, let me move on to the second mission concept that we did this last year called FARSIDE. In this case, it's actually an acronym, as you see here. This is an array on the far side of the moon. Here are members of the team. Greg Hallinan from Caltech and myself are the leads. JPL and their team actually did an absolutely sensational job of working on the first engineering design study of this array. So we feel like we have a good handle now on these characteristics. Here's the science. And again, this relates somewhat to what Jim was talking about a few minutes ago. This is exoplanets and habitability of exoplanets. I'm going to start off with an analogy of Mars. We know that 2 billion years or so ago, Mars was wet and warm, but when its magnetic field shut down, then its atmosphere started to be stripped by the solar wind. We see that today with MAVEN as that stripping continues, and the net result is it transformed Mars into the desert planet that it is today, and no obvious signs of life, at least on the surface of that planet. So the space weather from the host star, along with the magnetic field, are two added ingredients associated with habitability that we need to explore. So being just in the habitable zone is not enough to know if a planet could be habitable. The kind of stars we're going to be looking at nearby are M-dwarf stars. So that just is because the majority of solar neighborhood stars are in this category. These are lower mass, lower temperatures, which means the habitability zone is within about 0.2 of an astronomical unit. So pretty close to the star. One of the problems with these M-dwarf stars is they're very bursty. They emit a lot of X-ray emission, some radio emission. In analogy to the sun emits coronal mass ejections, and associated with them are type 2 and type 3 solar bursts in the radio, generally below 10 megahertz. These are associated with shock regions, which expand out into the interplanetary medium, but they allow us to probe the space weather. In addition, these shocks also energize particles in the magnetic fields and raise the auroral emission by orders of magnitude, making them potentially visible also in exoplanets. This gives us a handle at low frequencies to being able to probe the space weather. The magnetospheres themselves, the frequency of radio emission is directly proportional to the magnetic field. Here you're looking at flux density versus frequency for planets in our solar system. Only Jupiter is visible from the ground because its magnetic field is so high. Everything else, including the Earth, is below the ionosphere cutoff on the Earth. So that means we have to go to space, we have to go to the moon to observe these planets. And similarly, Earth-like habitable planets around other stars, we would need to go to the moon. So here's the FARSIDE mission concept. We're going to operate all the way down to 100 kilohertz. That's 2 orders of magnitude below the ionosphere cutoff of the Earth. We'll use a commercial lander. We've been working with the Blue Origin company and their Blue Moon lander to baseline this. One or more rovers, which will then deploy these tethers, these science tethers that will be used for power and communication. And we'll put out 128 of these nodes. They will be distributed over an area of about 10 kilometers or so in this petal-like configuration. The node itself, the individual antenna node, some of that is derived from the Sunrise heliophysics mission. In our case, we have these tethers, which will also have the low frequency antennas embedded. These will be 100-meter tip-to-tip thin wire antennas, as well as stacer antennas for the higher frequency. To operate during the day and night, we'll have a radioactive heater unit to survive the night and radiators to be able to operate during the heat of the day. So when you put all this together and look then based upon an end-to-end study, this is kind of the deliverable. This is what we think we'll be able to see. This is the flux density from exoplanets versus distance. And here we're looking at the magnetospheric emission. The colors represent different models of enhancement due to the stellar wind, but we have several dozen exoplanets are in view here to be able to determine and measure their magnetic field, and then add that to our understanding of potential habitability. Here is a video that we put together just showing a little bit of the mission concept, the deployment of the rover off of the lander. The lander will also have our correlator, our power station with two MMRTGs, data and command. Here's the rover deploying a polyamide tether and one of the antenna nodes here with the stacer antennas coming out from there. So let me just, thanks, Greg. Let me just show one last thing here, and that is we've been also working on a prototype of a small mission to get us started, a 6-element interferometer in an L-shaped configuration here that is capable of doing some imaging of type 2 solar bursts. What we want to do is use the sun as well as Jupiter and possibly Saturn in our solar system as prototypes of what we would be doing with Farside for exoplanets. But importantly, by down risks, we'll use the JPL Axel rover to deploy the tethers and buy down risks on mobility, deployment, operations, and also understanding the interactions with the lunar surface. So let me just put up the last slide here and conclude that the Artemis program, the CLIPS program, it is beginning to open up for the first time access to the moon and to the far side of the moon for doing low frequency radio astronomy. DAPPER, Farside, and PRIME are missions that we are eager to pursue. So with that, Greg, I think I'll just stop there.
Excellent. Thank you so much, Jack. And it's great to see the progress that you've made since we first met back in the NLSI days. Just fantastic. And please feel free to put your questions in chat. I'm not immediately seeing any, and so so maybe I'll ask one, and that's what's the angular resolution that you're expecting from Farside, and given previous cosmological results, would you expect to see any structure at that kind of angular resolution?
So Farside, again, the principal design there is for exoplanets, although we are going to be pursuing some cosmology. Right. And the angular resolution will be roughly 1 degree or so. That's good enough to be able to monitor where radio emission is going to be. So with this array, we're actually going to be sampling the entire sky in 1-minute intervals with this angular resolution, 1400 channels, so that we can monitor thousands of exoplanetary systems and look for bursts that would be associated with space weather, with coronal mass ejections, and enhancements of the magnetic fields. So this is really an all-sky monitoring telescope that has sufficient resolution to deal with the nearby exoplanets.
Great, thank you. And there is one question in chat from our friend Mark Kleinvolt in the Netherlands, and he says, Jack, are you also considering techniques like additive manufacturing to build antennas on the moon?
Yes, in fact, we're working with a group in Houston, Lunar Resources, on a mission concept to manufacture antennas on the surface of the moon. We're actually hoping to submit that as part of the PRISM program.
Excellent. Excellent. Fantastic. Well, thanks for a great talk, and good luck with all this.
Thanks. Thanks very much, Greg.
I'm going to turn it over to my co-chair, Alicia, for the last talk.
Yeah, thank you. I also share Dr. Burns' disappointment that it's not going to be, or well, not in Boulder this year, because I'm also from Colorado, and it would have been so nice to show everyone our mountains and our beautiful scenery, but this will have to do, and I'm having fun and learning a lot so far. It's my pleasure to introduce Chip Shearer as the next speaker. He got his PhD from the University of Massachusetts, and he is currently at the University of New Mexico. His research interests include planetary basaltic magmatism and the evolution of planetary interiors. He's the head of Apollo's Next Generation Sample Analysis Consortium, which he's going to talk about right now.
Great, thank you very much. Can you see my screen right now?
Absolutely.
Okay, wonderful. It's very nice to be here representing the ANCSA science team and the JSC Lunar Curation Office. And I'm going to provide you with an overview of the Apollo Next Generation Sample Analysis Initiative, or ANCSA. As many of you all know, between 1969 and 1972, Project Apollo returned over 380 kilograms of material from the lunar surface. These images here provide you with some idea of the different types of materials that were returned. For example, hand samples that were collected by the astronauts that represent different lithologies, from impact to magmatic lithologies, core samples, rake samples, and also what I refer to as special samples. These samples were either collected in unique manners on the lunar surface or were processed in unique manners once they were returned to Earth. What's really important about these samples that I can't emphasize enough is the Apollo samples really strongly influenced our understanding of the moon and the solar system. It provided important chronological data and chemical data for the origin and evolution of the moon, planetary differentiation, and the impact history of the inner solar system, but also the potential dynamics of the outer solar system. The ANCSA initiative is examining 3 different types of samples: unopened, vacuum-sealed Apollo samples that were that these samples were placed within either SESCs, special environmental sample containers shown to your right, or core sample vacuum containers, and sealed, and ideally maintained a Mars-like vacuum on those samples and preserve them. These containers had a sealing mechanism as shown in the bottom right-hand corner, indium seal with a stainless steel knife edge. In addition to these unopened Apollo samples, they are also, the ANCSA initiative is looking at some of the frozen Apollo samples and Apollo samples that were opened, curated, and remain stored in helium versus the traditional nitrogen atmosphere that lunar samples and curation are kept in. The Apollo Next Generation Initiative consists of 9 original teams and over 60 scientists, engineers, and astronauts, both current and former astronauts. My initial concept for this initiative, and it was designed as a new and obviously cheap lunar sample return mission, as these samples have never been analyzed or examined in the past, and essentially processing, conducting preliminary examination and final analyses utilizing new and improved technologies, and then tying this data into recent mission observations. And finally, the concept of the ANCSA initiative really is linked to engage the very first generation of lunar explorers with future generations of explorers of the moon. Some of the sample goals for this initiative are shown on the left-hand side. Overall, we hopefully are investigating the volatile cycle on the moon as recorded by the regolith samples and the core sample vacuum container. Also, there's a joint engineering and science goal that focuses upon how well did these containers work in preserving the lunar record, and what are the implications for future lunar exploration. And then finally, some other science goals, and there are many others depending on the team. How do lunar landslides work in terms of triggering them and their dynamics? And what is the chronology of various lunar events? What I would like to do right now is really focus on the double drive tube sample that was collected during Apollo 17. And the reason why I'm focusing primarily on that is a large number of team members are examining this sample, and we've accomplished the most work on this sample within the COVID-19 environment. 73001 is the lower part of the drive tube. 73002 is the upper part of the drive tube. 002 was extruded from the sealed drive tube, where 73001 is the lower part, still stored in the core sample vacuum container. The site for this collection is Station 3, shown right here on this image of the Taurus Littoral Valley. It's within a light mantle deposit, and the core penetrates what is a landslide material off the South Massif and penetrates to a depth of a little over 70 centimeters. This study by the ANCSA team is both a continuation of Apollo goals to look at gases that may have been derived from the Lee-Lincoln Scarp, but also feeds forward to Artemis because of the unique containment and the unique geology. We're providing a variety of different perspectives in our analysis of these core. For example, placing these members of the team are placing these within the geological context, whether they be surface geological context, surface sample context, or a much broader local and regional context derived from recent orbital data. And this lists some of the team members involved in each of those examinations of the source, the site. The first measurements that were done on this core were done on the 73002, which again is the upper part of the core that was still within the upper part of the double drive tube. Just illustrates the advancement in technology that we're utilizing to curate and examine these samples. The diagram, the image on that's labeled 1974 is a simple X-ray image of the same core taken, and the bottom part of the bottom image is a very recent image that we took in November via XCT. And you can see the incredible increase in resolution, which is important for science and examining the dynamics of lunar landslide deposits by being able to analyze grain sizes, but also really important with regards to developing strategies for dissecting the core. In addition to this obvious difference in resolution, the XCT analyses can provide a multitude, thousands of different slices through the core, so we can look at different segments of this core. The core was, excuse me, extruded and derined in early November. This is the 73002 core by a processing team at the Johnson Space Center. And this illustrates two of the images of the core before processing. Soon after extrusion, members of our team from the University of Hawaii conducted both multispectral imaging of the core and hyperspectral processing or profiling of the core. And those different reflectance wavelengths are shown in diagram B and C, again, derived from the initial measurements of this core. As we process the core more and more through different levels, we'll be doing additional spectral measurements in addition to the spectral measurements that will be done on 73002. The core in November through end of February was dissected and examined by the curation staff and the PE team. And this just again illustrates the dissection process. And we perform these dissections in a series of passes across the core and essentially collect samples in 0.5 centimeter segments down the core. These segments are sieved into less than 1 millimeter and greater than 1 millimeter grain sizes. And the insert diagram I illustrated here is just some of the lithic fragments collected from one sieving. In addition to just observing the samples and processing the samples, XCT analyses were done on these lithic fragments that were greater than 4 millimeters. And this illustrates the variety of lithic fragment types and textures that are revealed by the XCT imaging. Soon after we released this information to our science team, the University of Notre Dame hopped in very quickly and performed analyses of the crystal size distribution, where they were then able to utilize this data, particularly on the ilmenite from the basalts, to determine crystallization kinetic histories of these basalts. And this will be applied to other lithologies represented by these lithic clasts. Part of the sample was also early on submitted to the NASA Goddard Astrobiology Lab. And this team performed a variety of organic analyses and looked at the distribution and origin of amino acids. And their results will be reported at the fall AGU meeting in a special ANCSA session that will be held at AGU. Another portion of the sample early on was sent and is being analyzed at the University of New Mexico Stable Isotope Lab and the Johnson Space Center Radiogenic Isotope Lab for halogens, hydrogen, chlorine, oxygen, and for a traditional mineralogy petrology study. And the image to the bottom right just illustrates some of our measurements, which are step heating measurements and analyzing the hydrogen content and the hydrogen isotopic composition of the initial sample that we started to analyze. In addition to this processing and analyses, the team is also examining the core sample vacuum container in terms of deciding the best way to open the sample and to collect material or samples from this sealed container. We have already developed a core sample vacuum container strategy, and that has been finalized, and a piercing tool that will be linked to a gas manifold to extract gas from this container will also be an important part of this analysis. And we're doing this because during the Apollo missions, the core sample vacuum containers, which there were two, one collected during Apollo 16 and one collected during Apollo 17, were never analyzed, and a strategy and tools for opening this were never finalized by the Apollo program. Finally, in my last slide, what I just want to illustrate the really important linkage between ANCSA and its link to the Artemis program. As I mentioned, ANCSA is a multi-generational international initiative being run as a sample return mission. Therefore, it trains future generations for sample return missions and really hands off the torch, if you will, from Apollo to Artemis. These unopened Apollo samples, particularly the core sample vacuum container, represents our best chance to evaluate sampling approaches for ANCSA and perhaps also providing additional insights in requirements for handling and processing samples during in situ measurements. And then finally, this is really important in fulfilling the HEOMD specific strategic knowledge gaps that have been kicking around now for the last decade or so. And I think this will provide us an approach for removing some of those knowledge gaps. Thank you very much.
Thank you, Chip. That was a really great talk, and I was so amazed to see how much care was taken when you guys analyzed the core samples. There was some meticulous work going on there. We are running out of time, so I think maybe just one question from David Chevron. Is there any objective to address dust mitigation with this project? Do we have pristine dust samples that preserve physical properties, such as the sharp edge forms? If so, how much?
Could you repeat that one more time? I'm sorry, I didn't hear it all.
Oh, okay. So is there any objective to address dust mitigation with this project? Do we have pristine dust samples that preserve properties such as sharp edge forms? If so, how much?
Yes, what the ANCSA program is trying to do is, again, cover analyses and answer science questions over a fairly limited range. Some of the dust analyses will be done by TEM at the Johnson Space Center, but we are also trying to leave a number of materials and science projects for the overall science community, so that when our documentation is put into a preliminary examination document for the entire planetary community, there will be other science that can be done from these samples.
Thank you.
Yeah.
Greg, shall we move on to the next?
Sure. And I'd like to thank you, Licia, for stepping in at the last moment here. Really appreciate that. And thanks in general to all of our next gen co-chairs. This was, I don't even remember whose idea this was, but it's just been fantastic. And I think this is going to be a feature of the forum from now on, seeing as how well you and everyone else has done. So thank you so much.
It's my pleasure.
Yeah. Okay. Well, so now we are moving to a really very touching and important part of every forum, and that's the award ceremony. And we're going to be presenting in this order the Susan M. Niebuhr Award, the Angioletta Corradini Award, the Michael Wargo Award, and the Eugene Shoemaker Medal. And I'm going to share the stage with Brian Day and Christina Gibbs from the Survey Central office in reading the descriptions of the awards, and then the bios of the awardees, and just to share just a couple of minutes of the process. These are awards that are nominated by the community, all of you. And I think that that's one of the things that that makes these so important. And I you know, as always, the awardees this year are incredibly deserving. My one regret is the same as with all meetings now, is that I can't give hugs and shake hands in person. But that doesn't negate at all the importance of these. And so congratulations in advance to everyone. We have detailed descriptions on our website that a lot of you I know have seen already. But if you miss any of this, please feel free to go over and check these out. And then thanks to Jen Baer on the Survey staff, the awards were actually sent out to all of the awardees early, so they should have them now, mail notwithstanding. And finally, I'd like to ask that all of the awardees stay for the entire ceremony so that we can do a group photo at the end. So with that, let me move to my my file here, and I am going to take the first two, and that's the Susan Mahan Niebuhr Early Career Award. And so this award is an annual award given to an early career scientist who's made significant contributions to the science or explorations communities. Recipients of this award are researchers who are no more than 10 years from receiving their doctorate degrees and who have shown excellence in their field and demonstrated meaningful contributions to the science and/or exploration communities. Susan Mahan Niebuhr, who passed away in 2012, was a former Discovery Program scientist at NASA who initiated the first ever Early Career Fellowship and the annual Early Career Workshop to help new planetary scientists break into the field. This year, the prize is awarded to two very deserving people, Amy Fagan, Professor Amy Fagan, and Dr. Ryan Watkins. And I want to give a special shout out here to Kurt Niebuhr, who I believe is online and listening to this. So we're going to start with Professor Amy Fagan, who received her BS in geology with honors from Washington and Lee University in 2006, and her PhD in lunar petrology from University of Notre Dame in 2013. Professor Fagan's doctoral research under the guidance of Dr. Clive Neal focused on volcanic and impact processes on Mars and the Moon. Using MOLA data, she examined the morphology of impact craters and subglacial volcanoes on Mars's surface, while the bulk of her research examined the chemical composition of Apollo basalts and impact melt products. In 2009, she was a lunar exploration student intern supervised by Dr. David Kring, one of the Survey PIs, as part of Survey's Center for Lunar Science and Exploration team, quickly rising to the level of graduate student researcher and then a postdoctoral fellow. In 2012, she received the Lunar and Planetary Institute Career Development Award. Her service to the professional activities of this community have been exemplary. She's served on several NASA Science Mission Directorate review panels as a NASA Lunar Exploration Analysis Group member and operations chair, a COSPAR Rapid Response Specific Action Team member, an LPSC co-chair, an NESF co-organizer, session co-chair, panel member, and many, many other things. Dr. Fagan is now Associate Professor in the Geosciences and Natural Resources Department at Western Carolina University, and is currently involved with the same effort that we heard about earlier on Apollo samples. Serby is very honored to present the Susan Niebuhr Award to Professor Fagan. Amy, please take it away.
Thank you, Greg. I'm gonna see if I can share my screen here. Can y'all hear me okay?
Yes.
Awesome. Can you see my main slide?
Yes, yes.
Fantastic. It's a good day. So thank you, Greg, for that introduction. It is.
Uh-oh. Did it freeze for anyone else?
I cannot hear her any longer.
Okay, I will text her. I will text her. We were texting.
Maybe come back to her.
I guess my internet went out. Can you hear me?
Yes, now I can. Yeah, okay. Thank you.
Sorry, I live in the mountains of Western North Carolina, and sometimes our internet can be a little spotty. So hopefully this will work.
No
anyways,
problem.
Back in 2014, I wondered what I would talk about if I ever won this award. And I thought that mentoring was one of the most important things that had helped me on my career path. And so that's what I would talk about someday if I ever won it. And then, of course, my friend Noah Petro stole that topic in 2016, but I forgive him. And I think it's still important to talk about. So I'm going to talk about mentoring today. Let's see. I never met Susan Niebuhr, but I know a lot of people who knew her personally and spoke very warmly of her. And when I found out I was going to receive this award, I wanted to find a way to honor her legacy. And so I've included this quote that a lot of people include from her, that all that survives after our death are publications and people. So look carefully after the words you write, the thoughts and publications you create, and how you love others. For these are the only things that will remain. And there's one thing in here that I really want to focus on, and it's people. The people in our community are really important to us, and taking care of those people are important. And that's where mentoring is going to tie into this. But there was still one thing that I was really wanting to focus on in terms of honoring Susan's legacy, that I wasn't sure that mentoring was quite enough. Her blog, Toddler Planet, and the last blog after she passed away. And furthering Susan's through a contribution to the Inflammatory Breast Cancer Research Foundation, or please choose to make a difference somewhere, anywhere, to anyone. And Ryan and I have talked about this, Ryan Watkins and I have talked about this, and we're both going to make a contribution in Susan's name to the Inflammatory Breast Cancer Research Foundation. I encourage anyone who knew Susan or feels compelled to honor her legacy to do the same. But the other part really captures, again, what Susan said, that making a difference somewhere, anywhere, to anyone. And that's where mentoring comes in. So mentoring is the key to how we grow and we succeed. And it starts very, very early. This is kind of my envisionment of how mentoring has worked for me. It starts off with family. They give you your first values, teach you important lessons like how to do a proper handshake, which right now might not be the best life skill due to COVID, but it's maybe going to come back at some point. Friends and family. Friends teach you how to meet other people, which for some of us can be very difficult. And then school teachers, your first taste of education and looking for answers. And I know for a lot of us, we really got into science when we were young, and it was an elementary school teacher or a middle school teacher or a high school teacher who really made a difference. But it's not just in the classroom. One of the most important lessons that I learned from a mentor was from my algebra teacher in high school, Mr. Simmons. I was talking to him one day in the office, and most of you who know me would probably be shocked to know that when I was a child, I was terribly shy, painfully shy, could not talk to people. So I was talking to him in the office, and in my typical way, I was mostly staring at the floor. And he stopped me mid-sentence and he said, "Amy, when you talk to somebody, look at them in their eyes." And it was such a simple piece of advice, but no one had ever told me. And after that, I really worked hard to incorporate that into any time I was talking to somebody. So think back, actually, it's interesting of what important lessons you learned from your school teachers. From your coaches, hopefully you learned how to fail with grace and to succeed with class, and also to work together. College professors help to teach you more about your field. Some of you may have gone to college thinking you were going to major in one thing, and there was one class that made a difference, and now you're here in this field. So they really play an important key role. But the two that I want to focus on the most are graduate school advisors and postdoc advisors, because for me, they've played some of the most important roles in mentoring. My graduate school advisor was Clive Neal, postdoc advisor David Crane. And from the two of them, so many lessons. One, that the scientific method that you were taught as a child is not as simple as what you were taught. My writing needed improvement. My public speaking needed improvement. Working independently needed improvement. Working together as a group needed improvement. And my networking skills needed to improve. And they helped me to do that. There is no way that I would be sitting here talking to y'all from the bonus room above my garage today if it weren't for those two people. And one thing I want to highlight is that they're very, very different people. They have different perspectives. They have different strengths. But I need both of them. They both support me, and they have a vested interest in my success, and they have no problem telling me when I need to buckle down. And they're also the first ones to congratulate me when I do something well. You need people of various different backgrounds to help you and be your mentors. It's difficult to have one person cover all your bases. So for the students and the early career people listening, I encourage you to seek out other people to supplement your advisors. The last one I want to point out are colleagues. These can be people of various different generations, teaching you how to network, teaching you that maybe you shouldn't be using those two colors, because if you're colorblind, you won't be able to tell the difference between the symbols. There are many colleagues that have really helped me get to where I am right now. But as with any flower, you need to have water and you need to have sunlight to grow. So this is my advice for mentors, because this was the most important thing to me. For mentors, please introduce your mentees to your colleagues. This is the most important thing that David and Clive did for me when I was working with them, and they still introduce me to new people. If I hadn't been introduced to all these different people, there's no way I would be talking to you today. They played a key role in getting me where I am today. For mentees, it's not all the work on the mentor. Mentoring is hard. Tell your mentor what you want to be. I was always upfront with David and Clive that I wanted to teach, and they were always very supportive of that. But if I hadn't told them that, they wouldn't have been able to give me advice about it. So tell your mentor what you want to be. It is helpful. And eventually, you'll have seeds of advice that you will spread out to people, and your mentors will be giving their advice through you. So it's an important relationship that needs to be cultivated. Sometimes it goes awry. There's a lot of resources out there about mentoring. This is a recent one that covered some of the problems that have come up in mentoring, specifically with undergraduates, but I think we've all probably encountered one of these at some point in the past. I'm not going to dwell on this, except to say that there are some areas for improvement. But the one thing I want to point out is absenteeism, that this was pointed out as one of the major negative mentoring experiences. And during the global health crisis, we're all encountering this. So please take a moment today and reach out to your mentors. Mentors, reach out to your mentees and check on them, because when we're absent from each other, it's hard. So take care of your people. The good news, though, is that there are always resources to improve. One recent paper looked at 3 really simple tasks of how to improve your mentorship. One was taking cues from research on parent-child relationships. Oftentimes, the dynamic between a mentor and a mentee is very similar than that of a parent and child. Tell your students you believe in them and that you're helping them to reach their full potential. Often when you get only negative feedback, even if it's meant to be constructive, it can be hard. So tell them that you're working with them to improve. And the last one is helping your mentees embrace failure as growth. We sit in the audience or stare at our computer in this case and see all these people who are so successful. And it's really hard to put yourself in those shoes when you might be having failures. And it's important for people to know that anyone who is in this field has had so many failures, but they're just hidden. So if you fail at something, take that as a lesson and don't dwell on it. I'm terrible at dwelling on failures, but use it as growth and recognize that everybody here has failed as well. The second resource is actually from the National Academies Press, and it's a recent report that gives you a lot of resources of how to improve your mentorship. It talks about why mentorship is important and gives you recommendations and tools to help succeed. So I encourage you to go to that website. I have it listed here below, but I can also put it in the chat box as well. So my last slide is to, again, encourage everyone to take care of each other. And by doing so, you're going to need to embrace and expand your mentoring repertoire. For mentors, please introduce your mentees to your colleagues. It really is the single most important thing that my mentors have done for me. Ask your students and your early career mentees what their career plans are. They might not know yet. You can help them figure it out. For students and early career scientists, tell your mentor what you want. They cannot read your mind. And also recognize that network opportunities are really important. Seek them out. And that you never can have too many mentors. One place that you can find those networking opportunities and potential mentors is through the next generation of lunar scientists and engineers, which Ryan Watkins is going to be talking about next. I've included the web link here, but I also want to put myself out there as an alternative mentor. If you want to know about teaching at a predominantly undergraduate institution, reach out to me. I've included my email address. If you want to know about being in this career with kids, reach out to me. I've included my email address. I'm very, very open about talking about these topics. So I'm offering my services to you. Don't be afraid, reach out. And then to everyone, I want to remind you that there are resources to help you improve. Mentoring and actually improving our mentoring techniques is not something we often talk about, but it's there, it's important to everyone, and it helps to bind us together. So check out that webpage on the National Academies Press and see what you can get from it. So that's all I have, except to leave you with this quote again from Susan Niebuhr, and to remind you to take care of your people. And thank you to those who have mentored me. Without you, I would not have given this talk today, and it means the world to me. Thank you, Greg. That's all I have. Wow,
Amy, thank you. You're getting me all choked up here. This is
my job is done then.
Take care of each other. What a great theme. You know, I think that should be the theme for this entire meeting, quite frankly. So I love it. What a wonderful talk. I don't think I can add anything beyond that. Thank you so much, and congratulations again.
Thank you, Greg.
So I'd like to next introduce Dr. Ryan Watkins. Dr. Watkins' research focuses on integrating remote sensing data sets to characterize the physical and compositional properties of airless bodies, with particular emphasis on the lunar surface. She specializes in using photometry to understand physical and compositional properties of the lunar surface and in integrating planetary data sets to assess landing site safety hazards for future missions. Dr. Watkins obtained dual BS degrees in physics and space science from the Florida Institute of Technology in 2010, and her PhD in Earth and Planetary Science from Washington University in St. Louis in 2015. Before joining PSI as a research scientist, she served as a postdoctoral research associate at WashU in St. Louis with Dr. Bradley Jolliffe, who you'll be hearing from later. Dr. Watkins is actively engaged in service and leadership within the planetary science community. She serves on the organizing committee for the Next Gen Lunar Scientists and Engineers group that Amy just mentioned, on the executive committee for the Lunar Exploration Analysis Group, LEAGUE, on the steering committee for the Equity, Diversity, and Inclusion Working Group, and on Blue Origin's Science Advisory Board for their Blue Moon Lander project. In addition to research and planetary community service, Dr. Watkins regularly participates in education and public outreach in her local community and with the Solar System Exploration Virtual Research, SERVI, Toolbox for Research and Exploration Treks team. SERVI is very pleased to present the Susan Niebuhr Award to Dr. Ryan Watkins. Ryan, please take it away.
All right, are you seeing my slide?
Yes, and we can hear you.
Yeah, so again, thanks Greg, and thanks SERVI. So I will talk for a few minutes. A lot of people know me primarily because of my involvement with the Next Gen group. So I want to spend the next few minutes talking about my vision for the future of the Next Gen, not so much from an organizational point of view, but more from a personal and professional point of view. Before I do that though, I just want to put out a few thank yous to key players along my journey. First and foremost being my family, my parents who are always supportive and encouraged me to pursue my dreams, even if that meant moving far away from them, which I know is difficult. And also for my husband who supported me through every step, including probably doing the crazy act of marrying me 2 months before I defended my PhD. But they have always been there to support me and cheer me on. And kind of like, Amy mentioned, I've had some very great mentors in my life, and I want to call out 2 of them specifically here. First off, being Phil Metzger. I want to thank Phil for giving me my very first research opportunities. Honestly, without those, I don't know that I would be here where I am today. So I want to thank him for always being willing to lay on the floor in buildings to get very cool pictures, as you can see up here. And for just countless conversations and adventures that I will never forget. And then second, my PhD advisor, Brad Jolliffe. I want to thank him for the opportunities he gave me. Like Amy said, he was one of those people that introduced me to his colleagues, and that really made a big difference in my career. Also, thank you for bringing me on to Moonrise before I was even a student. That really laid some of the foundations for where I would go in the future. To being crazy enough to keep me around for a postdoc after I graduated while I secured my own independent funding through PSI. And always looking out for me, and also for knowing the proper way to position me to actually maybe look like I'm a geologist, even though I'm not. And then I also want to thank my support network. So this support network, it fluctuates with time. People come in and out of it. But I just want to call out 4 people who have been really key just over the last couple of years, and especially during this pandemic. These are people who are there to talk science, to talk life, and everything in between. They're the people who encourage me to take a break, go get chocolate or whatever I need to do. I highly recommend getting yourself a group of friends that you can send weekly to-do lists to, who help keep you accountable for meeting your goals, who encourage you, again, to take breaks and to not get too hard on yourself if you maybe don't meet one of your goals. So these are Sarah Valencia, Lillian Ostrach, Erica Jawin, Lauren. And sorry, Erica and Lauren, I didn't have really great pictures of you. And I didn't want to just steal anything off the internet without asking, but you are very much appreciated. And then finally, I want to thank, obviously, Susan Niebuhr, who I unfortunately never had the privilege of knowing, but she was a strong advocate for early career scientists, women, and families in science, which are all topics I care very much about. Her passion, strength, and courage really shone through her words. I spent a lot of time reading her blog this past week. It was obvious that in the midst of her suffering, she was always helping others, and I just wish I'd had the chance to cross paths with her. And then again, thank you to Survey and League for the support of NextGen, and several other people I've listed here that have been key players in my career. So I'll move into trying to quickly talk about kind of my vision for what the NextGen looks like. So the first thing I want to talk about is I want the NextGen to be passionate. So in our statement about who we are, we define the NextGen as an assemblage of grad students, postdocs, and early career scientists who have a passion and vision for lunar science and exploration. And these aren't words that we use lightly. So anyone can look up at the moon in awe, but only those with a true passion for uncovering the mysteries and secrets it holds can truly pave the way for a sustainable return. And I'm talking here about, the NextGen lunar group, but these traits are all applicable for other areas of planetary science as well. I also want them to be diverse. So there's a lot to untangle in the word diverse, and I don't have time to detail every element of diversity that our field needs, but I think most of us are all too aware that our field is too white. We need more Black scientists, more brown scientists, just a wider range of ethnicities, more underrepresented groups in general. We need more people of different social identities, different cultures, different backgrounds that are historically overlooked or marginalized. And I'm not intentionally leaving any one group out here. Obviously, I don't have time to name all of them in one PowerPoint slide in about 30 seconds, but know that if you have skin on your bones, we need you in our field. And I recognize, my privilege as I try to address this issue again in 30 seconds. And I'm not perfect, but I am committed to staying informed and aware. And it is my hope and desire that the NextGen does the same and continues to be outspoken on these issues, and not just outspoken, but active in doing things to change the direction of our field. And I won't spend a lot of time on this element since Amy just covered it very well, but I do want the NextGen to be well mentored. It's possible to be successful without having a good mentor, but quality mentoring just truly enhances the chances for success. And again, I won't belabor this. You can go back and rewatch Amy's talk if you want to hear more about it. I also want them to be well funded. So there are a few programs that exist to financially support early career scientists as we essentially get on our feet after completing our PhDs or postdocs. Susan obviously did a lot to get this started, but soft money early career scientists are often just thrown into competition pools with more experienced scientists. And this isn't saying that we can't write a good proposal or do good science or get funding, but it's just a plain fact that implicit bias exists in our review system, and that name recognition often unintentionally leads to higher funding rates for more established scientists. So I really think we need more programs dedicated to funding early career scientists who do not necessarily rely on successful PI-led proposals being selected or being competed against the rest of the community. And these kinds of programs need to be open for all early career scientists, regardless of their institution type or their career trajectory, which I think is another important element. I also want the NextGen to be accountable. And what do I mean by accountable? It means acknowledging when we make mistakes, whether it's professionally, socially, or culturally. It means accepting responsibility, holding higher positions within our field that obligate us to advocate for continued lunar exploration. It means taking it upon ourselves to ensure that the US has a robust and sustainable lunar exploration program, and to make sure that the planetary science community continues to welcome all people. It also means learning from our mistakes, knowing how to receive constructive criticism, and knowing when to step back and let others take the lead. And finally, I want the NextGen to feel that they belong. And this doesn't mean only belonging to a community with a shared vision, but belonging to a sense of a higher purpose of moving beyond our planet so that we can understand our planet. And a higher purpose of again, advocating for underrepresented groups, a higher purpose of inspiring students and the general public. So what can we do to support the NextGen? First off, let them have other identities beyond just scientists or students. Let them be parents, let them be athletes, whatever it is that fits in their kind of definition of their other identities, like let them be that and support them in that. Foster work-life balance. We could spend a whole hour talking just about that, but there does need to be more support for this work-life balance. Invite them onto mission teams, committees, proposals, strategic action teams, etc. And I know League and Survey have done a great job at this, but there is still room for improvement within the community. Value their time. Don't just assume that because they're early career that they're not busy or they're not committed to things. Obviously, again, invite them to do things, but if they say no because they just don't have the time, like respect that. It's not something to shame them for. And value their contributions. Just because they're early career doesn't mean they don't have things worth of value to contribute, again, to your team, to your committee, to your proposal. And finally, just speak up for them. We need the voices of the more established scientists behind us. And this slide is partly an excuse just to show pictures of my adorable children, but it's also, I just want to say that there are a lot of reasons that I care about early career scientists and the next gen. Again, they're the future of our field. We need to support them as they step into their roles to lead us back to the moon. But I also care because I'm raising the next gen, whether they're next gen, lunar scientists or not. These traits that I've mentioned are things I want them to be. I want them to be passionate. I want them to care about diversity, to be accountable, to be well mentored throughout their lives, and just to feel like they belong in whatever elements that they may go into. So I want others to value them, and I want them to see that hopefully their mother did all she could to advocate for them and for others, much of the way Susan Niebuhr did. And I just kind of want to end it on that note again with a little tribute to Susan and a big thank you for all that she did to support early career scientists. So again, thank you, Greg, and thank you, Survey.
And thank you, Ryan. And what a wonderful talk. What two wonderful talks. I just take so much out of what both of you said, and what a privilege it is for me personally to have been able to work with you, Ryan, and you, Amy. I'll just share the very quick story that Clive and I chaired a certain workshop a couple of years ago, and as you well remember, and you, Sarah and Erica, were the people that I would say made the workshop a success. Is really the bottom line, and I've been telling everyone that I have every confidence in the next generation, and for me, I consider that helping the next generation is the most important thing I do, and I know a lot of other people who feel exactly the same. So anyway, what an honor it is to bestow these awards on two such deserving people. So thank you so much. I'm going to turn it over now to Brian Day to introduce the next awardee.
Thank you, Greg. The Servi Angioletta Corradini Mid-Career Award is given annually to a mid-career scientist for broad, lasting accomplishments related to Servi fields of interest. Angioletta Corradini, who is with us from 1946 through 2011, was an Italian planetary scientist who has inspired astronomers around the world. The 2019 Angioletta Corradini Mid-Career Award is given to Dr. Harold Hiesinger, Professor of Geological Planetology at the University of Münster in Germany. Professor Hiesinger is a person known for his curiosity. He enjoys finding out how things work. He is a member of both the American and European Geophysical Unions and the Geologic Society of America. He has been recognized with multiple achievement awards from the European Space Agency and has received NASA Group Achievement Awards as part of the Dawn Mission Science Team and the Lunar Reconnaissance Orbiter Team. He is a participating scientist for ExoMars and JUICE, two upcoming ESA missions to Mars and the Jupiter system. In 2014, the International Astronomical Union named asteroid 26811 Hiesinger after him. He has been a strong collaborator with Servi teams. His research into planetary processes and the geologic evolution of terrestrial planets and moons has advanced our understanding of the lunar chronology and helped constrain the age of the South Pole Aitken Basin and other potential lunar landing sites. He recently detailed mission preparations for commercial in situ resource utilization demonstration and is engaged in a wide array of other projects, including astronaut training. After 30 years in planetary sciences, he still loves his job and hopes to play a role in returning astronauts to the moon and beyond. I'm sure he will. In addition to being widely published and credited with numerous journal articles, his many contributions and achievements make him a worthy recipient of the 2020 Angioletta Corradini Mid-Career Award. Herzlichen Glückwunsch, mein Freund. Sie verdienen diese Auszeichnung. Doch. Congratulations, Harry.
Thank you very, very much, Brian. So I hope you can see my presentation now.
Not quite yet.
Can you not see it?
I can see it, but it's in slide.
Okay.
There we go.
There we go. Okay.
We see the presenter view, Harry.
Pardon? The presenter view. Oh.
Yeah.
How do I do this then?
Yeah, within PowerPoint.
You can go and swap displays.
Does this help? Okay.
That's perfect.
All right, sorry for this. So what I'm gonna try to do is sort of, yeah, a little bit of retrospective things, and then also, of course, some forward looking. So I try to give you a personal mid-career reflection. Before I do this, of course, I would like to thank a couple of people. First of all, of course, the Corradini family. I've known actually Angioletta a little bit, okay, when I was a young graduate student. She often visited Gerhard Neukum, one of my mentors and advisor. And of course, we weren't really talking to each other because she was basically playing in the major league, really advancing planetary sciences in Europe quite a bit, whereas I was basically as a young graduate student playing rookie league. So, but I can tell you that Gerhard Neukum really respected her because she was a very influential person, very straightforward, and just a great advocate for planetary sciences in Europe. I would also like to thank, of course, Servi for handing me this award. And as Greg said in the beginning, you know, the nominations come from you. So thank you, all my colleagues, all my friends, and I have hopefully many of those among you. And of course, also my mentors. And not the last, you know, of course, thanks to Carolyn and my two kids that sort of have to live with, that I'm gone for quite a while, and of course also my dad and my mom. So mentors, yes, very, very important. I had the luck that I had really three very influential, very, very great mentors. First of all, Gerhard Neukum, that many of you know. He taught me that you have to fight for the things that you really want, and you cannot let go before you get what you want, okay? And he also was brave enough to stand up for his opinions and tell people that they are wrong, okay? This is one of the famous quotes that a lot of you probably have in mind when you think about Gerhard Neukum. And I think this is really, really important. And of course, Ralf Jaumann, who involved me or got me the chance to be part of many, many space missions, who actually helped me with writing my thesis, you know, by commenting on early drafts and so forth. And finally, Jim had, you know, who opened an entire new universe for me when I was able to work for him for a couple of years. So thank you all. And also thank you to all the other people that who inspired me. So if you are at the beginning of your career, you have to make a couple of choices. And I would like to start out with this poem by Robert Frost from 1916, where he describes basically two guys that go down a wooded pathway and then come to a junction. And so you have to make a decision. And when you look down the pathways, yeah, you cannot look all the way to their end. You cannot look into the future too much, but nevertheless, you have to make a decision. And so the really important part that sort of comes close to what I'm doing or what I was experiencing is, are the last three lines. Two roads diverged in a wood, and I took the one less traveled by, and that has made all the difference. Okay, so let's look at a little bit in my career, what were actually the choices and the paths that I took. So here you see me, that's me here, okay, close to a keg of excellent Bavarian beer. So the first choice would have been to become an alcoholic, having access to lots of excellent beer. But I did not take this road and instead took another road. So for a long time as a little kid, I thought I would become a caterpillar driver in Africa. Well, that didn't really materialize. And then after that, first career end, I had really for a long time no idea what I should do. So through my entire high school career, I just didn't think about what I want to do. And then all of a sudden, the second career, going to high school, was over. So then what to do? Well, I decided to become an Air Force officer. So I went to the test, failed it miserably. So I have it now in writing that I'm too stupid to be a German Air Force officer. So that's something that you have to stand up again and move on. So then I thought, maybe it's a cool thing to become a veterinarian. But there, my high school grades were not good enough. So that was also a very short career. And so finally, I started studying geology at the University of Munich, and I loved it from day on, from the first day on. So at the end, I tried to get the PhD in ore mining, but there was no funding in this. So that's how I ended up in planetary sciences. So I'm clearly the kid that did not dream about becoming a planetary scientist from this age on, but came to the business fairly late. Then, of course, at some point you have to decide, and I got married. I went sailing a lot, which resulted in a very long PhD. It took me 9 years and also resulted in divorcing my first wife. So what a great time then to move to Brown. And so I met just an incredible set of people there. Jim had Carly Peters, Pete Schultz, Jack Mustard, and of course all the fantastic grad students that really changed my perspective. And that's when my career really, really took off. I got married with one of the Brown family members, Carolyn. Excellent choice. We are married now for 20 years, but it also meant that we got into this classical two-body problem. So Carolyn was commuting to New York. I was commuting in the other direction. That was really very, very difficult during the times when I was a professor at Central Connecticut State. And so we were both quite happy that we got the opportunity to move to Germany to the Institute for Planetology in Münster. And so now we also have 2 kids, the next gen that was just mentioned. Actually, Carolyn, of course, got the kids. And I don't know where my future will be. I cannot look down far enough the past, but I have a little coffee mug with a cartoon on it that says basically basketball, football, baseball, retirement, golf, death. So mid-career would bring me somewhere into the baseball area. But actually, if I think about it, I think I'm more like in the basketball and football league, but we will see. Okay. So a little bit about science. What are my interests? Well, a lot of people know me best probably for the work that I do on the chronology of planets, but in fact, I'm much more broadly oriented. I published a number of papers on various topics, and that's one of the big lessons that I learned in my career, that you cannot build a career on just one topic and one planet. So you have to think broader. You have to expand to many different planets, work on many different topics. And that is also reflected in all these missions that I'm involved in. And what I really enjoy, what comes with all these missions is the international collaboration across any culture, across any color of your skin, across any religion. It all doesn't matter because we are all scientists, and that's just beautiful. And so also I do a lot of work on terrestrial analogs. Again, pretty much anywhere I can get to, Svalbard, the Reese Crater, China, and of course that results in a lot of publications so far. But what's also very dear to my heart is that I would like to serve the community and inspire the next generation. I'm trying hard to provide good and exciting teaching, and also what was mentioned earlier, providing a network or building bridges and providing opportunities for the next generation. And in general, promoting science, very, very dear to my heart. And Brian mentioned it, remain curious. You know, I always wonder what would happen if you could just keep the curiosity of a 5 or 6-year-old across the teens, you know, when they all of a sudden it becomes uncool to ask questions. If you ask questions, you will find interesting topics and you will find interesting challenges. Okay, so just a really quick science slide just to show what we did over the last 30 years. If this is a midterm thing, if you just look at the colored surfaces, a lot of the area on the moon is still not colored. So there's still a lot of work to be done. Okay, and I guess I have to hurry up finishing all the rest of the moon by the end of my career. So let's just step back a little bit and not talk more about the science that I do, but some sort of general thoughts, you know, why I think science is important to us, why I think science matters, and how it relates to our society. So as planetologists, we are all very good in problem-solving thinking because we usually have only limited amount of data available, but still have to figure out how things work. So that makes us, in my opinion, really good leaders. So this would be this bear here, this polar bear. We might not always know where we're going exactly, but we have a good idea of our environment, of the context, if you will, and we will find out a way of different problems. Other people, politics, society, they might get into deep water, you know, and if the water is up to their necks, then in an ideal case, they would look to scientists for answers. And this was what happened over the last couple of 100 years. But nowadays, with fake news and so forth, politics and also society sort of doesn't see scientists as leaders anymore. And this is really something that concerns me and this is highly frustrating to me. And I think we need to work on this. So this is a diagram that I stole from Jim Head. It sort of shows time on the x-axis and space on the y-axis. And most people obviously are concerned about themselves. So it's all about me. You know, do I have enough bread at home? How do I get my kids to piano lesson or to soccer lesson? That's what we are usually operating in this little part of the diagram. But as planetologists, you know, we are not concerned about this. We are concerned about stuff that is up here somewhere or even beyond that. So we really have to step back and think hard what we can learn from planets that affect our planet here, our Earth, our daily life. So think big. And for that, I think you also have to leave your comfort zone. You know, you have to go out and challenge yourself. And that might be very difficult. You might get answers that you don't like, and you might have to change your personal life to save the planet, if you will. So, and that's also reflected then, of course, in this sapere aude from Horace, which means basically dare to be wise. So see the big picture. If you start or if you continue burning fossil fuels at the rate as we do now, this will end up in a very bad situation. So it's not sustainable. And that's what we need to consider and where planets can teach us. Okay. And we have to stand up. This was already mentioned before. And I just took a quote from Gene Kranz, you know, after the Apollo 1 disaster, you know, where basically says, yeah, we did not do our job. We did not stand up. So we should be, as scientists nowadays, we should be the ones that stand up and say, damn it, stop what you're doing. Okay, we are moving in the wrong direction. So tough and competent, those are the really important words. And tough here means, you know, being held accountable and never compromise your responsibilities. So we have responsibilities as scientists that we have to fulfill. And anytime we walk into mission control or anytime we talk to the press, anytime we deal with the public, we will have to know what we are standing for. Competence means that we never take anything granted and that we, you know, that we keep searching, that we educate ourselves. And so I think this is really a great quote that guides my sort of thinking. And in fact, I went into my office and I just did that. I wrote it on my blackboard or on my whiteboard actually, and it will remind me that what we as scientists stand for. So there are numerous obviously problems, big problems that we can address. Here's just a glacier in Svalbard. And we go to this area now for a couple of years. And since 2011, this glacier retreated by almost 2 kilometers. Okay, so climate change, burning fossil fuels. This is obviously a huge problem that we have to solve, that we have to address. And where even Mars or other planets might help solving us. What will happen if we get a more and more pronounced greenhouse effect here on this planet? Well, go to Venus. There you have it. You know, this is the super greenhouse planet. Mars, on the other hand, also indication for lots of climate change, maybe even more radical than what we experience right now. But the outcome is not pretty. The other question that we, of course, can address as planetologists is life. You know, how did it evolve and how did it develop? So if you look at the Earth record, we see that there were periods where lots and lots of species got extinct, some by large volcanic eruptions, some by impacts. But we only have a very sort of limited record of history, let's say the last 600 million years, where we have good record. But look at this, the entire half of this diagram is empty. Okay, so there is almost no information that we can learn from Earth. So that's where the planets help us to fill in this part of information. And when you do this, you end up at times where life actually started. Okay, and so how is the beginning of life related, for example, with the impact flux that happened early on? Is there really this spike that frustrated life very early on, or is this cataclysm not really existent? So those are really important questions that I think we need to work on. And then, so for the last couple of minutes, a little bit of outlook. Well, obviously, this is one of my favorite slides because the moon here is very prominently featured, okay? And so as a person that worked a lot on the moon, I would actually like to see that we go back to the moon. So forward to the moon, if you will, with humans. And I'm just hoping that I can play a little role in sending back humans to the moon and maybe beyond, you know, maybe at the end of my career, we will be at Mars. Sample return mission and space missions to multiple bodies. Yes, I would dream about, or I'm dreaming about this, because this is really key to understand our own planet. And all this, of course, requires a solid international space program. And I think we need some altruism in terms of international collaboration and cooperation. So I really like the "for all mankind" quote from the Apollo times. It is really for everybody on this planet. And so this is really dear to my heart. And then there are other things that are equally interesting, but the more important ones are certainly up there. And for the sake of time, I'm not really talking about this, but maybe just the improved funding and the improvement in the educational system. This is particularly in Europe extremely important because we don't have many resources. The only thing that we have in Europe are our brains, and that's where we should invest our money to get better trained students and better trained next generation scientists. And then, of course, on a personal level, I would wish for many, many more collaborations with the planetary community and the continued friendship with many of you. And of course, tons of new exciting science results. And there are tons of them out there, believe me. So that brings me to the end, basically. And I started with a poem from Robert Frost, and I would actually like to end with a poem from Robert Frost. You can read here, it's much longer, of course. This is just the last 4 lines. And I would actually like to rephrase this and put it in our contents. So science is lovely, dark, and deep, but we all have promises to keep, and miles to go before I sleep, and miles to go before I sleep. Thank you very much.
Thank you, Harry. That was wonderful. Very, very inspiring, and I appreciate it. And congratulations from me. So with that, we are running a little bit late, but these talks have been fabulous. And so we're going to carve a little bit of time off of our breaks and continue on with the awards that we have to give today. It's my pleasure to be announcing the Michael J. Wargo Science Award, Exploration Science Award. And this is an award given by CERVI to a scientist or engineer who has significantly contributed to the integration of exploration and planetary science throughout their career. Dr. Wargo was an outgoing and strong advocate for the integration of science, engineering, and technology. He worked closely with planetary researchers, especially in the lunar and Mars science communities, to develop collaborative and highly productive missions. He also provided guidance and direction of our predecessor institute, the NASA Lunar Science Institute, and the creation of CERVI. Dr. Wargo was a shining example of collaboration and open communication that has inspired many scientists and engineers. And so it is my pleasure to award the 2020 Michael J. Wargo Exploration Science Award to Dr. Mark Robinson. Dr. Robinson is a professor of Geologic Sciences in Arizona State University's School of Earth and Science Exploration. He is a member of the NASA Advisory Council and serves as a principal investigator for the imaging system on NASA's Lunar Reconnaissance Orbiter. LRO has collected a treasure trove of data and is making an invaluable contribution to our knowledge about Moon, as you all know well. Dr. Robinson's stewardship of this instrument has enabled numerous groundbreaking discoveries that has created a new picture of the Moon as a dynamic and complex body. Throughout his career, his investigations have used a variety of remote sensing techniques and data sets from dozens of NASA missions. He worked on the Clementine mission, which provided our first complete look at the lunar surface, including the poles, and found evidence of ice in the bottom of the permanently shadowed crater at the Moon's south pole. His collaborative research on old data resurrected from the Mariner 10 to Mercury missions extracted compositional information about the surface rocks that had laid hidden in the old data for roughly 20 years. Much of his current research efforts focus on expanding our knowledge of the lunar surface, paving the way for future human and robotic exploration of the Moon. His discoveries and research developments have set a scientific framework through which to challenge and improve our understanding of the processes throughout the solar system. With that, I'd like to congratulate you, Dr. Robinson, and offer you the floor to present your thoughts.
Okay, thank you very much for those nice words, and I will try to get the share screen to work. Okay. Pointer.
That looks great.
I'm trying to get the laser pointer here to work. Okay, cool. I think we're set.
Okay.
Okay, again, thank you very much. I'm going to talk about Mike mostly because he was an incredible force of good. And what you see in the background here is Wargo Crater, which was named for Mike 3 or 4 years ago. And I helped select the crater, and I thought it was an incredibly appropriate crater. In fact, it was our second choice because the first choice was overruled by the IAU due to some obscure, I can't remember now, it doesn't matter. But the reason I love this crater for Mike is because it's full of geologic landforms that represent what happens during these incredibly energetic events that shape the solar system, basically. And I know he would have been asking lots of questions as we, of how the crater formed and how all those landforms, and I'll get into that in a minute. But I thought this was a great picture. I remember this moment when Mike appeared on the screen at a survey meeting in 2012. And we always like to laugh about it. It was the Big Head Mike talk. And it was, as usual, incredibly entertaining because that's just the kind of guy he was. But he always brought a sense of competence to whatever he was doing. And in fact, earlier today, I was sitting down here trying to think of what would be 3 words that I would use to describe Mike. And what I came up with was competent, curious, and fun. So I think that really summarizes at least my experience with Mike. I know everybody's, humans are very complex and they have all different sides. But I really think that that sums Mike up as competent, curious, and fun. And he brought that into everything that he did. And here's a picture of Wargo Crater, a little, that same picture, a little background. It's 14 kilometers in diameter to give you a sense of scale. And it's superimposed on Jewel T Crater. So even though Wargo Crater is much smaller, it somewhat dominates this bigger crater, Jewel T. And as I was mentioning earlier, here's these amazing array of landforms that I think we're way behind. I was going to talk about them somewhat, but I think it's more fun to talk about Wargo stories. But just to give you some sense of relief, that back wall from here to there is 3,200 meters, or for those of you who don't think in meters, that's 10,000 feet tall. It's crazy big. It's a wonderful crater. And you'll see this link down here in the bottom left. While I'm talking, if you get bored, it'll be on the next several slides. You can go to Quick Map, and this will bring up Wargo Crater, and you can zoom around and look at it in detail. Let's see, here's, we're zooming in a little bit more. Again, the scale is 14 kilometers across. And the other day when I was starting to put this talk together, I really had a chuckle to myself, or I guess as all the next gen would say, an LOL. When I saw this impact melt that was splashed out of the crater, because it reminded me of the day that I met Mike. And that we had a meeting in NASA headquarters in some ridiculously small rectangular room. It was like 2 feet on either side of a table. And the room was full. There was about 10 people in there, and there were 10 chairs, but there's only 9 people there. But of course, the 10th chair was on the opposite side of the table. So Mike, always a dominating force for good, when he walked into the room, had this big leather briefcase type thing that he had, and a binder, and a giant cup of coffee. And so he had to suck up, walk around, go all the way around to the other side, getting behind people. And when he finally was able to get down in his chair, as he was putting all of his stuff down, that giant mug of coffee went. I was sitting exactly across the table from him, and it was much like this crater, this tidal wave of impact melt. Coffee came across the table. Fortunately, I was able to push my chair back in time. It all went down on the floor. But that was just a Wargo story that, and of course, he felt terrible, but we all laughed about it and liked to joke about it for years afterwards. So that's the Wargo coffee spill. Here's, as we zoom in closer and closer with the LROC images, there's all sorts of geologic landforms related to impact melt. Here's a crater that formed, it's about 150 meters in diameter after the impact melt hardened, because you can see the eject on it, and it gives you insight into how craters form on coherent materials relative to how they form on granular ejecta. Here's where impact melt sloshed up and then came back down and formed what we have called fences. We've seen these in many different places on the moon. I think the most famous example is in the Highland Ponds, which I remember talking to Mike about that. It was a bizarre discovery, which we now believe is impact melt from Tycho Crater on the other side of the moon. And again, you can see all the small little impact craters that formed subsequently, but I know we're running way behind, so I'm just going to skip on a bit. Again, here's that link if you want to go to Quick Map and explore Wargo Crater in more detail. What we're seeing right now is about 5 kilometers in diameter. Here we've gone all the way down to the full resolution of the SNAC image. Okay, Michael was always positive, no matter what happened in the meeting, and he was always paying attention. I don't know how many of you have been in long NASA meetings that last all day and your mind starts to wander off into the weeds somewhere, or I've never done this, but you actually start to nod off. That was not Mike. He was always paying attention. And I think I have a couple minutes to tell this fantastic story about, this was at the LROC Preliminary Design Review. And I was a new PI. So I was somewhat nervous. Are we actually going to pass this review? Because if you don't pass the review, then that means that the, potentially would mean that the instrument gets canceled and it's not going to fly. So one of the engineers at MS Cubed, who's incredibly competent, got up there and he was talking about the electronics that run the LROC experiment. It's the SCS. And that there was a worry that it was sensitive to radiation hits, would result in single event upsets, causing the camera to go into a stupid state. But it wouldn't damage anything. And so our strategy was just to power cycle the camera every orbit, which is every 2 hours. And that way, if the camera did go into a stupid mode, it would recover and everything would be fine. And the worst case scenario is we would lose 2 hours at the most of imaging. And someone in the review panel asked this engineer a very pointed question in a very pointed way. Aren't you worried about damaging your instrument by power cycling it so frequently? And this incredibly competent engineer from MS Cubed, I think, took exception to the question. And he crossed his arms and just kind of stared at the floor about 20 or 30 feet in front of him, and he was turning beet red. And I'm sitting in the back of the room thinking, oh my God, what's going to happen? Have they exposed a flaw in the design? What is this engineer going to say? So finally, after what seemed like a day, but it was about 30 seconds, the response was, don't you think you really ought to be in a different line of work if you design an instrument that's damaged by power cycling? He didn't look at anybody. And after that, the room was dead silent. You could hear a pin drop, and I'm sitting in the back of the room melting, right? Oh no, he just sank us. And of course, Mike, I can't remember what he said, but it doesn't matter. But in his usual positive way, he spoke up, said something that caused the whole room to erupt in laughter, not making fun of anybody, pointing out some positive aspect. And we just moved on, and it was not an issue, right? And he did that repeatedly. That was his role. One of his big roles in these meetings is to keep the ball rolling. It was just, a wonderful part of his personality. Okay, and then, again, these endless meetings, there he is, again, always paying attention, always asking, insightful questions and keeping the meeting rolling. This was back in 2008, I believe, when we were working on this LMMP project, which was to take data and make maps, which is still ongoing today, 12 years later. Okay, Mike and I really saw eye to eye on a lot of things, and he joined the project. I can't remember the year, but it must have been 2006 or 2007. But one of the things that we really like to talk about and agreed on is that there was this artificial division between NASA's exploration side and the science side. And back in those days, the human exploration side was actually called ESMD, Exploration Systems Mission Directorate. And then the science side, as it is still today, the SMD, or Science Mission Directorate. And ever since going back into the NEAR project, it was always on my mind that it seemed like there was this engineering side of the fence and the science side of the fence, and there wasn't a lot of opportunity for them to speak. And, that was a lot of it, it was understandable. It was just the way institutions are set up physically, and also budgets are set up. But I had this great experience on the NEAR project where I was given complete freedom at APL. I was a free-ranging scientist. Even though I did not work there, I spent a huge amount of time there while we were doing the NEAR mission and while we were developing the messenger mission, the messenger proposals. And I spent a huge amount of time knocking on doors, sitting in engineers' offices, asking them questions about how does this work? And they were always incredibly patient with me. It was like, oh, a scientist, you're interested in what I do? And so that's how I became sort of a junior engineer. And it's been really great for my career because it really helps me understanding how to think about missions in a realistic way and how to get the questions answered. So this, when LRO started and I was trying to come up with a logo or a patch, as people like to call it, for the LROC experiment, it was a group effort with the team. I always try to do things as a group effort, but I had a few ground rules of what was going to be on the patch. And one of them was science enables exploration and exploration enables science. Remember, this goes back to the ESMD versus SMD days. And I really wanted to emphasize the fact that this mission, this LRO mission, was the epitome of what I had wanted to happen, was the merging of ESMD and SMD, because ESMD was paying for the mission and they built the spacecraft. And after a year, they turned it over to the science side, which is SMD. So it was really a fantastic opportunity. And then when I was looking at patches from the Apollo era, some of my favorite slogans, logos, or whatever, were in Latin. So we translated that thought into Latin, and that's how that got on the patch. And Mike really, that really resonated with him, and he liked to use the science enables exploration, exploration enables science in public talks and in NASA meetings and so on and so forth. And so that's really the story of where that comes from and how much Mike and I got along. And it's not only just Mike and I, it's the LRO project. She really took to heart what LRO was doing, which is supporting a human return to the moon and enabling NASA to work towards getting the most science out of this return to the moon. And, you know, the LRO project really appreciated his tireless and positive efforts, and we certainly miss him dearly. But we've come full circle now. LRO is again providing key observations for human return to the moon. And as an example of that, this picture just came down a month ago, 8th of June, 2020. This is the Shackleton Deger Latch Ridge. You know, somewhere in here, I think that's the most, I was going to say logical, but I don't want to use that word, most popular thought for where the landing site will be, somewhere on this ridge, which, you know, maybe on the other side, maybe right here. But the fact remains that due to LRO, we have the data, and also the other international missions that have been returning data for the last decade. We have the ability to really make smart decisions about where to go. So the science that we've returned from the LRO mission is really enabling this return to the moon, this human exploration of the moon. So it's very gratifying to me, and I wish Mike were here to see that we have come full circle. And with that, I will call it a talk. Thank you very much, and thank you for the award.
Great. Thank you. Thank you so much, Mark. Congratulations to you and Harry both, and thank you for sharing the story about science enabling exploration and exploration enabling science. That is really the foundational principle on which our institute is based. So it's great to hear that, and I have a lot of Mike's stories as well, but I won't share them in the interest of time. So thank you, and congratulations to both of you. So I would now like to introduce the final award, and it's the Eugene Shoemaker Medal. Before I do that, I'm just going to mention that I'm quite aware that we're late, and what we're going to be doing is taking time out of the breaks and shifting things to the right a little bit. So so we will adjust when we get to the sessions. So the Eugene Shoemaker Distinguished Scientist Medal is the final award of the day. and it's named after American geologist and one of the founders of planetary science itself, Eugene Shoemaker, who lived from 1928 through 1997. This year, it's awarded to Bradley L. Jolliffe for his significant scientific contributions throughout the course of his career. And the award includes a certificate as well as a medal with the Shakespearean quote, "And he will make the face of heaven so fine that all the world will be in love with night." Dr. Bradley L. Jolliffe is professor of Earth and Planetary Sciences and director of the McDonald Center for Space Sciences at Washington University. He received his doctorate from South Dakota School of Mines and Technology, and his research is focused on the study of minerals and rocks of the Earth, Moon, Mars, and meteorites, and what they reveal about conditions of formations and planetary processes over the past 4.5 billion years. As a member of the LRO camera science team, he investigates the surface of the moon, relating what can be seen from orbit to what is known about the moon through the study of lunar meteorites and Apollo samples. He's made significant scientific contributions in sample analysis, surface science, and remote sensing, as well as laboratory studies. Professor Jolliffe also leads the Washington University team that is part of NASA's Apollo Next Generation Sample Analysis program that you heard about earlier. Survey is very pleased to present Professor Jolliffe with the 2020 Eugene Shoemaker Distinguished Scientist Medal. Congratulations, Brad.
Thank you, Greg. Let me see if I can share my screen. See somebody, here we go. And, I got to stop sharing to get my video on. And presenter view. Okay, quick sound check and video check.
Gotcha.
Okay.
You're actually not in the presentation view. You're in the presenter view, so you might want to change that.
Let's see if we can get it to. Okay.
Slideshow, yeah, that should do it. Oh.
Just hit the swap displays button at the top of that screen.
Hit the which button?
Swap displays.
Oh, I see what you, yeah, I think I know what the problem is. So sorry. Try one more time. Let's see. Well, that probably isn't doing it yet, right?
Yeah, that was looking fine.
Yeah, that looked good.
Yeah, hang on a sec though. So sorry. Let me see if I can do this. Let's see. Is it sharing now?
Not yet.
No.
Let me try this one more time. How about, well, what do you see now?
Just seeing you.
So sorry.
Not seeing a screen. You can go to one of the other views. That's okay.
Yeah, let's see if we can get it going now. I think if we do this and then at the top.
There you go. That's
it's
fine.
looking fine now.
That's good.
Oh, okay. You can see that. Okay. Yeah. All right. Well, thank you very much, Greg. And thanks very, very much to the nominators and the awards committee. I'm totally honored and I'm totally humbled by receiving this award. Just in thinking about those who have won the award before me, they're all my heroes and they're all wonderful, wonderful people that I look up to. There's a picture of Gene Shoemaker that I love. He's sitting at the microscope there. Gene challenged us in many ways. He was persistent. He never stopped exploring. Don't forget your roots. And just really a wonderful person. I got to meet Gene when he visited Washington University in the early 90s to give a distinguished lecture. And I count it as really, he's one of my great heroes. I'm going to, and I should mention that last year's recipient, Harrison Schmidt, Jack Schmidt, again, one of my great heroes, and one who I count myself very fortunate to have been able to meet and work with in my career in a number of different situations. And that sort of leads me to what I want to say in these remarks. The real reward of doing science is not great research. It's not the great discoveries that you make or the publication count that you get. It's the people that you're fortunate enough to meet and to work with and to call friends and colleagues. So let me just go back and say that when I first got into this game, I was working on terrestrial projects. You can tell that this is not the moon. The little inset there shows a huge tourmaline spray and a rare element pegmatite in the Black Hills. This was not the moon. But my advisor as a graduate student, Dr. Jim Popike, led me, and he gave me the start, I think, of an interest in the moon in talking about the use of minerals such as pyroxene as recorders of petrogenetic processes. And I really came to love that. And you could see another person there I worked with, young research scientist working with the group at that time, none other than Chip Shearer. So I was very fortunate to, and I also want to indicate that there's some serendipity here. I was not necessarily looking to work in planetary science, but the opportunity came up to go and work with Larry Haskin and Randy Korotev at Washington University. So Larry was my postdoc mentor. There he is in the upper right. Wonderful, wonderful person. Passed away in the mid 2000s, and we dearly miss him. And there's Larry and Randy together at a photograph in the Black Hills on a field trip. I learned a tremendous amount from these two and still work with Randy. We've been working together now for over 3 decades, and it's just a wonderful, wonderful relationship. Okay, so at Washington University, I got to work with some other young scientists whose names you will recognize. Mark Wazarek, who as a grad student with Roger Phillips, brought geophysics to our group, along with a fierce loyalty to the moon that even Roger had trouble understanding. Jeff Gillis, now Jeff Gillis Davis, who had worked with Paul Spudis and the Clementine mission, came our way and introduced me to lunar photogeology. And we got involved in working with the Lunar Prospector mission and the likes of good friends now like David Lawrence, Rick Elphick, and Tom Prettyman. Then I got my introduction to working with remote sensing data through a collaboration, again, serendipity. I got hooked up with Paul Lucy and Dave Blewett, looking at Clementine data and trying to correlate the orbital data to ground truth samples. So we were looking at the iron and titanium mapping effort in these times. And this led to a long-standing collaboration with this fellow shown in the lower part there, Mark Robinson, who you've just heard from. And of course, I've later had the good fortune to become part of the Lunar Orbiter Camera science team, and that's been fantastic. Great group of co-Is, researchers, and students. Then this fellow in the upper right there, Ryan Ziegler, now the Apollo Sample Curator at Johnson Space Center. He was Larry Haskin's last PhD student, but he worked alongside Randy and me, developed a love of working with the lunar samples, Apollo samples and lunar meteorites that rivaled even my own, and in fact surpassed my own, I think. Ryan and I got hooked up with wonderful colleagues in Beijing, and you see the paper in the lower part there, and Professor Dunyi Liu, who runs the Beijing Shrimp Center, and had a really great collaboration that continues to this day. And this was introduced to us by my longtime colleague at Washington University, Professor Alian Wong, who, by the way, joined our group when I was working with Larry Haskin to show us that we could use laser Raman spectroscopy to explore lunar mineralogy. So the Moonrise mission proposals, I have to mention something about this. Moonrise consumed almost 2 decades of my life, I think, but this was another great highlight of my career, owing to the fantastic group of scientists and engineers that I got to meet and work with closely at the Jet Propulsion Lab, working with Lockheed Martin. Whether or not we got the mission, this was just a wonderful group of individuals to get to work with. And you can look down through those names and you see quite a few. I would just point out that some of the individuals, such as Carly Peters and Jim Head at Brown University, have just been longtime collaborators. And I think I've gotten to know each and every one of their students who have graduated with them. Fantastic group. And I would be remiss if I didn't mention the great group of engineers at JPL, led by this fellow, Dr. Leon Alkali, a great friend of the moon and a great friend of Moonrise. So now we come to sort of the best part, the best reward for somebody who has hair that is turning the color that mine is. In the past 10 years or so, I've had a wonderful, wonderful group of students that I've been fortunate enough to work with. Steve Sedio, highlighted here, took up my love of granite, lunar granite that is, and worked on these samples. There you see a beautiful lunar granite on the left, backscattered electron image in the middle. And on the right, the results, Steve used the electron microprobe to date uranium lead age dating 3 different minerals in one of the granite samples and actually got a concordant age at around 3.9 billion years. So that's fantastic. The other thing that has really been great for me is having a wonderful lab manager in the electron probe lab, and that's Paul Carpenter. So then moving on, here you heard from Ryan Clegg Watkins earlier today. Ryan came to Washington University with an intense focus on the moon, a love for the moon, and got into working on the photometry of the blast zones around the Apollo landing sites. Who knew we would get into such kinds of things? Mike Zanetti came and got our group into crater counting, thanks to another person you've heard from, Harry Hiesinger, and there's Carolyn Vanderbogert as well, who trained Mike and then sent him our way. Juana Coleman, she followed up some of the LROC studies on the titanium content of the moon using LROC data by using some laboratory spectral analysis. Very nice work. And then Sarah Valencia. Sarah has an unparalleled love of sample analysis, especially with the electron microprobe, and she made the Northwest Africa 773 clan meteorites her thing and published a beautiful paper on this. And she's also doing some tremendous work on another beautiful Apollo sample, 12013. Catherine Shirley, upper left there, was an undergraduate working with me on LROC projects and actually took up the challenge to determine the age of the Compton-Belkovich volcanic complex. Catherine recently finished her PhD with Tim Glotch at Stony Brook. Amanda Stotterman, also working as a graduate, as an undergrad at the time, but now at the University of Arizona, took on the reanalysis of the youngest basalts south of the Aristarchus Plateau, the P60 region. Very, very nice paper. And then again, at the bottom, you see another of Ryan's papers and a list of co-authors that includes some of the LRO team, Tom Jaguar, Julie Stopar, and Sam Lawrence. We've just benefited so much from having this great group of collaborators. Then I would just say at the very end here, to my friends and colleagues and all you lunatics, thank you so much. And I would just also add that for my current students and recent students who graduated a year ago, Michael Bouchard and Tim Hahn, also current students, Emily Cully and Chris Yen. This is just the best that you can have when your students are so wonderfully independent And I just, wish them all the best going forward, and all of you folks. And let's get back to the moon. Thank you.
Thank you so much, Brad, for another wonderful talk, and congratulations on receiving this medal. And one thing that I can reflect on quite briefly here is that in each of these talks, there's been a theme, and that's that it's all about the people. So all of us here are interested in these things, but we all support each other. And I'm not a lunatic by training, but I have been adopted, I suppose you might say, and I love this community, and it's just such an honor helping support it and working with all of you fantastic people. So congratulations again to all the awardees. And if I could ask all of the awardees, as well as Brian and Christina from Service Central, to turn their cameras on, and Ricky, we can get a group shot, and then we can move on with the program. I do apologize. I know that we're quite late here. We'll make up for it in part with the breaks. So let's see. Mark, great. And okay, I believe we have everyone, Ricky. So just let us know when you're done.
Okay, great. Thank you.
You got it?
Yes.
Excellent. Excellent. Thank you. All right. Well, congratulations again, everyone. And I will turn it over to the next session.
Greg, if I may, we should probably let everyone know that while we were managing the awards, the parallel session 2 did start. So if there was a talk that you intended to go see, apologies, but we are recording everything, and it will be made available, and you can reach out to the speakers. But go ahead and jump in there. I don't think they're completely done, and we can get started with the parallel session 1 now. Do we have Carrie and Jennifer? Go ahead.
Yeah, I'm here.
Okay.
Carrie's here.
Great. Thank you.
Okay, so I guess I'll start this off just welcoming everyone to parallel session number 1, which is the solar system history. I'm Carrie Donaldson Hanna from the University of Central Florida, and I'll be sharing duties with Jenny Larson, a grad student also at UCF. Unfortunately, our first talk by Anna Galliano has been canceled. And so given the extra time, we're going to have oral presentations in this session, which will be 10 minutes long with 4 minutes for question and answer. We will give speakers a warning at 8, 10, and 14 minutes, just so you know how your timing is going. For all speakers, do make sure to turn on your camera if your bandwidth allows, and be prepared to start your talk when your time slot starts. And we do ask for all speakers to stick around in the Zoom room during the discussion period to answer any remaining questions. For those of you in the audience, please mute yourself and keep your video off. And if you have any questions, please raise your hand using the Zoom tool, and we'll call on you in the order hands are raised. If you prefer, you can use the chat window to write your question, and we'll ask the question for you. And with that, I'd like to introduce our first speaker in this session, Ernesto Palumbo. Ernesto, are you online?
Yes, I'm here. Can you hear me well?
Yes, I can hear you. And so if you'd like to start sharing your screen.
Yeah. Can you see my screen?
Yes, I can see you're not in presentation mode yet, but I can see your screen. Perfect. And so with that, yes, perfect. And so with that, I'd like to welcome Ernesto to speak on the spectral properties of bright and dark areas on Ryugu surface.
Okay, thank you. Good morning to everybody. Okay. Hayabusa 2, maybe I recall something about Hayabusa 2. It's a small Japanese mission, and you can see here that there are only 4 instruments: the camera, navigation camera, thermal infrared camera, near infrared spectrometer, and the lateral altimeter. The target is a Ryugu. This is near Earth asteroids, very small, it's less than 1 kilometer. In comparison, you know that there is another NASA mission to the asteroid Bennu, which is similar to Ryugu. It's a little bit smaller, with a lot of instruments more. The payload is richer than Hayabusa 2, but you can see here the mass of the 2 missions are very different. We have at least a factor of 10 of volume of the spacecraft. In this presentation, I will show you the analysis of the NIRS-3 spectrometer, which is a small spectrometer with a wavelength range in the range between 1.8 and 3.2. This means that we are able to detect and study the OH present in the minerals. The resolution in 20 nanometers, and we have a spatial resolution which is 35 to 2 meters, and when we are very close to the surface of the asteroid. These are all the observations we obtained from June to 18 to February 19. There are about 160,000 spectra. They are mainly located in the equatorial region, you see here. But there are even fewer observations in the other higher latitudes. Here a summary. Ryugu is a very dark object with a very low reflectance. It is very homogeneous. You see here how it is similar, the reflectance variation among the different locations on Ryugu. We defined the bright areas, and these are our definition for the bright areas and dark areas. And for the dark areas, we are obliged to put inferior limits to avoid noisy observations. The data presented here are the data we analyzed here, the ones we collected on July 2018, when we were far away from the surface, around between 20 and 13 kilometers. Let me go on the next slide. Here I show you an example of what you are when you try to detect a bright area. And these are 6 observations. This is the bright area we call B6. You have 6 different observations, 6 different times. And in each observation, you have a different spectra that are located inside this area. And in all these 6 occasions, you obtain the reflectance that are in the definitions I showed in the previous slide. So we are in this condition here for the dark. For the bright, this was a bright area. So the reflectance was larger than 5% with respect to the more than the average. This is the average value. So totally, we obtained 36 bright and 28 dark areas in the on the Ryugu surface, and you see here many of the features are associated to geological features, in particular to boulders. In fact, the Ryugu asteroid is very rich in boulders. Here you see the location of the bright areas, and you see there are some examples with the large boulders, and there are even crater rims which are brighter than the surrounding areas. And you can observe that there is a strong longitudinal dichotomy on Ryugu. There is this region between 0 and 120 degrees, which is poor, and the richer region is between 240 and 360. Regarding the dark areas, you can observe that we have the dark areas are located on lows, so this means on crater floor and depressions, and large boulders that are darker than the surrounding area. And even in this case, you can observe that we have differentiation. In this case, we have a strong latitudinal differentiation. The equatorial region are very poor in dark areas, whereas the polar region is richer. If we take all these areas and we apply spectral analysis, we have to define the most important parameters. In this case, our important parameters are reflectance value at 1.9 micron, which is here. The band depth of the 2.72 micron, which is a very clear band in the Ryugu spectrum. And you see the 2.8, which in the first analysis, we thought that could be a real feature, even if it is very, very weak. You see here. And then for the final is the reddening parameter, which is defined as the reflectance difference between 1.9 and 2.5. Then here is how we took the band depth. Let me show you the first analysis we made by comparing the band depths of the two OH bands, the 2.7 and the 2.8. Here you can see that these two bands are show a very moderate correlation, but it's a very good correlation.
8 minutes.
Yeah. Can you hear me well or not? Does it sound some problems?
No, keep going. I just wanted to give you the 8-minute warning.
Okay. And this is you see how the two different the dark areas and the bright spots behaves in this scatter plot. And the red one is the Ryugu. If we take another behavior, which is the behavior to versus the reflectance, so we don't see any kind of correlation. Here we show how these areas, dark and bright areas, behaves in comparison with carbonaceous chondrite, which is Ivuna carbonaceous chondrite, which was processed at different temperatures. This is 400, 500, 600. And you see that the 400 is very close to our clusters. If you take this other scatter plot, which is reddening on the y-axis and the x-axis, you see the band depths of the OH, the 2.7, 2.8. You see here again that the Ivuna 500, in this case, very close to the cluster. And for the 2.8 OH band, you see that there is a a moderate anticorrelation with the slope. And this is an important point. And you see again that this very close to the class is the IVUNA processed to 400 degrees. You see here how the two spectra are compared. They compare, you see the IVUNA 400 degrees and the mean Ryugu that are scaled, but you see that how they are very, very similar. Our results, main result is that we found dark and bright areas on Ryugu, although Ryugu is a very homogeneous, but we were able to detect bright and dark areas, and that they show latitudinal and longitudinal dichotomy. These dark and bright areas are related to geological features. The bright area to quadrilateral bulge and crater rings and boulders, and the dark with the lows and saxon. The carrier of the OH bands could be more than one single field silicates. We were able to detect a 2.7, which is a very clear band, but even a 2.8, which is, seems to be real. So this means that maybe we observe magnesium and aluminum rich and iron rich field silicates. Dark areas are more red sloped, so they are redder and show weaker hydroxylation bands. And an example is a Jima Saxon in this case. And this means that maybe dark areas are more space weathered. The material composing both the dark and bright and the typical Ryugu material seems to be compatible with the thermal processing if we compare with the IVUNA carbonaceous chondrite method. We were processed at 400 and 500. Thank you very much.
Great, thank you so much, Ernesto. Are there any questions for Ernesto? We have a little bit of time for a question. I have a question, Ernesto. Yeah. In the high albedo areas that we see on Bennu, there's evidence for exogenic materials that perhaps originated from a Vesta-like body. Do we see any evidence for that, the high albedo regions on Ryugu?
Yes. I know the situation on Bennu, but it is very different from in our case because if you see here the spectra, we are not able to evidence a 2 micron band. You see here the mean Ryugu, it seems that we see a 2 micron. We were trying to understand if this feature could be real, but we didn't find any correlation with a geological feature. So since in this area and this spectral interval we have a filter, we think that this is due to a filter. This weak inflection is not real. So we're not able to see a correlation with the exogenous material coming from, for example, Vesta or other bodies. The only feature we observe are OH, which seems to be related to the primitive material which we expect Ryugu is made.
Great, perfect. Thank you so much. So unfortunately, we're not going to be able to do the 2 additional minutes for Q&A during our session, since we are off track from the other parallel session. So from this point forward, we're going to be giving the typical 12-minute slots, 10 minutes for talk, 2 minutes for Q&A. And so with that, we'll move on to our second speaker, who is Marco Delbo. Marco, are you online?
Yes, I am. Hello.
Great, great. And so Marco is going to be presenting on observing the planetesimal size distribution amongst main belt asteroids today.
Okay, I'm trying to share the screen, hoping that it's going to work. Right, I hope you can see it.
We can, thank you so much.
Okay, thank you. So first of all, thank you. This is a project that we have been working on for some years. and it's funded by the National Agency of Research in France. And some of us are also members of external international co-Is of the survey class project, is led by Dan Britt of the UCF. So I'm going to talk about one of the most fundamental problems, I would say, of planetary formation and the lives of asteroids. And that goes back to the questions: what are the typical sizes of the planetesimals, what their composition, and if they can still find them in our solar system. And the planetesimals are, let's say, the theoretical objects, the first stage of formation of planets. And there's a big debate in the community about their sizes in particular. And while this problem is typically addressed, let's say, theoretically, our idea was to try to locate them as many as possible in the main belt. To see how this works, I would like to introduce the asteroid formation paradigm, which is basically telling us that the asteroid in the main belt that we see today, some of them formed directly from accretion of dust in the protoplanetary nebula. And they are accreted in different regions and in different sizes, probably, with different compositions, and which I painted here in this cartoon with different types of asteroids and colors. You can see a high albedo asteroid and a low albedo asteroid. So those that accreted directly from the dust are planetesimals, right? So, but throughout their lives, asteroids can experience impacts, and some of them are catastrophic impacts. And so the first asteroid on the top might break and create a family of fragments. These family of fragments are themselves new asteroids created from the disruption of this original planetesimal that does not any longer exist in the main belt, but just its let's say its daughter asteroid. And however, some asteroids might not experience this catastrophic, some planetesimal might never experience this catastrophic breakup, and so they're still there in today's main belt, preserved as they were originally formed in the protoplanetary disk. Let me just draw your attention that there are families of fragments that have different albedos, different composition, which are painted here, one white and one black. And I also want to address the problem and just to show the problem that the collisional families of asteroids, that their members diffuse with time in orbital elements. And so the families start, as they age, they start to overlap among themselves and also over the original asteroid. So the picture is very confused, as you can see in this third diagram. So it would be amazing if we could find the survivors, because if you can locate the original planetesimals, the asteroids that are planetesimals, getting rid of all the asteroids that are family members that were created after by the collision, we could actually get an idea of the original size distribution of these planetesimals, which is a tremendous important constraint for planetary formation model. You can read these papers by Morby, Sean Raymond, and Anders Johansen, and so on. There are many with this topic. So let's look at the belt. Here we see a distribution of the asteroid in the belt in proper semi-major axis as function of the inclination, proper inclination. The asteroids, each point is an asteroid, and they are colored with a palette according to their albedos. These are essentially data from WISE, Nakari, and IRAS. You can see by eye that there are clusters, and these clusters, they are also clustered in albedo. These are the asteroid families. And there are techniques to identify the families. So one could think that we could try to identify all the families. Here we see only the inner part of the main belt. So between the Nu-6 secular resonance and the 3-to-1 mean motion resonance with Jupiter. And we see different orbital plots. Okay, so we can use the hierarchical clustering method to basically grab these clusters that I highlight like this, and then let's try to play this game. So let's remove them. And ideally, we would love to see this. So a bunch of planetesimals that are there and they were never catastrophically broken up. And so once we remove the collisional products, we should see the original asteroid. But unfortunately, it's not what we see. We see something else that is more like this. So we see a crazy background that has a lot of structures. These are halos of families that have first identified by Alex Parker and co-author in 2009. But what are them? Are these very small planetesimals? Or there are, since they have structure in orbital element space, they could still be undetected, very ancient families. So we try to identify collisional members with a different technique. We use the V-shape of the Yarkovsky effect. If we actually take the members of a collisional family and we plot their semi-major axis, we plot their inverse diameter, so 1 over the diameter, as function of the semi-major axis from the center of the family, for instance, we see this kind of V shape. They look like a V, which with the vertex of the V pointing to the center of the family. Here we see in the y-axis, big asteroids are to the bottom, near the 0, because it's 1 over d, and to the top, it's around 0.9, 1 over d is almost the size of a kilometer. 0.5 is 2 kilometers, 0.1 is 10 kilometers, and so on. The main important thing is that the Yarkovsky is this non-gravitational force that pushes asteroids in two directions, depending on their rotation state, and also depending on their sizes. And so large asteroids, they don't move, whereas small asteroids, they move much more. And so if we let time goes by, we see that the V shape expands like this. We can also measure the age of the family by simply fitting the border to the V shape. So our idea is to basically locate asteroid V shapes in the main belt. And you can see here another cartoon showing a bright V shape, high albedo V shape against a dark V shape. And the asteroids that are not inside the V shape, they could be the original planetesimals, because all the members of V's are collisional products, whereas those that cannot be put in V's are the planetesimals. And so we can, thank you. We can reconstruct this game and go back to the original asteroid, of course. So I think I will skip a little bit how we do this identification of V-shape. You can actually find the paper by Bryce Bolin and by myself in 2016 and 2017, and I come directly to the point. So we have identified a series of V-shape that were not seen before, and here's one. So you can see here, if you can see, I can draw the lines just to guide your eyes. There are 3 V shapes here. One, the blue and the red, they were known before. They were identified by Walsh et al. And Kevin Walsh, myself et al. In 2013. But in 2017, we identified this very wide V shape that basically spans over the entire inner portion of the main belt. This is only low albedo asteroids. So we think that these are all collisional families. And the wider one could be as old as the solar system. But the most interesting thing, one of the other interesting things are these asteroids that just made them square that are outside the V shape, and there's no way to put them inside V shapes. These are planetesimals. So we went on and we identified more V shapes. Here's another paper that we published in 2019, where we identified 2 more V shapes in the inner main belt with intermediate albedo, and they are also bounded by other asteroids that cannot be put in V shapes, and these are for us the planetesimals. So we can start to reconstruct the planetesimal size frequency distribution of the original planetesimals in the inner main belt, and it looks very, very shallow. It's very, very shallow, not like -2, but is shallower than -1. If we, I'm almost to the end, if we fit a function to this distribution, we see that the PDF, the probability distribution function, correspond to a Gaussian centered around 80 kilometers with a wide distribution around 50 kilometers. So basically, these are the conclusion. I just leave it there, and I conclude saying that if this work shows that the planetesimals were essentially born big, with a diameter around 80 kilometers, and the smaller asteroids essentially are all collisional products. And I take questions if there are.
Great, thank you so much, Marco. Are there any questions from the audience? Don't see any raised hands. Quickly, Marco, could you describe any follow-up observations that would be helpful in pushing this work forward?
Yes, we are doing that, and it's a very interesting question. So there are a number of things. One thing is interesting. With our list of planetesimals is public in the paper, and we can give to anybody who's interested. And it's interesting because they can basically, for us, these are the objects that form accreted directly in the protoplanetary disk. So it's interesting to see what their spectroscopic class is, what is their composition, and so on. Another interesting thing to do is to, let's say, constrain the composition of the families. So I know that some of the guys from your university are following up our families to prove or disprove their compositional homogeneity. And I think these are very beautiful things to do.
Great, thanks so much, Marco. I'm going to now turn over the chairing duties to my co-chair, Jenny Larson.
Hi, so we're going to continue going on with our next speaker, who is Nicholas Schmer, and they're going to be talking about the geophysical exploration of the dynamics and evolution of the solar system. So you can go ahead and share your screen.
Yeah, can you hear me all right?
Yes.
All right, let me get the sharing going here. All right, can you see that?
Yes.
All right, great. So thank you for joining everybody today virtually all across the world. I want to talk a little bit today about this new survey project that we've started this year, thinking about how to go about using geophysics to look for the kinds of structures that tell us about the evolution and dynamics of the objects throughout the solar system. I'm going to focus a little bit here on the moon, but this is also highly relevant to studies of asteroids and other planets in the solar system as well. And so our project is really focused on how to take that human and robotic component and look at the subsurface with the tools of geophysics. So we're thinking about how to go about doing exploration and science in these different regions, with the emphasis in our particular study of looking for natural resources that will enable future in situ resource utilization. So we're focused on a couple of ISRU targets. There's a lot of different ones that are out there. I know everybody has the ones that are near and dear to their hearts, but one of these is tubes and void spaces. Another is looking for where there might be ice deposits in the subsurface, or looking at the regolith itself and the structure beneath the surface. This is of interest, of course, to people who want to study the evolution of planets, because the regolith is this history of it. And then also the sort of magma tectonic evolution of these bodies as well, because volcanoes and faults are fairly commonplace features that we can find at the surface of nearly every body in the solar system that has a solid surface. This is a project that's really building off of a lot of different expertise, and our team consists of at least 7 different universities, 5 different research institutes, and then 4 different NASA centers. And we also have a geophysics consulting company working with us on this. We're still team building right now, where we've brought on several students that are going to start this fall in the various institutions, but as we grow, we're probably expecting to add more people. So one of the days in the near future, maybe this will be one of you who join this list of folks. Our project is really building off of the heritage that was given to us by Apollo over 50 years ago now, where the Apollo missions brought a whole bunch of different, almost the kitchen sink version of geophysics to the surface of the moon, where investigations range from looking at potential fields like gravity and magnetometry to more active source experiments and passive listening to the moon's ground motion. So we could listen to moonquakes and discover that the moon was seismically active. And then we also have all kinds of other techniques that let us look at the subsurface. So the astronauts were really sort of integral to putting these kinds of experiments out, and they give us this sort of wealth of information about what's going on within the lunar subsurface. Following on Apollo, we've had a lot of orbital missions that have given us more information about sort of the large scale structure of the moon. Here I show a couple of results from either the magnetometry, looking at the magnetic signatures across the surface of the moon, and then also mapping out the gravity field and looking at the topography and shape of the moon. And these have been revolutionary for our understanding of essentially how this object formed and evolved through time. And so as we start to collect more geophysics, the question is, what can we do to sort of answer some of the more detailed questions that are out there that remain about the history and the evolution of that moon and the dynamics that have driven a lot of the signatures that we see here. And so the next generation of geophysics at the moon is nigh. I think with the Artemis program, we're looking forward to having new kinds of instruments and revisiting some of the types of tools that the Apollo astronauts took to the surface, and then applying those techniques in new areas, including like the permanently shadowed craters of the South Polar area, looking for volatiles. The commercial lander payload service will give us an opportunity to put new kinds of geophysical observatories on the surface of the moon in places where we weren't able to investigate during Apollo. And we also have all kinds of robotic missions that are going to be doing subsurface sounding that are going to be of relevance for trying to better understand the evolution of the moon. So I think that there's a lot of really interesting missions coming on. The New Frontiers 5 call for a lunar geophysical network will give us a chance to basically monitor subsurface of the moon, listen for new moonquakes, listen to those impacts that sort of tell us about what's going on inside of the moon today. So what is GEODES going to do? Well, we're focused on basically preparing for this next generation of lunar geophysical exploration. And one of the strengths of geophysics is you can combine different techniques and put them together. And we're trying to find ways and working on ways to basically take these techniques and put them into these Bayesian type of inversions that can rapidly inform us about what's going on in the subsurface. So for example, like here's an analog study where we're taking radar studies of a lava flow and also seismic sounding of that same lava flow and putting together to try and understand the amount of fracturing and porosity that might be in the subsurface. We're also interested in how to sort of understand the fundamental basic processes that drive some of the geophysical observations we see. So we're doing some modeling where we basically try to understand how fractures form in a lava flow, or how a tube might express those fractures in its wall, or how volatiles would be stored in the subsurface through thermal modeling. We're also interested in how to go about doing sort of the best kind of equipment deployments we can on the moon, and this includes deployment practices and how you actually go about collecting the geophysical data in a robust way, and then also making sure that the equipment that goes to future missions is moon ready and can actually be deployed in the environments properly and collect the data that we want to get in those studies. So we're using Earth-based geophysical analogs to study those kinds of topics and basically validate the kinds of structures that we might want to use. So you can think about geophysical analogs in terms of the geometry of the outcrop that you're trying to study, or how you're actually going to go about doing that data collection, how you're going to actually interpret those data while you're on the moon or trying to do your study, and sort of thinking about the geometry and then the logistics behind doing that exploration. There's also like a very great opportunity here for people who want to try out and test out equipment that we can take them out into the field with us and essentially get things to a technology readiness level that it's putting them ready to fly to the moon and actually do those kinds of studies. So I'm going to walk through a couple of examples of the things that our group has been working on. This is in collaboration with the Goddard Instrument Field Studies program, where they're studying how to essentially do these types of measurements, and then also several P-STAR grants that have been used to study analogs here on Earth. So the first of these is focusing on how do we map out the the distribution of volatiles in the regolith, and also thinking about the structure of the regolith itself. And here we're, as a study by one of the Goddard Instrument field team studies, thinking about how to map out subsurface ice using GPR. And this is looking at basically ice that was buried underneath the eruptions of this Asco volcano that essentially put the ice underneath a layer of ash. So by using GPR, they can basically scan along the top of the lava flow or the ash flow and see these layers of buried subsurface ice with the GPR. So this is something of an analog you could think of, maybe like an ice deposit at one of the polar regions that's been buried over by impact ejecta, even though maybe the massive ice that we see here might not be present on the moon, but it gives you an idea about how you could actually go sound for this. We're also thinking about how we can use the different outpourings of like lava or fractures and faults, and thinking about how those might be a resource for future. So you want to image through a lava flow and better understand essentially the structure and the subsurface. Thinking about where there might be faults at depth. This could be a potential hazard. There's a talk later today that I'll highlight by Lisa Schliegler. It's going to be talking about how to evaluate the hazards from seismic events on the moon. People might want to check that out. But this is the kind of thing.
8 minutes.
Thank you. So what we're doing is basically taking profiles similar to what was collected during Apollo, where we take a seismic line, stretch it out across some geological structures that are of lava flows. Here, this is in the San Francisco volcanic field in northern Arizona, and then trying to recover basically that structure through fast inversions, and basically use this as then maybe a tool that we could use for sampling or figuring out where you might want to go install a habitat or a base, knowing where those hazards might be. We're also interested in the surface and being able to detect those. These are places that could potentially serve as a habit or a place for shelter for astronauts, or as a unique place for doing some geological studies, because they preserve pristine habitats for maybe on Mars, where you have an environment that would be unique, or on the moon you might have samples that haven't been altered by space weathering. And so we can detect these with geophysical tools. Here we've been studying Skull Cave and the Lava Beds National Monument up in Northern California. This is with Kelsey Young's P-Star TubeX project, where they've been working across this tube system and mapping out with magnetometers essentially the location of the subsurface void spaces. And this is work by my graduate student Ernie Bell, who's been using the magnetometer to try and understand if we can make a relationship between the size of the magnetic anomaly that we see and the size of the tube beneath, and we can use that to then calibrate for looking for tubes, say for example on the moon or other planets in the future. And so if you're interested in learning more about this project, we're just kind of getting off the ground. COVID-19 has put a little bit of a damper on our field activities, but we're still able to work with a lot of the data sets that we have from pre-existing studies and working forward with some of these kinds of investigations. So you can go visit our website at geodes.umd.edu. We have a couple of presentations here that if you're interested in, you can go check out. Lisa's talk is later today, which is talking about constructing this probability seismic hazard analysis framework for the moon, which I think is going to be of interest for safety of astronauts in the future. Kelsey will be talking a little bit about how to use instruments in the field. And then Molly, our public outreach officer, is going to be talking a little bit how to use NASA expeditions to advertise some of the field work that you're going to be doing. And then Norbert, who's one of our ice volatiles team, is going to be talking about ice on Ceres. So there's a whole variety of different talks you can go check out. And then the poster sessions have, and you can go check these out at your leisure, of some of the work that's being done by our students and postdocs. So thank you for everybody for your attention. Take questions.
All right, we have like 1 minute for a quick question, if anyone has one. I do have a quick question, actually. So what is probably like the biggest step that you have to overcome when testing in the field, your equipment?
I think one of the biggest challenges, of course, is getting to the field. But in terms of testing the equipment, it's really making sure that it's something that would be applicable for a planetary type of study. I mean, we could do geophysics with a lot of freedom here on Earth because we have an atmosphere and it's you can get around pretty easily. But I think for astronauts, we have to really be thinking about like what kind of tools would be appropriate and how can we make that equipment and technology more readily accessible and easy to use. Sort of the ease of use is probably one of the big questions, I think, for how to make this flight ready stuff for astronauts to work with.
Great. Well, thank you very much. All right, we're going to move on to our next speaker. We are going to be having Henry Sia, who is going to be talking about the Themis asteroid family, a potential source of ice-rich near-Earth asteroids. So if Henry, you are here and would like to share your screen.
Yep. Let's see. How does that look?
That looks good.
Okay. And everyone, you can hear me okay? Is that a yes?
Yeah, sorry.
Yes.
Go
Okay,
ahead.
that's okay. All right, thank you. Okay, so yeah, so thanks. So yeah, my name is Henry Shea, and I'm happy to be able to talk to you all today. So thanks to the organizers for the opportunity. So today I'm going to be talking about the Themis asteroid family, a potential source of ice-rich near-Earth asteroids, and this is work I've done with my collaborators, Norbert Schophofer, Kevin Walsh, and Boyan Novakovic. So, so I know I'm the last speaker in the session, and we've had a long morning or afternoon. So I thought, just to make sure I get my message out, I thought I'd actually start with my conclusions. And this will also help guide everyone else to kind of see where I'm going as I give this talk. So basically in this work, we did dynamical integrations that indicate that dynamical pathways exist from the Themis asteroid family, which is in the main asteroid belt, to near-Earth Jupiter family comet-like orbits. So these are have parameters of less than 3 and perihelion distances of less than 1.3 AU. We then did thermal modeling of these objects as they evolved from the main belt to near-Earth space. And then we found that if they had ice to begin with, that this ice could actually be preserved fairly near the surface, like within 5 meters or so, in the polar regions if the object tilts are not too large. And so based on those results, we suggest or conclude that if some Themis family asteroids are icy, as appears to be the case, some currently observed active comets could actually originate from the main asteroid belt. So that's, we find really interesting from the scientific perspective. And then also that other inactive near-Earth asteroids with accessible ice could be identified by their dynamical and rotational properties. So that's so for the exploration oriented people here. And this is funded by NASA Solar System Workings and the survey programs. So, so Marco actually did a great job of introducing families, which is great, which means I don't have to talk about them. But I will focus on the Themis asteroid family itself. So it is one of the largest and oldest asteroid families in the asteroid belt. It's thought to have formed about 2.5 billion years ago, and about 5,000 members are currently known. And its largest member, which gives the family its name, is the asteroid 24 Themis. In terms of composition, the family is dominated by objects with primitive type spectra, so C-type or B-type. And this is consistent with its location in the outer main asteroid belt at about 3.1 to 3.2 AU, as you can see from the semi-major axis versus eccentricity plot there. Very interestingly, there seems to be evidence that there's ice, present-day ice in the Themis family. First, there are these objects known as main belt comets, which are objects that orbit in the main asteroid belt, but they have exhibited comet-like behavior sometime in the past and at the present time as well. And basically, this cometary activity implies that they have present-day surface or near surface ice. And actually, multiple MBCs are actually known to exist in the Themis family. Meanwhile, there's actually also independent spectroscopic evidence of ice in the Themis family in particular. People have looked at large Themis family asteroids because these are easier to observe, and they've actually found absorption features that correspond to water ice frost on a couple of these asteroids. And so you see the spectrum of 24 Themis itself there. And so what we want to know is what happens to icy Themis family asteroids that escape the family, if they indeed escape. So that brings us to the first component of our work, dynamical analysis. So basically, we're trying to see what happens to Themis family asteroids over time. So what we did is we created test particles representing all of the known Themis family asteroids, and then we integrated them forward in time for 100 million years using the Mercury 6 hybrid integrator. And then we took the output, which was, we had several time steps, and classified the intermediate orbital elements as these objects evolved into different dynamical categories. So here are the results. You don't really have to look into the table too much, but basically the punchline is that the vast majority of our test particles remained stable. They remained in the Themis family, or at least in the main belt, for the entire duration of our integrations. But about 1% did escape from the main asteroid belt. So this is an example, or these are some plots of one of the objects that did escape. So on the left there, we have semi-major axis versus eccentricity and semi-major axis versus inclination plots. And so you can see the sort of the big black dot is where this particular object started within the Themis family, which is the kind of massive small gray dots. And what happens is that it's sort of on the outer edge of the family, which is close to the 2-to-1 mean motion resonance with Jupiter, which tends to destabilize small bodies. And so the object basically encounters the resonance, and then once it does, it has its eccentricity and inclination pumped up, basically. And when the eccentricity reaches a certain point, as you can see in that top left plot, it can actually cross this perihelion of 1.3 AU line, which actually makes it a near-Earth asteroid. On the right, you see sort of orbital elements versus time, and you can see that the transition to, so the blue dots basically show when it's in the Themis family or the main asteroid belt, and the red dots are when it becomes, basically it has a dynamical characteristics of a Jupiter family comet. And you can see that transition to the cometary orbit is accompanied by many close planetary encounters with Jupiter and Mars, basically, and that's that bottom panel down there with the colored dots. So, so what we conclude from this is that for objects that undergo this evolution, it's driven by eccentricity excitation by Jupiter, which then causes the object's orbits to start crossing orbits of other planets. And during close planetary encounters, the Ciceran parameter gets lowered to cometary values. And what's interesting is that this does not appear to be uncommon. Like I said, it's about at the 1% level, which is actually, pretty substantial. These objects appear to have very similar properties to other comets, except that their semi-major axes are clustered near the original position of the Themis family, so 3 to 3.5 AU. We think that the implied contribution to the comet population is fairly modest, on the order of a few, but we did make some assumptions, which means that this could actually be, we made some assumptions in the modeling, which means that this could actually be quite a bit higher. So, so that deals with the dynamics, but we want to know what happens to the ice itself. So, so then we did thermal modeling using the dynamical. Sorry.
You're 8 minutes, by the way.
Okay, thanks. So then we did thermal modeling using the dynamical trajectories of these objects as they traveled from the main belt to near Earth space. This thermal model uses sort of a combination of two models. It uses asynchronous coupling between a 1D thermal modeling that uses small time steps to capture subsurface conduction, and ice evolution model that kind of captures a larger scale evolution that takes into account the changing orbital properties as objects evolve dynamically. And then we recorded the temperatures and depths of ice over the course of each object's history, and tracked them as a function of time, latitude, and axis tilt and thermal inertia. So this is the results from the same object I just showed you earlier. Basically these are the plots to focus on are the second and third ones, where the blue plot is the temperature at the poles of an object with an axis tilt of 25 degrees from vertical. And the red plot shows a more extreme axis tilt of 80 degrees. And basically what we see is the temperature at the poles remains quite a bit colder than the object with the higher axis tilt. And if you look at the bottom panel, which shows the depth to ice, you can see that after some initial ice loss, the depth to ice for the object with modest axis tilt actually remains fairly constant over very long time scales. Especially compared to. Okay, thanks. Especially compared to the one with a larger axis tilt. So we also just took a histogram of all the objects that we integrated and found that all objects, if we assume, with all these different trajectories, we assume it has a modest axis tilt, they have depths to ice of 5 meters or less, which is really exciting and interesting. So what we found in terms of our key, the key takeaways are that ice loss is actually dominated by the time spent in the asteroid belt, because the time scales are so much longer than the time spent as an NEA. And like I just said, objects with axis tilts of 25 degrees can actually retain water ice near the poles within a 1 thermal skin depth beneath their surface. And this is, we think, pretty exciting, because it means we could potentially identify near-Earth objects with shallow polar ice by identifying objects with semi-major axes in the outer main belt and have small axis tilts. But this is pending studies studying how axis tilt might evolve over time, which we didn't consider. And with that, I'll just put up my conclusions, which I already explained to you. And you can see the 2 papers there if you want to get more information on our project. So with that, I'll end. Thank you for your time, and I'll take any questions. Thanks.
All right, thank you, Henry. It looks like we are almost out of time, but if you have a quick question, like a really quick question that you want to ask, we are heading into the discussion time, and this would be a good time to continue with this discussion and ask any further questions.
This is Marco Delbo. I have a question for Henry, if I can.
Yes, go ahead.
Sorry, I can raise my hand because I have a old Zoom version. My question is, what are the thermal property of the regolith? So you assume a fine regolith on the surface for thermal modeling? I haven't read the paper, admittedly, in Icarus. I apologize for that.
Oh, no, that's fine. We actually tried a variety. We basically tried all, like a low thermal inertia, a moderate thermal inertia, and a high thermal inertia. And they all find actually very similar results.
Thank you.
So,
it's very interesting.
Yeah, thanks.
All right, thanks. So it looks like we have one more question for Henry in the chat. So I am going to hand this over to our discussion period right now due to time. So
can I really quickly interrupt for just a moment? I just want to make an announcement on timing. We are updating the program online, but I just wanted to please continue your discussion, but we're going to start the next block of time at 11:10. That'll be the student lightning round talks. And then the third block of time will start at 12:45. So in theory, we'll end about 10 minutes late today. So if everyone could make note of that and go to the online program for times, that'd be great. Thank you, and please continue.
Yeah, so I want to encourage all of the speakers to remain in the Zoom room for like the next 10 to 20 minutes, just in case there are other questions that anyone has. And definitely I encourage all of the audience members to feel free to stick around and use the chat window for questions and follow-ups and such. Thanks.
Ginny, I think you were going to ask the question from the chat window to Henry.
Yes. For Henry, what variation in your model assumptions that could increase Trojan family small bodies into the NEO population?
So we actually didn't look at the Trojans at all. So because we were focused on the Themis family, so the assumption would just be that we would, add the Trojans into these integrations. We're actually running a larger set of integrations of the whole main belt right now because there's some interest in seeing where else asteroids might come that might infiltrate the comet population. So again, this doesn't include Trojans, but we could certainly do another set of integrations that include Trojans. But right now, it's just something we didn't look at. Oh, yeah.
Thanks. Are there?
Oh, sorry.
Go ahead.
Sorry. I see another message. I guess this is Diane. It might have been a typo. So the assumptions for increasing the Themis family small bodies is using non-gravitational forces and also changes in the size distribution that could increase the number of objects reaching cometary orbits.
Henry, it also looks like you have another question from Chris Bennett. He is asking either you or maybe if Norbert's online, if you could talk a little bit about the ice stability modeling that seems to indicate the ice is only stable at depth. And he was wanting to know, have you done this modeling on Themis 24? And does the modeling predict the ice would be at depth there? Or does this agree with the fact that water ice was observed at the surface?
So I think Norbert is online. So if he is, I'd like to pass it to him, but I can try to answer it. If he's
online.
Okay, great.
Yeah, so for Themis and the whole outer belt, there is no long-term stability on the surface, right? Only in a subsurface. And but one can have impacts and recent impacts which can create surface ice. But a long-term surface ice is not stable in the entire asteroid belt, only in the subsurface, in parts of the asteroid belt.
I had a general comment. This is Marco. I love this coupling of thermal modeling with orbital evolution. It's great. As a matter of fact, we did some exercise with Patrick Michel in 2010, and this was, I think, this was a mostly comment for Ernesto, because we looked at the orbital evolution of Ryugu, and it's very plausible that it was heated to 500, 600. I forgot now whether it's, I apologize, I have to look in the paper, whether it's Kelvin or Celsius, but it's quite high temperature. I know there's a big difference between the two, but I have to look at the paper now. But I strongly, it was heated importantly.
Cool.
Is there any other further discussion or questions for our speakers? I haven't seen anything come across the chat window, and I don't see any raised hands. So if not, maybe perhaps we can, thank all the speakers and take a short break before the lightning round talks start. But definitely, if there are further questions for the speakers, feel free to chat with them via the chat window or via email. Thanks for a great session, everyone.
And thanks to our co-chairs and speakers as well. And we'll see you in about 12 minutes. Thanks.
All right, are you able to hear me?
Yes, we are.
Okay. Are we ready to begin?
Go for it.
Okay. All right, folks, welcome back to the plenary for late this morning or this afternoon, wherever you are. As we saw yesterday, there is some really outstanding work being done by students. This is something that we can all be very heartened by and really leads us to have great hope for the future of our community. We're going to see more examples of that today in these student lightning talks. So I'm going to pull up each slide. I would like the student to then share their screen, or rather to not share their screen, excuse me, to activate your video and your microphone and give your presentation. So we're going to start out with Neil Bassett from the University of Colorado Boulder. Neil.
Thanks. Hi, everyone. My name is Neil Bassett, and I am one of the members of the team working on the DAPPER mission, which you heard about earlier today from Jack Burns, and Administrator Bridenstine also gave us a shout out yesterday. So the main goal of DAPPER is to measure the low-frequency observational signatures from hydrogen in the early universe, so from the dark ages and cosmic dawn when the first stars and galaxies began to form. So I work on the data analysis side of the project. So we've created an analysis pipeline that's based on pattern recognition to analyze these low frequency observations. And so my poster is about a method that I've been working on for ensuring that the results that we get from this pipeline are robust and how we can know that we have sufficiently modeled each component of the data for these low frequency experiments. So again, my name is Neil Bassett, and if you're interested in this really exciting field of cosmology and astrophysics from the far side of the moon, please come and visit my poster. Thanks.
Thank you. Next, we have Aisha Khatib from the University of Maryland. Aisha.
Hi, can you hear me?
Yes, we can.
Okay, great. Hi, everyone. My name is Aisha Khatib. I'm a first-year PhD student at the University of Maryland. I study geophysics and planetary seismology. The project I'm presenting in my poster involves the passive seismic experiment package on the Apollo 11 mission, and discusses how we can use anthropogenic or human-caused events as seismic sources to characterize the lunar subsurface. Apollo 11 seismic experiment is pretty unique in that there's only a passive component, there's no active component. And also because
on this paper.
And also because the astronauts set up the seismometers partway through their extravehicular activity, or EVA. This means that a lot of the astronauts' unrelated activities after they set it up, for example, collecting core tube samples, loading equipment, or jettisoning equipment after the EVA, would register on the short period seismometer. And instead of looking at these spikes in the seismic signal as noise, I use it to try and build a seismic velocity profile of the subsurface of the landing site. This presents pretty interesting challenges, such as how to determine what events are, where they originated on the lunar surface, and how exactly to calculate time differences between their origin times and their seismic event times. It's an interesting experiment to see whether it's possible given the constraints of the equipment and data collection on Apollo 11. I hope all of you stop by. Thank you all for listening, and I hope you have an excellent rest of conference. Thank you.
Excellent, thank you. Next, we have Vanessa Lowry from the University of Central Florida.
Everyone hear me? Excuse me. Hi, my name is Vanessa Lowry. I'm a PhD candidate at the University of Central Florida. I'm currently working with Dr. Carrie Donaldson-Hanna on linear spectral unmixing in the thermal infrared. I've written an algorithm for the weighted least squares algorithm, which is basically a chi-square minimization, and also implemented a sum to one constraint on that, where the abundances all sum up to 100%. I applied this to the OSIRIS-REx blind study data, which are primitive asteroid analogs, mixtures, and real meteorites. And we unmixed with a full spectral library of fine particulates in a full and limited spectral data range. Basically, we're trying to show how effective a linear model would be on fine particulates that exhibit nonlinear behavior. So please come visit my poster tomorrow, and I look forward to meeting you. Thank you.
Thank you. Next, we have Nivedita Mahesh from Arizona State University.
Hi, my name is Nivedita Mahesh. Can you hear me okay?
Yes, you're coming through fine. Thank you, Nivedita.
Hi, my name is Nivedita Mahesh, and I'm a fourth-year grad student at Arizona State University, working with Professor Judd Bowman. My primary research focuses on analyzing various aspects of the Far Side Array, a radio telescope designed for the radio quiet zone of the moon. In this work here, I present some tangible results from the notional array layout, which includes investigation of various layouts that could mitigate artifacts in the image, to designing a strategy that could enable dual polarization measurements with the array. This strategy involves directly embedding the two polarization receivers in the tether as the rover traverses its path. This would result in the two orthogonal antennas being offset from each other. Thus, I've carried out a feasibility study of non-co-located antennas in an array. The importance of this work lies in the fact that dual polarization measurements would help the science cases of the far side by decreasing the integration time and differentiating the host star signal in case of exoplanet studies. I hope I've sparked enough curiosity to encourage you to stop by poster number 56 tomorrow. Thank you.
Very good. Thank you, Nivedita. Next, we have Ryota Nakano from Auburn University.
Can you hear me?
Yes.
All right. My name is Ryota Nakano. I'm a first-year PhD student working with Dr. Hirabayashi at Auburn University. Tomorrow morning, I'll be presenting our work on asteroid Phaethon. Most of you may know what the Gemini meteor stream is, which is the meteor stream that you can observe in December. And Phaethon has been considered as a meteor, as a parent body of this meteor stream. And here in work, we investigated the structural sensitivity of Phaethon and found that it is sensitive to structural failure regardless of the bulk density condition at the current rotation state, requiring some amount of cohesiveness. This is consistent with the recent observations which revealed dust tails. And more importantly, we also find that Phaethon may be much more sensitive in the past due to faster rotation, which implies that the large-scale mass shedding process can be triggered, which can be a source of the Geminid meteor stream. And for more information, I posted tomorrow, and the poster ID is 100, so it should be easy to remember. And again, I'm Nakano, present shedding activities of asteroid Phaethon. And thank you.
Thank you. Next, we have Katarina Slavichinska from the University of Central Florida. Katarina.
Hello, so I'm Katie Slavichinska, and I work for Dr. Christopher Bennett at the University of Central Florida. And I'm going to be presenting a poster on spectral effects of carbon-bearing species during the space weathering of airless bodies. So understanding the effects of space weathering is essential to asteroid characterization due to its oftentimes drastic effects on their spectra. Most of us here are probably familiar with the spectral effects of space weathering seen on lunar soil caused by submicroscopic metallic iron formation, but a wide range of other spectral effects have been observed during space weathering simulations of carbonaceous chondrites specifically, including sometimes spectral brightening and bluing. So constraining and understanding how different variables can affect such spectral changes in carbonaceous chondrites during space weathering is going to be vital, especially now as Hayabusa 2 and OSIRIS-REx are working on bringing back samples from dark carbonaceous asteroids. We've designed an ultra-high vacuum chamber for simulating space weathering on regolith samples that will include multiple irradiation sources, heating and cooling capabilities, and an optical setup for collecting diffuse spectra in the visible near IR and mid IR with a geometry similar to RELAB. We are planning to simulate space weathering on both carbonaceous chondrite meteorite samples, as well as simulants of them produced here at UCF in the X lab, so we can control mineralogy and organic content. This experimental design will hopefully enable us to selectively control many variables that can affect space weathering processes and therefore systematically constrain their effects. If you're interested in hearing more or discussing this with me, please come see my poster, which is number 89 tomorrow.
Thank you so much, Katie. Next, we have Keith Tauscher from the University of Colorado at Boulder.
Hello, everyone. My name is Keith Tauscher. I work with Jack Burns at the University of Colorado Boulder. I'm a soon-to-be graduating graduate student, and I work with him on the Dark Ages Polarimeter Pathfinder, which is DAPPER, which he talked about this morning. And I basically designed the data analysis pipeline for DAPPER with the help of a few others. And really the main problem that we have to solve in that, like for the data analysis to measure this 21 centimeter global signal to learn more about the early universe, is to look through the galactic foregrounds. So the foregrounds are 4 to 5 orders of magnitude larger than the signal. So we really have to use pattern recognition to separate out the foreground from the signal. And my poster is about our method for making this as easy as possible. So it's easier to separate the signal and foreground when they look more different in the data. So basically we have two different methods of making the foregrounds and signal look differently. So the signal is the same for all time bins, and it also appears only in total power polarization, whereas the foreground appears differently in every time bin and it appears in all polarizations. So basically how we measure the data using this dual dipole antenna allows us to measure polarization and time dependence. And my poster is about how we use those two things to help in the separation. So come check out my poster tomorrow if you want more information.
Excellent. Thank you, Keith. Next, we have Gavin Tolometti from the University of Western Ontario.
Hello, everyone. Can you hear me?
Yes, very well.
Excellent. So, hello, my name is Gavin. I'm from the University of Western Ontario and the Institute for Earth and Space Exploration in London, Canada. And my poster, using temperature constraints to identify potentially traversable permanently shadowed regions at the lunar South Pole, builds off the work by Sargent et al. 2020 when they were trying to study the trafficability of regolith within PSRs. And we know ever since water ice deposits have been detected in some PSRs in the South Polar region, future robotic and human exploration missions have been proposed to prospect and potentially mine this material. But we knew little information about whether these robotic platforms could actually traverse on the regolith. We didn't know much about whether it was strong enough to hold rovers that we've been designing, or whether they'd be stronger than regolith we can actually see through videos and images from the Apollo days. So from Sargent et al. 2020, where they were able to peer into the shadows using secondary illumination scattering off of opposite crater walls, they were able to study the bearing capacity of the regolith using boulder tracks so they could find within and outside PSRs. And they discovered with certain thermal conditions that the regolith is potentially traversable for robotic platforms. So we use diviner annual and maximum temperature data to constrain these temperature conditions and narrow down what PSRs that are greater than 0.15 kilometers squared could potentially be traversable for robotic platforms. So if you would like to learn more about where we could send robotic platforms to look for water ice deposits, come see our poster number 73 tomorrow morning.
Excellent. Thank you, Gavin. So clearly we have some fascinating presentations ahead of us at the next poster session. But there's also some additional exciting work being done by students. And for that, I'm going to pass the baton to my colleague, Ashkan Najad.
Thank you, Brian. Thanks for a fantastic lightning round session. And just to say an additional word or two, this next talk that you're going to hear is part of our major emphasis on supporting young people, early career people. I think you're going to really enjoy it. This is a project we've supported at the University of Michigan, but to introduce it, I am going to introduce our staff member, Ashkan Najad, who has been the project manager of this for the last year. So Ashkan, please go ahead.
Thanks, Greg. Yeah, I'm incredibly proud to introduce the team behind this next presentation. Last year, Survey participated in NASA's XHAB, Exploration Systems and Habitation Academic Innovation Challenge. And the call was to evaluate the viability of mixed reality tools and technologies in the field and how they might also complement existing capabilities. We've had the pleasure of working with a two-group team, the Bliss and Claus teams out of the University of Michigan. These are comprised of just exceptional individuals. I'd also like to just take a moment and send some gratitude to members of our Survey teams for lending some of their time and support to this project. So from the Bliss and the Claus team, I'd like to go ahead and hand it over to Riley Schnee, Alex Senna, Sahil Farishta, Rupal Nigam, Emily Russell, and Caesar Mu. Guys, go ahead, take it away.
So hello, everybody. Today I'll be introducing the work done as a collaboration between the Claus and Bliss teams at the University of Michigan, all to create new tools for future lunar astronauts. Claus is the collaborative lab for advancing work in space, which creates human-centered, software-driven applications, all to further humanity's presence in space and streamline mission procedures. Over the last 2 years, this has come in the form of augmented reality or AR software for the Microsoft HoloLens. And Bliss is a bioastronautics and life support systems group. They address the physiological and psychological problems that are needed to improve human space exploration architectures. And this has come over the last 4 years in the form of 6 XHAB challenges with various NASA centers, with our 7th beginning work in September. And I'm Alex Senna. I'm the systems lead for the project this year. The whole team is a multidisciplinary group of undergraduate and graduate students from across the University of Michigan, all developing software to further human space exploration. This current breakdown allows us to start our work from the earliest stakeholder ideations all the way through that final implementation. And this project specifically had the goal of creating that next generation of technology for the unique problems of planetary exploration. Sampling, task management, navigation, and pre-ops planning all need modern solutions before we can comfortably return to the lunar surface. And the collaboration between these two groups formed from the overlapping needs of the suits competition as well as the XHAB challenge this year. The suits RFP specifically mentions granting astronauts new independence while equipping them with new tools specific for the lunar environment. And the XHAB challenge specifically wanted to take these same ideas, but put them in the analog field trek environment to serve as a practical demonstration. And we're not the only team working on this. Several people in industry have been working on AR projects with the same goal. And we've been using Jarvis and HoloSextant as well as many others as inspiration throughout the entire development process.
Hello, everybody. My name is Sahil, and I am the systems administrator for Claus. I'll be going over the architecture of our solution. In response to the RFPs, our team decided to focus on making exploratory tasks such as navigation and sampling easier by creating a flexible and non-intrusive toolkit. And we call this system Atlas, the AR toolkit for lunar astronauts and scientists. Atlas interfaces with an external server that hosts the Claus Mission Control Center. This enables an exchange of information during EVA operations and allows for mission data to either be transmitted to the HoloLens or reviewed later by Mission Control Center operators. To support all of these objectives, we put together mobile support equipment. This includes a suite of external sensors connected to a Raspberry Pi for data storage and processing. To address the drastic changes in lighting in a lunar environment, we have included an external lighting source that is activated by photoresistors. The building blocks of the Atlas infrastructure are protocols and modules. Each protocol is designed for a specific mission state and has modules which provide the core functionality for each task. In addition, we have some utility classes that contain general use functions to streamline development. The protocol manager runs at startup and ensures smooth transitions and continuity between protocols and their modules. Here we can see an example of the sample collection protocol broken down into the various modules and utility classes that it leverages.
I'm Rupal, the administrative lead, and I'm going to talk about some of our protocols and modules. For the navigation protocol, our goal is to provide guidance through waypoints while minimizing obstruction to the astronaut's field of view. In addition to the general use case waypoint, we also have special classes for landmarks, sampling sites, and hazards. Astronauts can receive navigational guidance to all types of waypoints, and they can also set waypoints at their current location during an EVA. Here's the data structure of a waypoint. All of this metadata gets captured whenever one is set by either the astronaut or by mission control. For the sampling task, our goal is to support and augment planetary science operations through GeoNotes. GeoNotes are a custom data structure that we created, and they consist of sampling specific mission tasks, associated imagery, audio recordings of voice notes, and the QR codes of the sampling containers. Every GeoNote is also associated with a waypoint, and all of this information is stored on our MCC and can be easily accessed during post-mission analysis. The primary way to interact with Atlas is through voice commands. The naive solution is using keyword recognizer, which maps specified words or phrases to different functions of the backend. However, we can improve upon the solution using conversational AI. Our smart voice assistant is called Vega, which is built using an open source platform and handles natural language processing. We can currently provide information to the astronaut about biometrics and also plan to extend these capabilities to include navigational guidance. On the right, you can see a sample conversation that an astronaut could have with Vega, and as you can see, they can ask about their heart rate, if there are any warnings, and how long the water supply will last.
Hi everyone, I'm Caesar, the Mission Control Center lead, and I'll be giving an overview of our MCC. So the MCC is a web application that relies on a Django web framework and a PostgreSQL database. This serves as a central hub that will be used by everyone on the team in every stage of the mission. So before the mission, the team can come together to review mission procedures and mark any important waypoints and areas on the map. And then next, during the EVA, the supporting team of mission controllers and scientists can enter the control room page. This is where they can see an overview of everything that's happening in real time, including biometrics, communications, and GeoNotes. They can also modify waypoints and mission procedures, such as adding get-ahead tasks, for example. Finally, after the mission is over, the team can go through all the data that's collected and use this information to improve upon the next mission. And then the cycle starts all over again. So here's a look at our navigation tool. We're currently using the Bing Maps API to display all of our waypoints, which you can see in the list on the left. Here's a look at our GeoNotes tool. The notes are listed on the left side, and clicking on a note will pull up the details on the right side panel. Aside from the main mission-specific functionalities, the MCC also provides other miscellaneous tools, such as mock telemetry and warning streams. For example, this is a tool to toggle different warnings that can be used during testing to see how our system reacts to different malfunctions. In terms of the overall design of Atlas, our philosophy is centered around minimalism and uncluttered user interfaces. More importantly, the display needs to be readable in both bright and dark environments. We also wanted to standardize the design across different modules so that the overall system felt clean and intuitive. We kept all of these ideas in mind while creating the mock-ups I see here and on the next few slides.
Hi, my name is Emily, and I'll be walking us through an Adobe XD mockup of our Atlas application. So at the upper left, the task list displays the ongoing mission and can expand to its full length to show previously completed and future tasks. The voice assistant Vega serves as the information center, where astronauts can receive warnings, notifications, and messages. When inputting a voice command, a transcript is shown for confirmation, and the associated action is performed. In the bottom left corner, the minimap displays the astronauts' destination, home base, and no-go zones. The user is fixed in the center and is always facing forward. When they turn, the minimap rotates around them for situational awareness. If an issue occurs with the astronaut's partner, their status will turn red, which can be further expanded to show the associated biometrics. To distinguish the current speaker, a microphone will appear next to their name. Warning messages contain their cause and instructions to resolve the problem. Primary warnings are displayed in red and cannot be dismissed from view. Secondary warnings are displayed in orange and are stored as a small dot above the voice assistant. Astronauts are able to set waypoints at their current location through voice commands. The voice assistant guides the astronaut as they drop and name the waypoint. QR codes are assigned to individual sample containers. When a QR code is scanned, a GeoNote will begin. The voice assistant will display the GeoNote duration, the number of images taken, and a red dot indicating that note-taking is in progress. And then once the camera is activated, the window will be wrapped in a green ring indicating the camera field of view. After taking the photo, it'll briefly stay under the voice assistant before disappearing. And then finally, for perspective, this is what our system would look like in the Microsoft HoloLens.
Hi, my name is Riley and I'm the team lead for Claws. I'll be talking about our team's future work. In addition to migrating our Atlas mockups to the HoloLens and conducting testing, we're planning to work on expanding the capabilities of these systems. This includes finalizing control room functionality for the MCC, building external hardware components, and integrating Vega into Atlas. We also have 3 new projects planned for the future. The first of these is Rigel, which stands for Rock Identification and Geological Evaluation. With this project, we'll handle hazard detection and collaborate more with NASA Survey to develop a Trek API for easier integration with systems such as Atlas. For the second project, we want to create a distributed lunar network of nodes using a peer-to-peer system of small and affordable radio towers, such as the one shown here. This system will be able to support multiple astronauts leveraging the Atlas system and relay information between them. The third project will involve incorporating machine learning into our biometrics module in order to model resource depletion on the fly. This idea originated from a meeting with former astronaut Dr. Jim Bajan, where he suggested that using machine learning in this way could give astronauts in mission control a method for determining if biometrics are following an expected trend. And finally, we would like to thank all of our wonderful supporters. Most importantly, we would like to thank Survey for all of their support and also inviting us to speak today. And that is our presentation. So thank you for listening. If you have any questions or would like to chat, please feel free to reach out to us.
Wonderful. Ashkan, do you have any final thoughts?
I just want to commend these students. These are absolutely one of the most incredible groups of people I've had the privilege of working with, and their self-sufficiency and their professionalism and their commitment has truly been unparalleled. So my hat is literally off to you guys, and I wish you all the best and look forward to continuing to work with you guys.
I agree 100%. And what I've been particularly amazed by is your response. You've continued this work and been very, very innovative despite the pandemic and despite having to work from home, and given some great results. And so anyway, wow, what fantastic work. And thank you for sharing it.
Thank you.
All right, great. Well, so we are ready to move on then to the next thing on our agenda, which is plenary session 5, which is co-chaired by Brian Watkins and Marina Gemma.
All right, thanks, Greg. Yeah, I'll go ahead and take it over. Like Greg said, this is the session on impacts and space weathering. So just a couple of reminders, if you have questions, type it in the chat box or raise your hand and we'll keep an eye out for it. So we'll go ahead and move on to our first speaker, which is going to be Carly Peters, speaking on Lunar Sample 61016, documents a rapid development of weathering products in the lunar environment.
Okay, let's see. I should be able to get this going right away. Okay, that look right?
Yep, looks good.
Okay, this is a lunar sample from Apollo 16 that I'm going to be using to talk about space weathering and how quickly it appears to be performing. Okay, and sort of the bottom line will be that return lunar samples are very important to provide some of the key constraints for this very complicated assessment that is ongoing. Okay, 61016 was collected Apollo 16 by Charlie Duke. There you see him picking it up. It's probably the largest lunar sample collected. It's huge, 11.7 kilograms. It's often called Big Mooly after Bill Muehlberger, who was the leader of the Apollo 16 field geology team. Now, when it has been analyzed, this is a cut section through it. It's a very aluminous impact breccia, the bulk of it, but capped onto this aluminum breccia is a highly shocked anorthosite. And between the anorthosite and the breccias, there's a very vitreous material, very vitreous layer. The The sample has been dated, and it's believed to have been emplaced at the Apollo 16 site from South Ray Crater, which is dated at about 2 million years. Okay, now I'm going to switch to how the tools I use to analyze this lovely rock. I'll be doing spectroscopy, and in particular emphasizing plagioclase and anorthosites. So a couple of quick lessons on spectroscopy. Over on the left are a series of lunar samples, anorthosites that have been returned. They all have this characteristic 1.25 micron absorption, which is due to a little bit of iron in the crystal structure of plagioclase. In the bulk anorthosites, there's a few other little things depending on trace components in the sample. But if you look on the right, these are some pure minerals, a pure plagioclase, as well as an olivine and a couple of pyroxenes. And the key piece of information you need to recognize is that plagioclase is very distinctive in its diagnostic absorptions compared to the more mafic, more iron and magnesium rich minerals. Okay, now, of course, we've been looking across the moon for the characteristics of anorthosites. And it wasn't until spectrometers were flown to the moon and could look at high resolution outcrops that we were able to detect this diagnostic 1.25 absorption band. This was first found by the Kaguya instrument in 2008, followed by an overall survey in 2009, which was about the same time that M-Cube started seeing the same thing, and a highly diagnostic characteristic absorption that clearly identifies the presence of crystalline anorthosite. At the same time, however, and this goes back to longer periods using telescopic measurements, these outcrops of anorthosite are always linked to what we call featureless plagioclase. Namely, they're very bright, they're still fresh, but they have no absorptions, no crystalline plagioclase and no mafic minerals as well. So featureless plagioclase and plagioclase sort of go together. The diagnostic properties of the 1.25 micron band is key for making sure you know which mineral you're looking at. Another survey was done later using M-Cube data by Carrie Donaldson-Hanna, and all the little red dots across the moon show you where crystalline anorthosite has been identified. If you can look closely, you can see a lot of little black dots, and those are areas where the featureless plagioclase has been identified. And one of the primary hypotheses was that, well, featureless plagioclase must be plagioclase that have lost its crystal structure and therefore cannot have the electronic transitions that you have diagnostic of crystalline. So it's always thought, well, it must be some process or shocked or some form of plagioclase. Well, we do have shocked plagioclase in our collection. Here's a lovely lunar meteorite that's a gabbro with nice large crystals, and you can see the transmitted light, and you can identify all those bright areas are the what used to be plagioclase, but now under crust polars is glass. There's no cross polar signal. So that's characteristics of glass, which has without the crystal structure. Now, what do the spectra look like? Well, unfortunately, the reality is that maskelinite, this shocked plagioclase, has a strong feature at 1 micron, which means that the little bit of iron that's remaining in the structure is slightly ordered in a wonky octahedral site. When we look at other lunar glasses, like the wonderful pyroclastic glasses or synthetic glasses made from feldspathic material, we see the same feature at 1 micron. So shocked plagioclase is not featureless. This we can also see in laboratory experiments that Fred Hertz and Jeff Johnson did many years ago with a terrestrial anorthosite, but going from a crystalline plagioclase up through higher shock pressures, and eventually you have glass. So you don't have featureless material. Shocked plagioclase, in fact, has a weak glass band near 1 micron. Okay, well, let's get back to 61016. And we had been looking for many years now, trying to understand the properties of crystalline plagioclase and shocked plagioclase. We've obtained samples that have been described as having heavily shocked. And here's some of the first 3 that we looked at. And the first 2, which are actually shown in the orange and green spectrum, have lovely crystalline plagioclase features. Oz has looked at these with particulate samples, and yes, indeed, it's largely crystalline plagioclase with only minor amounts of mescalinite. Well, we had one sample, our first sample of 61016 that we looked at. We said, oh my gosh, it's flat. There's nothing there. Maybe we found it. Well, but if you look at that, that doesn't look quite right. It shouldn't look like that. It's too dark, and it's really, really featureless. And it turned out, yes, that sample, which was saw fines, had some contamination in it from the saw, and that was wiping out the features. So the curatorial group were very kind to prepare us 2 new samples of the same rock, specifically to meet the requirements that we're trying to look at, namely this shocked component.
2 minutes left.
Okay, and I'm close. These are the 2 samples, one that has a chip of that anorthosite zone and the vitreous material below it. And here's a first sample of the vitreous material, large grains. Because they're large grains, it's relatively dark. But if you expand the scale, essentially what you see is a lot of mescalinite, the glass, and a little bit of anorthosite. And this is held up by the analyses that Oz was able to look at as well. So completely consistent story, but it's not featureless. Well, when we look at the chip, here we have this very, very shocked plagioclase, as well as this part of the plagioclase that was exposed to the surface since emplacement Apollo 16. When we look at that, this is what we get. And the first thing, well, the first thing I'm going to talk about is in both of the shocked plagioclase as well as the patina at top, you can see the effects of the mescalinite, the clear glass bands. But what you can also see is that the exposed surface clearly has some weathering components. And the classic characteristics of nanophase iron. So there's no question that this exposed surface has undergone in only the 2 million years that this rock has been exposed at Apollo 16 to accumulate weathering products that we all know and love. So the summary, the main conclusion is that this big Mully shocked anorthosite, emplaced from South Lake Crater, dated about 2 million years, exhibits clear weathered surface patina that must have developed within the last 2 million years. And it's probably less than that. For those of you who know the environment, there's micrometeorites that will abrade the surface constantly. So that's an upper limit of the time scale. The second thing that is likely is that the source of the nanophase iron is not likely to be the anorthosite itself, in that you need to mobilize the iron atoms so that you can have them collected into these individual nanophase components. So you need some mechanism of redistributing any kind of FeO across the sample. And it's unlikely to be the anorthosite itself, which requires some remobilization, perhaps by micrometeorites. There you have the basic story. I don't have time to go through the others, but there are other obvious conclusions that have to do with the character of anorthosite and the featureless plagioclase, which we still don't understand. Last comment I'd like to make is that obviously the lunar samples, and we've looked hard, we haven't examined them all, of course, but the lunar samples continue to provide remarkable discoveries, even though their scope is limited. Clearly, we would love to have additional anorthositic samples, especially those that are probably very friable and are going to be hard to collect. That may be giving us clues where our featureless plagioclase is associated with. So let's get more samples. Thank you very much.
Thanks, Carly. We'll just do one quick question. We have one in the chat window here. Do you expect to see widespread shocked plagioclase on the lunar surface, and where do you think they're most concentrated?
That's the $64,000 question, as we used to say. We don't know. Clearly, there is shocked plagioclase. Clearly, it is distributed. We see mescalinite in the laboratory, but we don't see mescalinite in the remote measurements. We see crystalline in the laboratory, and we see crystalline in the remote measurements, but in the remote measurements, we see featureless plagioclase. How is that discrepancy resolved? I don't know the answer yet. There are several hypotheses that might work, but we don't have a definitive answer.
All right, great. Thanks again, Carly. All right, so we'll go ahead and move on to the next talk in this session, which will be William Farrell talking about mapping the surface potential and ion flow in the lunar south polar region.
All right, can you hear me okay?
Yep, I can hear you.
Can you hear me okay?
Yes, I can hear you at least.
Okay, great. And you can see me, and you can see my screen, right?
I see your screen, yep.
Great, let me get this, yep, hold on, it should be. There we go, sorry about that. What I'm gonna do is give a little review over really almost 10 years of work on our work on mapping the surface potentials in the lunar polar region. And the reason why this is important is because, of course, ion inflow and the surface potentials have a lot to do with weathering, but it's also, these maps can give an indication of where you have to look out for anomalous charging to explore. So there's both an exploration and a basic science reason for looking at this, study. I'm going to also emphasize some work recently by my colleague, postdoc Doug Rhodes, who's actually left Goddard in February. So he has some new work on this, which I'll highlight as well. So as you know, the moon spends 3/4 of its lunation immersed in the solar wind plasma. And of course, this talk is very different from Carly, who's talking about solid rock stuff. I'm talking about plasma, the most ethereal, low density. In fact, at 1 astronomical unit out near the moon and the Earth, the solar wind is 5 particles per cc. Of course, it's streaming at 400 kilometers a second. In fact, it's the flow, the plasma flow, which consists of protons and electrons, is collisionless. But the particles do exert an influence on each other. You can almost think of it as a viscosity through their electrical forces. For example, if you displaced a set of electrons relative to the ions, there'll be an electric field that will draw those electrons on back. And of course, the moon, which is mostly non-magnetic, it represents an obstacle, a solid surface obstacle to this plasma flow. And there's actually a trailing wake, which actually ends up being part of, which we'll talk more about. So, so if you just looked at how the surface of the moon would charge without any topography, because really the regolith is an insulator, it's really a story of contrast. On the day side of the moon, solar radiation frees up photoelectrons, and the surface charges a few volts positive. However, in the night side, you have this lunar wake. Really, it starts out almost as a perfect void that goes out to 10 lunar radii, and the density drops out to about 1/500th of what it would be in the solar wind. Further, on the night side, the surface charges up strongly negative. So it's a few volts positive on the day side, strongly negative on the night side, and you have this steep transition region up near the terminator. So the terminator is very complex. And just to show you that some of this is backed up by data, we have some super thermal ion detection experiment side LSEP data, which actually shows this drop in the surface potential as you approach the terminator from near zero to minus 100 volts here up near the terminator region. One of the things we started looking at then, barely inspired by the side data, is exactly how the solar wind would flow in the polar region. You have to realize that the solar wind is flowing horizontally in the polar region, and things like mountains and craters represent obstructions to the flow. And what you're going to form are little mini wakes behind the mountains and the craters, giving rise to large variations in the surface potential at the regional and local level. So we examined this plasma flow and expansion process. I mean, what really happens is the plasma flows over, gets obstructed, but the electrons move in ahead of the ions, and you end up with an ambipolar or an expansion electric field, which then deflects the ions in behind the crater. So it just doesn't stay a perfect vacuum behind these objects. The electrical forces actually, in some sense, deflect the ions, actually, in real sense, deflects the ions into the crater. So we modeled this effect. We modified known plasma expansion equations, and now included the fact which were normally one-dimensional. We include the fact now that they're both flowing in one direction in delta X and expanding in delta Z. Right? And this was in 2010, we looked at this. And a great example of this that we did is we looked at the plasma potential that forms within Shoemaker crater. Now, of course, this is a model, and early on we were using the Goldstone radar topo data, but when you get our plasma potentials, you can almost think of it as almost like on Earth, they'd be comparable to pressure systems in weather. So this is space weather within Shoemaker crater, but it's in the form of an electrostatic weather. And the plasma potential goes strongly negative on the leeward side of the solar wind flow, primarily because that side is in need of getting some ions, so it charges strongly negative on that leeward side. On the far side, ions are deflected and surface is less negative. These negative surface potentials are indicative of regions where you have a plasma dropout. In fact, the plasma density drops out as the exponential of the potential divided by the electron temperature. So in the leeward edge, you're getting a plasma dropout of almost over 1,000. Now, given this kind of model, you can now make surface potential maps. And these maps included both the expansion potential and the near surface sheath surface potential that forms. And actually, the maps look stunningly like illumination maps, don't they? Well, of course, they kind of should, because where you're getting the sun illuminated, that's where you're releasing photoelectrons and your potentials are a few volts positive. In contrast, where it's in shadow, you're getting that plasma expansion effect and the large negative potentials. So in fact, we ran our codes and end up with these maps. This is for solar wind flowing, I think for third quarter and for first quarter moon here. Given these models, you can do other things, like you can adjust the plasma temperature. For example, in the middle here, you have the typical solar wind of 10 electron volts. In plasma, we talk about temperatures in terms of electron volts. Each electron volt is 11,600 degrees Kelvin. So you're talking about 100,000 degrees Kelvin for the plasma, right? Not the surface, the plasma. Really represents the width of this distribution. But what happens is when a solar storm, a coronal mass ejection, is emitted from the sun, right behind it, you form a shock, but right after the shock passes the moon, the plasma warms up. And of course, our models would suggest that as the plasma warms up, the surface potential goes more strongly negative, right? But then once that warm plasma leaves and you're getting to the driver gas of the coronal mass ejection, it's actually a cooler plasma. And so in that case, the plasma is less negative. So these kinds of maps and these kinds of models allow you to map the dynamics of the solar wind down to the south polar surface where our astronauts are going to be. So Dov Rhodes, our postdoc, again, he left in February. Otherwise, he probably should be presenting this, but I have a chance to present this. You can tell I did it because I think I spelled instantaneous. I think I spelled instantaneous right. Anyway, this is he ran these models, actually modified them and ran them for Shackleton crater, kind of updated the models. And you can see again in Shackleton, you can get on the leeward edge of the flow, large negative potentials up in the upper left of minus 100 volts or so in that leeward edge. And you see the density, you see the density drop out on that leeward edge. Also, what you can see here in the lower left-hand panel is the ion flux, showing that the ions do in fact hit that far wall, but don't hit that leeward wall. So what you can do, okay, gotcha, couple of 2 minutes. What he did then is a lunation integrated ion flux of the ions getting to some of the various polar craters. And this just came out in a Planetary Science journal. But in particular, he found that, of course, there's a reduced ion flux to the floor of the polar craters on a lunation integrated map. And it's particularly true for Shackleton, probably due to the unusual or relatively higher depth to diameter ratio, which doesn't allow the ions to deflect in to the same degree as it would the larger polar craters. You can also look at things at sputtering lifetime for a half micron ice layer. And he found that on the walls of the craters, it's relatively short, like 100 years, but in the floor of the craters, because of the reduced ion flux, it can be closer to 10,000 years. But notice we're not saying a billion years. In other words, even if you, by sublimation processes, can keep that ice on the surface for a billion years, sputtering and plasma inflow really will limit the amount of time that ice will stay surface exposed to, tens of thousands of years sort of thing. Another application is charging. He has a paper out in Advances in Space Research on drill charging in a polar crater, where you generate charge by the triboelectric contact between the drill head and the regolith. But what happens is the regolith itself is a poor conductor in these cold regions, and you're in a plasma star polar crater, so you run the possibility that you can develop anomalous charging on the drill. In fact, he was modeling it with over 10 kilovolts in a few seconds. So that's something that you got to think about and need sound engineering practices to figure out how to remediate that kind of charge buildup. And in his paper, he discusses a couple of these. So to conclude, we've got these predictive maps. Actually, we've sent them to Marshall Space Flight Center, who are using them as part of their space environment studies. But ultimately, we need a modern day landed plasma system to sort of validate and map out the potentials for real for comparison to our simulations and our modeling. But again, the applications include charging within the craters, near these obstructions, and actually ion influx and plasma sputtering into polar craters where you, as a loss for the volatiles, surface exposed volatiles. Anyway, that's it.
All right, thanks, Bill. There is one quick question. Do you think similar things will happen to topography shaded regions on the illuminated surface, such as shadows of crater walls? And how do you think this effect compares with direct solar illumination?
I'm not sure. Could you repeat the question?
Yeah, it says, do you think similar things will happen to topography shaded regions on the illuminated surface, such as the shadows of crater walls? How do you think this effect compares with direct solar illumination?
Yeah, it depends on how deep the shadow is, and roughly the term plasma folks use is a Debye length. And if you're many Debye lengths in the solar wind, the Debye length is about 15 meters. So if you are at the terminator and you have an obstruction that's a couple or 3 Debye lengths, you'll start to see these really strong changes in the plasma potential. Less than that, you'll probably get a reduced effect.
All right, great. Thanks again, Bill. I think there's some more questions in the chat that you can take a look at if you have time. But we're going to go ahead and I'm going to hand it over to my co-chair, Marina, to introduce the next speaker.
Okay, thank you, Ryan. So next up, we'll be hearing from William Yingling about impact melt and placement on terrestrial bodies. So William, whenever you're ready.
Okay. Okay. Everybody see my screen okay? It's in, could you swap the displays? We're seeing the presenter mode.
There, is that better?
Perfect.
Okay, thank you. So I'm Will Yingling. I work with Dr. Catherine Niche and Dr. Livio Tornabene at the University of Western Ontario. Today I'll be talking about impact melt and placement on terrestrial bodies, particularly focusing on Mars and how it relates particularly to the moon. So impact melt is commonly found in and around craters. During an impact event, there is vaporized rock, there's melted rock, and largely displaced rock. And so we're focused on the melted rock. And we particularly want to know how the rock, the melt goes from inside the crater to outside the crater. And so we see a very famous example here of Tycho crater on the moon with melt to the southeast here. And we can see some clear examples of melt happening on the moon. So there's also impact melt on different worlds, particularly the study focused on looking at complex craters. And so there's complex craters, we see them on Mercury, Venus, the moon, Mars, even Ceres, and the Earth. So that's what we're focusing on for this thesis. To introduce the problem is that so as I mentioned earlier, is that we're looking to see how melt goes from inside the crater to outside the crater. And so we have two emplacement hypotheses that have been established for the moon and for Venus. For Venus, it generally has melts, and the energy imparted from an impactor is imparted into the melt, and which is able to push it up and over the rim during the excavation stage of emplacement. And just as a general reminder, we have our generally 3 stages of cratering process for the contact and compression stage, excavation stage, and the modification stage. So for Venus, it happens during the middle of the cratering event. For the moon, however, there are generally deeper craters than we see on Venus due to the inverse gravity scaling law. And there's generally smaller volumes of melt. I believe the difference in impact, the mean impact velocity between Venus and the moon is the Venus has about 25 kilometers per second, whereas the moon has about 19 or 20 kilometers per second average impact. What likely happens is that the energy, there's not enough energy from the impactor to push the melts up and over the rim, but rather the rebound mechanism that takes place during the modification stage likely adds to the momentum and is able to push the melts at the lowest potential energy barrier of what we call the rim crest low. So just basically the lowest point along the crater rim is where melt is preferentially going to cross over the rim. So we have, we have melts on Venus. In this example, we have Xantippe crater, where we have melt to the southwest, this very striking swath of melt in this radar image. Very clearly, the direction of the melt is to the southwest. And we also have a DTM here for panel B, which, can you see that okay? Okay. So for panel B, there's a DTM, and the rim crest low, so to speak, is to the north. You can see that there's a depression to the north, and so we consider that the rim crest low. And so what we then do is then we put those two together cardinal directions, and then is 135 degrees. And for the moon, we have another example of a crater with melt, Ohm crater here, where the melt, we have this nice zoom in picture of melt happening just to the southeast of the crater, where you have distinct surface roughness changes. You have distinct albedo contrast for the melt happening itself, but that's not necessarily as easy to see on Mars. So we have a different classification for that, which I'll get to in a second. And then for panel B, we have a rim crest low also to the southeast, likely because the pre-existing topography was already depressed. And so in this case, the melt distribution direction and the rim crest low, we say coincide, so lie at 0 degrees. So for Mars, how do we categorize melt? Is that since Mars has an atmosphere and it's dusty, we need another characteristic to help identify melt. So what we can use is crater-related pitted materials, which are quasi-circular depressions that occur in dense clusters with also subtle raised rims. And so the melt that these are found in often occur at topographic lows as well. So these crater-related pitted materials are important because they're associated with the volatile rich nature of the Martian regolith. And so we don't necessarily see these on the moon. It's not observed on the moon, or Mercury for that matter, since they're volatile pore bodies. But we do see them for Ceres and Vesta, which are also volatile rich. So for mapping examples, is that we have a couple of examples here of craters that I've mapped on Mars. The colors aren't necessarily too important in this case, just that the melt distribution is the important part. So we can see the clusters of melt distribution, and we can decide where the melt distribution is that way. And then from there, we can take the next step and make DTMs, and then assess where the rim crest low likely lies. And so we can do this either visually, or we can use basically ArcGIS, ArcMap to do a tracing of the crater rim, and that'll tell us exactly what the elevation profile of the rim is at every point. So for these cases, we have the rim crest low at these directions. Okay. So back to our mapping examples. We know the melt distribution, and we know the rim crest low direction. And so then we can categorize coincide, or for example, they're 90 degrees or greater. So how does this relate to other bodies in the solar system? So Mars looks, so our sample size is relatively small, with just 12 craters compared to the 49 or almost 50 craters for the moon. But Mars can tentatively be grouped with Venus and Mercury. So what does that ultimately mean? Is impact, melt, and placement on the moon seems unique amongst the terrestrial bodies, at least so far. We could see more follow-up work with on Mars or on Ceres even, but it would seem that surface gravity appears to play the bigger role in melt and placement than impact velocity in this case. And yeah, that's my talk.
Okay, great. Thank you, Will. I think we have a minute or two for a couple questions, if anybody has any.
And if not, I'll start off with one. So you're talking about the terrestrial bodies, and I noticed you did not include Earth in that category. Is that a reason for that, or are the impact craters on Earth not super useful for what you're doing?
We haven't seen a whole lot of impact melt is very hard to, it gets eroded very quickly. And so we don't see it nearly as much on Earth. So that's why we're looking to Mars.
Right. Awesome. Thank you.
Okay. Thank you.
Okay. If anybody has any questions. Okay. If not, I think we'll move on to the next talk in the interest of time. Thanks, Will.
Thank you.
So next up, we have Krisa Abdelidou talking about hypervelocity impacts on carbonaceous asteroid analog materials.
Hello, can you see me?
Yes.
Oh, 1 second. I'll share the screen. All right. Can you see now my screen?
Yes.
Okay. So first of all, thank you for giving me this opportunity to present the first work that we did, this large campaign of hypervelocity experiments. This work, as I said, is only the first step, and I will explain why. And it's a collaboration between 4 different laboratories, 2 in France, the Impact Lab in the UK, and also the Exolith Lab in the University of Central Florida. So what is the problem that we would like to address? So nature feeds us with free samples of different solar system materials. However, our atmosphere plays a very negative role for sampling in a wide range of these materials because it filters out the weakest of them. So the extensive properties of some primitive, specifically of the primitive asteroid materials, like the carbonaceous, for example, asteroids, such as their porosity, their strength, the compressive and tensile strength, the thermal conductivity, are not well captured, thus, and they are not well represented in our meteorite collection. So these materials are very weak, they are very rare, as far as we understand on our collections on Earth, but at the same time, probably they are very abundant in space. And why do we say that? The current ongoing space missions, the Sampler-10 space missions, the Hayabusa 2 and OSIRIS-REx, they have provided data from which we can infer thermomechanical properties of boulders, for example, of the asteroids Ryugu and Bennu, and they seem really to be weak and porous. So both of these asteroids are carbonaceous, so they are similar types, and they probably represent the largest group of asteroids. That's why we say that they're rare on Earth as meteorites, these materials, but very abundant in the asteroid belt. So the question here that we try to address is that how the different processes that they act on space act specifically on these very weak materials. The most important ones that I explain here are the impacts that they can cause small scale, but also large scale alterations on the surface of the small bodies. That is the comminution, so the production of regolith, but also the larger crater production. In addition, there are also the thermal cycling effects that it has been demonstrated in the lab, as you can see here in these images by a work in Nature by Marco that spoke before for families, not on this topic, that they demonstrate in the lab the action of the thermal cycling on the cracking of different meteorites. And also, it is now also observed, there are some works published on data from OSIRIS-REx, but also some works on preparation. So Bennu and Ryugu, therefore, can be more a rule than an exception in space. If we understand their materials, we can understand more closely this large group of asteroids. So specifically here, what we did. is that we want to do these several experiments in order to compare. Initially, our first idea was that how do we compare the process of impacts and the process of thermal cycling on the same, for example, meteorite type. But in order to have reproducibility, we realized that the meteorites that we could buy, let's say, they were too small in order for me to perform the impact experiments, but also we couldn't have good reproducibility, both in experiments, but also in thermal cycling. So we came up with the idea to use the best possible simulant materials that we can find. That's why we also were in contact with the Exolith lab, and they prepared everything for us. So let me explain. In this study, we advanced from the previous ones, and we didn't use for the impact experiments common materials that we used to do. Whoever of us did laboratory impact experiments in the past, we didn't use commonly used materials like earth basalt or anorthosites, or just simple sand regolith or glass beads to simulate regolith and so on. So we went exactly to have the best possible material in order to reproduce the types of rocks that we wanted. So we used the recipe of the Exolith lab of the CM2 asteroid simulant. And the only addition that we did of whatever they have produced and published is that we added 15% of the volume, some glass spherules, and the sizes were some hundreds of microns. Why we did that? That was in order to achieve that the sample that we will use has the same spectroscopic, very similar, let's say, spectroscopic match with the observations from Bennu, but also matches some of the observed properties from Mascot on the surface of asteroid Ryugu. And that was, they saw that Ryugu material has some inclusions that are around millimeter size, so larger than the contours that we can find on average on the CM materials. That's why we included some glass beads to simulate these observed inclusions, but they were larger than the controls that we have in the literature. So this mixture was then used in order to prepare the blocks that you can see here in the picture, and we used in the impact lab. And we had to do so big samples in order to be sure that we can have a beautiful crater formed on them. So let's go quickly. While we were doing the impact experiments, we were doing also some other measurements on the very same blocks that we use in the impact lab. So in collaboration with the lab in Grenoble, the University of Grenoble, we measured the compressive and the tensile strength of these blocks, as well as their thermal conductivity. And if you can see, the values here are very low, and they are very comparable with the lower values that we have for some carbonaceous meteorites. So let me show here the comparison. In particular, the compressive strength of our simulant rocks is an order of magnitude lower than the one that is measured for similar meteorites like the Murchison and the Sattersmere. Also, assuming that tensile strength is about factor of 10, let's say, 10 times smaller than the compressive strength, we see that the 0.7 megapascal that we measure is also much lower than the theoretical that we can infer for these two specific meteorites. In addition to that, the tensile strength that we measure is very much comparable to the one of some other meteorites, CI and C2, the Ivuna and the Taigis Lake. And these are among the most fragile meteorites that we have in the collections. So the great thing with the simulant blocks is another thing also, is their thermal conductivity in comparison, in combination, with their porosity. That, as you can see in this plot, this plot is adapted from last year from a paper in Nature Astronomy of Groth et al. That it is there are measurements of Hayabusa 2 from Mascot and Mara from the surface of a boulder of Ryugu, and this. You can see the comparison has two models for the Ryugu boulder, and you see that our simulant is really in between the measurements that we have for Col Pokeball, the only CM carbonaceous meteorite, and on Ryugu. So the simulant goes really in the good direction of properties. So very quickly, in the impact lab, we use the same simulants. We did 6 different sorts. We changed the impact speed and the size of the projectile. So we changed the impact energy. The projectile was a stainless steel, not super representative of the solar system material, but it was good enough in order to achieve beautiful craters and some ejecta production for further analysis. So some pictures before I finish. First of all, we saw that the texture of the material is very similar to the observations of Mascot. So in one side, you can see my crater, the other side, the observation from Mascot of Hayabusa 2. We have also the estimation of the roughness. And as you can see, the mean slope is very similar, both on our impacted samples and on the measurements that they did by Grot et al. Of the Hayabusa 2 measurements. So regarding the craters, here we have some images of the craters that we produce from different impact speeds. We can see material uplift around, it could be the spalling area, and also we recorded, we see formation of layers in the impact, in the crater, walls. So some of the samples, they had some pre-existing cracks, and we see that the crater that generated actually stopped at the borders of these cracks. It didn't expand more, so we had these square, funny crater shapes that they are very comparable with some measurements, some observations that we have on Bennu of OSIRIS-REx. Also, we have measurements of size of diameter depth ratio. We compare with other measurements for the mini craters on Bennu. I cannot talk about this more because this is a beautiful observation work by Ron Baluz et al. And team of OSIRIS-REx, so I cannot say more results. I hope he will present soon. And the last thing is that we also checked the ejecta, and we saw that we can produce both what we call monomineralic and the multimineralic fragments that probably come from the different locations around in the crater and around the impact site. We can see also shattered inclusions, broken inclusions, or also unshattered inclusions. So this gives us actually that we have a gradient of shocked material inside the ejecta. So that's it. I will leave you with our summary for now for this first set of experiments. And I'm very happy to answer questions now or later in an email. Thank you.
Thank you, Krisa. I think in the interest of time, we'll just move directly to this discussion section. So if anybody has any questions for Krisa, we can ask them now and also open up the floor to questions for all the speakers from our session. I'll start off with a question then. So I noticed that you said that your simulant was a 70 micron grain size. Do you guys have any plans to look at other grain sizes or mixed grain sizes?
So the simulants, I think this question is more appropriate probably to people from the Exolith lab. Probably there's some, I don't know if Dan is online now to answer. But for me, for now, because we have already started the design of new experiments, I will go for the same mineralogy, for the same grain size, with the same inclusions we did with this set of experiments, but we are going to try to change severely the porosity of these samples in order to try, actually, I don't know if you can see my slide. Where is it? Here. So we try really to change the porosity in order to see how the thermal conductivity of the same material, the same grain sizes, how this will change in order to try to mimic as much as possible the observations from the spacecrafts. So for me, the immediate future is to go that way.
Absolutely, thank you. So we have a question for you in the chat as well. How did you quantify the ejection mass / velocities? And what do you think causes the lower ejection mass?
Right. Okay. Very good question. So first of all, I have videos of the speed because I recorded the impacts with 2 different external cameras outside of the impact chamber, but we haven't analyzed this data. We are waiting to do the further experiments, and then we will wrap up all this problem of the speeds of the ejecta. Now, the mass of the ejecta, I had this set up, let's say. So I tried to collect the ejecta that I had from every shot. And I have to say, for the lower speeds, like 0.8 kilometer per second and 2 kilometer per second, we had no ejecta, or it was so tiny that it was just impossible to collect. So for the rest of the speeds, as we were increasing the impact speed, we were increasing a little bit the amount of ejecta. However, this is much, much, much lower than what we have seen, because I did other set of experiments using earth anorthosite and other type of materials. This is severely reduced compared to the same impact speeds and energies using other blocks and not these asteroid simulant materials. This could be because this material is very porous, so it has less production of ejecta. Some experiments have been done earlier in the past by other colleagues. And also it could be maybe due to some compaction, but still the porosity that we have is not so high in order to excuse a compaction yet.
Okay.
So
we have another. Oh, sorry.
No, this.
We have another question from the chat. Could you elaborate on the fifth point? Ejecta mass is reduced with increasing speed. I think this is from your conclusion slide.
Ejecta mass was? Yeah. I'm sorry, I want to say increasing with increasing speed, reduce. I'm sorry, that was a typo, is what I explained so far. But it was decreased with the porosity because we did complementary. That was a typo with the complementary, yeah. With the complementary experiment that we did on totally different types of materials with lower porosities.
Okay, thank you. And if anybody has any questions for any of our other speakers, feel free to ask them now.
All right, well, I think we will go ahead and wrap up this session. It looks like we have a little bit of a break before the parallel sessions start. So you guys can just check out the program to see we've got a session on all things asteroids and one on human and robotic exploration.
And those sessions will start in about 12 minutes. So thanks so much to the session co-chairs, Marina and Ryan.
Yaji?
Yes, I can hear you.
Okay, just checking.
Okay.
For just the reason that Ricky just posted something to everyone. And you can see me.
Yeah,
I can see you.
Okay. Mind you, I don't want to see me, but
I'm ready to go whenever I'm allowed to share my screen.
give us another couple minutes. They wanted, I think, to start at 2:45 my time.
They pushed everything back.
So.
Hey, Faith, can you hear me?
Yes, I can. Can you hear me?
Yep, perfectly. I just wanted to verify that whenever it's my time, you will tell me share screen, and I will do so with my PowerPoint.
Yep, I will tell you share screen. I'll also give you a, after 8 minutes, I'll give you a 2-minute warning before the end of the 10 minutes in the talk.
Okay.
Probably going to introduce everybody through you at least, and I'll start the whole session.
And Faith, it looks like we don't have discussion time built in at the end of this session. Is that right?
We have 2 minutes and for each paper, and then there is some sort of a discussion at the end, but I'm not quite sure how that's going to be.
It's Christina. I'll help you. The idea is just to allow people who have questions to continue the discussion. So go ahead once you're done with everybody to just close out all the questions, and then we can just be done.
Okay. Okay.
Greg may have an announcement or two at the very end. I need to ping him on that, but we'll,
at the end of the session.
Yeah.
Okay.
No, I don't have anything to announce, Christina.
Oh, I think you do. I think I have.
Do I? Okay. All right. I stand corrected.
I was going to send it to you in just a moment.
Okay. Okay. Very good.
Faith, I like your decorative use of a ladder.
Oh, thank you. Yes, we're very modern around here. You didn't sign on when I had, I guess, my cookie face on. So
No. And I'm anyway, I just moved into a house, and it's a little bit of a disaster. So I don't even know what my background would look like, but
I considered putting in one of my other backgrounds, but then I thought, well, maybe I should be a good kid about this. And that's up there because we had some storm damage, really.
Oh, okay.
So Larry's left it up there so we can check everything out all the time. Okay. I'm very close to starting. In fact, I'll go ahead and start. Welcome to the afternoon session of All Things Asteroids. I'm Faith Vilas. My co-chair is Yaji Kim from Auburn University. We have a number of talks. Each speaker gets 10 minutes to speak, and there will be 2 minutes for questions. Yaji will start off introducing people. I will be sitting there saying at 8 minutes, you have 2 minutes left, and that will be that. And at that point, I'll turn this over to Yaji.
Okay, thank you, Dr. Faith. Then I'm gonna introduce our first speaker, Dr. Dyer Darby from PSI. Her talk is going to be a quantitative machine learning-based modern taxonomy for asteroids. So, yeah, Dr. Darby, can you share your screen?
Yep, I just did. Can you see it?
Yes.
Yes.
All right, let's do the slideshow. There, how's that?
Yeah, it's fine.
Okay, yeah, it's great.
All right, so this taxonomy key probably won't look unfamiliar to most people in this audience, but I wanted to use it to start out with as a guide to how I got into this. So many of you know that I've been working with various machine learning approaches to understanding spectroscopic phenomena for more than a decade now, amazingly. And I was visiting MIT and talking to Rick Binzel, of course, and he gave me one of his postcards with the Bus de Mayo taxonomy on it, which he carries around in his pocket at all times. And I looked at him and I said, Rick, really? This is this is the new millennium and we're still looking at shapes like this? And he was like, well, Darby, nothing better has come up. And I said, well, I think we can come up with a better way of doing this. So for the past 2 years, we've been working on sort of trying to do proof of concept about how we can update the asteroid taxonomy. And so that's what this talk is about. We were fortunate enough to involve in this project a really brilliant undergraduate student named Sydney Wallace from Harvey Mudd College. She's just graduated, and I'm happy to say that she's going to actually work for us as a postback for the next year, funded by the RISE survey. So hopefully we'll make even more inroads into understanding and developing a new asteroid classification. So that's where this talk is going. Okay, so many of you in this audience will know that we've been struggling for decades to try to figure out a good asteroid taxonomy, starting with Chapman and then working on through Tholen, and of course the current taxonomy I just mentioned, Buss and Bindel and DeMaio. A lot of really great minds have worked on this, but it's a complicated problem, which I don't need to tell anyone about. And in particular, even the most modern incarnation of the Buss-DeMaio taxonomy has some issues. You know, the clusters are based on similarity. They're not based on mineralogy, so they don't really relate to what's going on in meteorites. The current taxonomy is based on only 371 asteroids, so it's not great. The data are all from the same telescope, and some of the other things. There's some very subtle differences. If you've ever tried to work with this taxonomy, you know that there's very subtle differences between some of these shapes. And as a result, there's very little error analysis associated with the taxonomy. So all of these, we hope, are problems that we can fix with machine learning. Okay, so if you step back for a minute and you say to yourself, how can we classify asteroids from a sort of a global sense? There's a bunch of different approaches you can use, and the 4 of them that we've kind of thought about are listed on this slide. So, you know, the first thing you can do is you could just take all the asteroids data that you have and group them with labels using something like principal components analysis, which is what Buss-DeMaio does. And you know, the advantage of that approach is that you don't need labels, but the disadvantage is that you have no independent knowledge of what they actually are, which means that you can't develop error analysis around it. So it's good for a description, but it's not great for analyzing future asteroids because you don't have a, you don't have a sense of the accuracy of your classifier. There are machine learning methods that can do this kind of unlabeled classifying data, but again, they suffer from the problem that you don't have any known asteroids really to work with. So we've focused our efforts on the number 3 and 4 in this on this slide. The first thing we wanted to do was to see if machine learning classifiers would be able to even do as well as the Buss-DeMaio classifier. And then once we established that, we went on to create a whole new taxonomy using data from spectroscopy of meteorites. So 3 and 4 are what the rest of this talk is going to be about. Okay, so where'd the data come from? We were very lucky to have many people in this community supporting us. So we got data from all the people listed here. We mined what was on the PDS. And of course, the data set now has something like, it includes a lot of NEAs in addition to the original main belt asteroids. And as you may know, the Buss-DeMaio website at MIT has a nice little link that allows you to classify asteroids. So we took all these spectra and fed them into the Buss-DeMaio classifier and came up with a Buss-DeMaio label for each of these. And I should mention that in the process of doing this, anybody that's worked with asteroid data is aware of the fact that they're all in different formats. And in order to make this work, we actually had to resample the data and make common file structures. So if anyone is interested, I can point you to our website where you can download this. We now have all of these data reformatted in the exact same format. In fact, the meteorite data and the asteroid data are all in the exact same format, all with headers and all the file information that you need. So we now have a workable data set, and we're continuing to grow this as things go on. We also, as I said, took meteorite data, and again, we've been very supported by the Meteorite Working Group. We've gotten representative samples of pretty much all of the meteorite groups now, and we just got, as it says at the bottom here, an additional 125 samples that were given to us by Relab, and we're going to create even more this summer. So we now have, data. The Achilles heel, of course, of machine learning methods is that you got to have a lot of data because they don't learn if they don't have data to learn from. So as I said, we now have these 2 nice data sets, one for asteroids and one for meteorites, and they're both growing. Okay, so let's look at the results of the first approach here. So the first thing we did, as I said earlier, was to try to use a machine learning classification to reproduce bus DeMaio classes. And to do this preliminary work, because this was literally funded by an undergraduate summer internship, we chose to use two of the sort of basic machine learning classification algorithms. The first one is called logistic regression, which is a kind of linear regression, but only with binary values. And it has a lot of interesting parameters that you can vary, in particular, a parameter called the regularization parameter, or C, which controls the variance in your data set. And so we took that data set of asteroids that we had classified using bus DeMaio, and we tried to build a machine learning model to predict which bus DeMaio group a given asteroid would fall into. And we were able to get a model that was 75% accurate. And I think that's pretty amazing, considering we didn't really do much spectral processing. And as this audience will know, if you're using data that come from a bunch of different telescopes, acquired under different conditions, there's a lot of sort of instrumentation parameters that might be affecting this. So I think 75% accuracy just for a first trial is actually pretty impressive. As you can see, we didn't remove the baseline. I think when we start doing things like removing the baseline and doing some things like smoothing and squashing, we may be able to get this accuracy up even more. But as a proof of concept, we thought this was pretty impressive. We also tested a technique called Gaussian kernel support vector machines, or SVMs. And this is one of a class of machine learning algorithms that projects data into a hyperplane. So as most of you know, when you do any kind of sort of normal regression analysis, in many cases as spectroscopists, we're using it incorrectly, because regression is not supposed to be used in situations where features are collinear. So machine learning algorithms have proven themselves in a lot of different kinds of spectroscopy to be useful in these kinds of scenarios where you get the data out of the dimension it's in and put it into a hyperplane. So that's the attraction of an SVM. It also has two different parameters, another regularization parameter C, and then a gamma parameter that controls the variance. And when we use SVMs to try to reproduce bus DeMaio, we got a 77% accuracy. So again, for a first trial as a summer project by an undergraduate, we thought these results were really promising. Classification results are often reported in these things that are called confusion matrices, which can be kind of confusing. So let me walk you through what these confusion matrices are. So you can see at the top, we're describing there's the regularization parameters, there's the validation score, which is the accuracy. And you can see on the left-hand side is the actual classification in bus DeMaio, and the numbers there correspond to how many examples we had in each of those classes. And then on the bottom, it's the same classes, only predicted. And it turns out that if all the data fall on a diagonal, that means that the classifier is being very successful. And in this case, you can see this is what a 75% accuracy looks like. Okay, let's see. And I just want to make a point here. This is a close-up of one of those. So here's the diagonal going obviously diagonally across. And notice that there were some near misses. And right now, that accuracy score that we're reporting, it would consider a near miss still an absolute miss, because this is a binary thing. So we're pretty confident that when we change our algorithm and use things that are more sophisticated and can use near miss algorithms, that we might come up with things that are a little even more impressive. So here's back to that. So again, notice that most things fall on the diagonal or close to the diagonal, with a few notable exceptions. So these results gave us the courage to try then to do something with actual meteorite classes. So now we're doing the same thing with meteorite classes. We're training a classifier. And here again, things fall pretty much on the diagonal, which means that we could create a model, and we could take our model based on the meteorite spectra and apply it to asteroids. And this then gives you, in some ways for the first time, a direct way of comparing asteroids and objects in the sky with meteorite populations. So on the left, we've taken all of the C-complex objects and predicted them using the meteorite trained SVM. And you can see that you get results that are actually fairly reasonable. So this could be the actual distribution of meteorite-like material in the C complex group. And then on the right is the same kind of thing, only for the V-type asteroids. And you can see, of course, that we expected vestoids to be HEDs. And in fact, that's what the model predicts. So again, very encouraging. And it's not a straightforward thing, because I just wanted to show you, here's a comparison of the two spectra. And they're not identical, but the machine learning stuff has the capability of seeing through these. All right, so to wrap it up, I'll just say that machine learning methods actually allow us to reproduce bus de Mayo pretty well in a much simpler and quantitative way. And that we think that there's great promise in using machine learning classifications based on meteorite classifications. We need a lot more data though. So we're busy trying to fill in the holes in our meteorite spectral database. And then we want to experiment over the next year with pre-processing methods to see if we can get these to work better. The biggest problem with this, I think, is going to be the differences in albedo and space weathering, and we're open for suggestions on how we can try to take advantage of, or how we can try to work around that problem. And that's all. Thank you very much for your time.
Thank you. That's it. We have to go on.
Okay, thank you, Dr. Darby.
Please,
so because of our time limitation, we are going to move on. Our next speaker, Dr. Xiang-Wen Su. Xiang-Wen Su, can you share your screen?
Yes.
If anyone has questions to Dr. Darby, you can leave like on chat, or you can use discussion session.
All right. So can you hear me and see the screen?
Yes.
Great.
I can hear you and I can see your screen.
Yeah, thank you so much for having us. So I'm Sean Shi, and from the Impact One Institute out of the survey located at University of Colorado, Boulder. We could have having you here in Boulder, but unfortunately that's not going to happen. So here I show the team members of photo. So next time we'll see each other again. And this talk, electrostatic removal of fine-grained regoliths on sub-kilometer asteroids, here we try to address one of the issues that are shown here, that on the screen you see 3 different sceneries from 3 different places of airless bodies in the solar systems, and you might just know where they are, and they are very different. So we try to understand what are the processes shaping the surface, and what are the implications, what we can learn from this. And so, you know, as mentioned, that Bennu is really, really rocky. So there is dominated by bouldery scenery, in contrast of the moon, of course, but also to the near-Earth asteroid Eros, which have ponded deposits and indicate a fine-grained regolith. And so this is a quite drastic difference. And if you look at these 3 bodies, one prominent difference is their sizes, which means their gravity is very different. So if you look at the moon, it's basically a planetary bodies, and it has a gravity in the order of magnitude of the Earth. And look at Eros or Bennu, their gravity is in much different regime. And it has been proposed that small bodies like in the Bennu Eros size could not retain thick regoliths because impact ejecta are just fast enough to escape the gravities. And unless you have sufficient gravitational well like the moon has, you will be depleted in fine-grained regoliths produced predominantly by impact. However, recent views somehow shift in the way that an important process, as mentioned this morning, that thermal fragmentations, that is the stress caused by repeated thermal cycles on these airless bodies, could actually produce fragments from the exposed rock. And in the Delbo 2014 paper, it shows that this is actually more effective a process compared to meteorite impacts. And there are indications seen by seen on Rugu and Bennu from these 2 fantastic sample return missions, showing that these quacks might really associate with these thermal fatigue fragmentation processes. And so we consider this is the first process we're going to include, and is independent of object size. So it's basically done by the heating process, not gravity. And the production rate is somehow, it should be tied to the influence of the sun and also the body rotation, that determine their thermal cycles and also what are the temperature change at different heliocentric distances. And the second process is we all familiar is the impacts. And as shown before, that the gravity is a big player here that would determine if these impacts are production or loss for the regulars from regulars retention perspective. So for a moon, which have an escape velocity which is basically higher than 99% of the impact projectile characterized by the large emissions around the moon, you can expect most of the projectile will be retained, in contrast to small body like Eros or Bennu or Ryugu. And but the other new information from the Hayabusa 2 small carry-on impactor experiment, which is showing clearly is that there are also slower impact projectile deposits around the impact crater newly created by these experiments. And so from this perspective, we basically took a really kind of order of magnitude estimate on the fragmentation rate to be 5 to the 10 to the minus 10 kilogram per meter square per second, which is roughly about 10 times lower than the terrestrial weathering rate that is somehow a weakly constrained parameters in the model, but somehow I think this is a good starting point. And the third process is kind of the main character here is the electrostatic dust transport. And it has many indications on airless bodies like Eros. You have these flatted, smooth ponded deposits indicating the presence of small particles, preferably located in the gravitational low locations, or on the 6TP CG comets that they have similar presences of these. And there are many models trying to understand how this is possible through electrostatic transportation processes. But one of the key ingredients in this model that has only been solved recently is how these particles are lofted. And at Colorado, we have serious experiments led by Dr. Xu Wang. So let me start the movie. On the left, you will see this popcorn-like dust lofting from a crater under this high-speed video camera. And what we do is, this is at Earth, and what we did was shining electron beams onto these particles to simulate exposure of ionization radiation in space. And so what we get out from these sets of experiments is that how particles can attend significant amount of electrostatic charges to repel each other is because the presence of these microcavity in the porous regulars, that ionization radiation will allow the electrons to accumulate in these microcavities, which will accumulate until the repelling force is strong enough to expel the grains and destroy these cavities held by the particle cohesion. And this is the mechanism that has been tested in these serious experiments, and so far successfully explained a lot of what we observe in the lab. And one recent achievement just accepted on Icarus is that we can actually carefully, through analyzing these microscopic trajectories of each hopped dust particles, we can constrain their size and velocity relationship. And this allows us to quantify the mass loss rate that's driven by the electrostatic dust transportation. And you can see that these are really slow ejection speeds, like a meter per second scale, and that will only affect the tiniest body in the solar system. So putting these two processes together, we can, and here shows the Bennu with an escape speed of 0.2 meter per second. That means a lot of particles will be able to escape the gravity from Bennu. And so if we put all these processes together, we get this plot, which is a little bit busy. So let me walk you through this. So in the vertical axis, it shows the regulars, mass, loss, and production rate.
2 minutes.
Yes, great. And on the horizontal axis, it shows that vary as object size. And you can see the blue one is the production and the red one is the loss. And you also see a different components. And what is important, of course, is the intersection of these two curves. And so if we look at another figure, basically the same thing, but we also examine the heliocentric distance relationship into this, you can see that at, for example, about at 1 AU distance to the sun, the objects smaller than 0.8 kilometer in radii will predominantly lose their regulars. That means they will likely, with time, to be looking very rocky and bouldery, just like what we have seen so far on Ryukyu Bennu and to some extent Itokawa as well. And larger bodies will be able to retain their fine-grained regulars and be and so far that is consistent with what the objects we see. And more importantly, I would like to discuss the implications. So first, I think this is important in regarding for future explorations, for sample returns or for mining opportunities, and what kind of instruments or mission strategies you are going to apply for different type of objects with or without regulars. And second is that removing these fine-grained regulars could have spectroscopic effects on their surface spectra observed on the ground or in space. And the confusing part is that removing the fines will actually give you opposite trends in contrast to the reddening caused by space weathering. And so these could be two competing effects, and that might need to be looked into, which we just submitted a proposal last month, fingers crossed. And third one is that this could also, changing the regulus property could also introduce changes to their thermal radiation effects, and that will affect the migration of small bodies, predominantly these ENA objects from their source region in the main belts and how they propagate into near-Earth space. And the good part and the best part about this is that we will have opportunity to examine this hypothesis in the next decades. And there are many opportunities. I will not repeat this. So that goes to another thing is that what we really need is ground truths from really characterize the properties of these electrostatic particles, not only in the lab, but also in space. And on lunar surface, there have been a lot of indication that of the presence of electrostatic activities, and an instrument development project led by Dr. Xu Wan is focused specifically on this. So this is a summary that for sub-kilometer asteroid, we think the regulus loss due to electrostatic process dominates over the production from fragmentations caused by thermal fatigues and meteorite impacts. And this could have effect on the surface and physical properties of these tiny bodies, and which may be, and their implications need to be looked into regarding planetary defense and future studies. And in parallel to advance our modeling technique with this approach, we also really need is the ground truth measurement of the microscopic effect like fragmentations and electrostatic lofting grains properties. And that's it. Thank you.
Okay, thank you, Dr. Su. Because of our time limitation, we're going to move on our next speaker, Dr. Thomas Prettyman from PSI. So Dr. Thomas, can you share your screen?
Tom, we're not hearing you.
Can you hear me, and can you see the screen properly?
Yes.
Yes.
Okay.
Yes.
Great. So I'm going to talk about carbon and organics on Ceres. This is going to be kind of a summary talk where I review the dawn and telescopic data and provide some interpretations. They're my co-authors, and work is partially funded by the Survey Toolbox for Research and Exploration project. So just to get started, looking at Ceres surface composition, Ceres has hydrated minerals that are pervasive on the surface, as can be seen in the chart on the right. The alteration assemblages that are globally distributed contain magnesium phyllosilicates, ammoniated clays, carbonates, and a darkening agent. And that darkening agent might be amorphous carbon. One key thing to understand about Ceres is that it's similar to the CI-CM chondrites, but they really do provide an imperfect analog for Ceres. And this is mainly because Ceres is large and it likely underwent extensive ice rock fractionation, producing a differentiated interior. And that would be unlike the CI-CM parent bodies. In addition to the hydrated minerals on the surface, there is water ice, and you can infer from data acquired by Dawn's gamma ray and neutron detector that you have a dry lag, albeit hydrated, covering ice at depth. Any elemental data that I show will be for the equator, where the measurements are less influenced by the subsurface water ice. Now, this is my summary chart for carbon. The background blue would be magnesium carbonates, which are all over the surface of Ceres. This is work by Carazzo et al. And then in certain regions, very concentrated in craters, for example, and in mountains, you have sodium carbonates. And the fact that you have different carbonates on the surface indicate that there were different conditions for hydrothermal processing within Ceres' interior and crust. So just making the rounds on the sodium carbonate deposits, these are bright features or facula. You have hydrothermal activity occurring in Akator, which could have been by impact heating, or brine sourced from the crust. You have extruded cryomagmas on the surface, such as Ahuna Mons. And you also have fresh impacts that reveal structures that might be brine plumes. In addition to all the carbonates that you see on the surface, you also see organics, which allow you to start to make some assessment of organocarbonate associations. And question endogenic or exogenic we'll get to in a second. But before that, I'll just mention that carbon itself as an element is higher than the meteorites in the global regolith based on grand observations, and a portion of it may be in the form of graphitized organics. So here are the Dawn Veer observations, and you can see here that places that are bright in the vicinity of Ernetit crater, which I showed you earlier, have enhanced 3.3 to 3.6 micron absorption feature, indicating the presence of organics. These are methyl functional groups associated with aliphatic hydrocarbons, so long chain hydrocarbons. These are also nicely associated with the carbonates, which appear to be magnesium rich in this region. Here's the case for endogenic origin versus exogenic. Very strong case for endogenic origin. One is just the association of the organics themselves with the carbonates and also ammonium-bearing compounds. This suggests that what you're looking at is the extrusion of cryovolcanic fluids. And with the high-res framing camera data making association with organics and red slope, you can see that the pattern of organics could result from small impacts that are recent. This is work by Peters et al. And then finally, the kind of linchpin here is that it's just very inefficient to deliver organics by impact. So they very well might be endogenic. So UV spectroscopy provides more clues. On the right, we have data from Hubble. This is Hendricks et al., where we have normalized reflectance versus wavelength. And you can see in the far UV, there's this bump. And this bump is associated with graphitized carbon species. And this could have resulted from organic molecules exposed to ionizing radiation. And then it produces, breaks bonds and removes the hydrogen, producing this bump. Further evidence for this comes from a model comparison where you have graphitized carbon comparing very nicely to the far UV Ceres spectrum. And this tends to imply that graphitized species are pervasive on the surface of Ceres. If that's true, then why didn't Veer see organic matter everywhere? And the answer is kind of self-evident, but verified by Kaplan et al., namely the strength of the 3.4 micron feature would tend to decrease with graphitization. So bottom line, organics may well be pervasive on Ceres, but not easily detected in the near IR. Grand observations are interesting because if you look at a plot of carbon weight percent versus hydrogen weight percent, you can see that the regolith of Ceres has more than 10 weight percent carbon compared to the meteorites, which are, and it's also less than comets. But this is still a really large amount of carbon. And the only way that we can think to explain it is that it's consistent with a differentiated interior. In other words, you had to have elemental fractionation and carbon species fractionation as Ceres formed. And this is consistent with geophysical data by Fu and Castillo and others. So it turns out also, a study by Marquis et al. Shows that surface chemistry and mineralogy can be reconciled if you have graphitized organics on the surface, and that kind of ties all the measurements together rather nicely. So one way to sort of discuss this is to look at the analog materials, and on the right I have a plot of carbon versus hydrogen for carbonaceous meteorites that have undergone aqueous alteration. And it turns out carbon's partitioned into organics, carbonates, and unidentified components. These are shown here. Here are the organics. The white is the total carbon, green is organics, and then the kind of magenta is carbonates. And it turns out that in these meteorites, carbon is primarily in the form of insoluble organic matter. But amongst the soluble component, you also have aliphatic hydrocarbons similar to what you might find on Ceres. Now, to understand this even more, we have to understand production modification of carbonaceous materials on these parent bodies. And Schulte and Schock proposed that most of the soluble component really comes from coupled aqueous alteration and abiotic synthesis of aliphatic organic molecules. This is easy to understand how this could happen. When you have aqueous alteration, you have serpentization. It's an exogenic process. It produces heat. And many of the reactions produce hydrogen gas, such as the one below. And then this thermal energy, plus the presence of accreted carbon species and high hydrogen fugacity can result in abiotic synthesis, such as in the reaction shown below. The flip side of the coin is carbonates. To make the carbonates, you can have oxidizing conditions in the hydrothermal system that eat up the organic matter producing CO2 gas. That combines with water to make carbonates. And you can see this rather clearly in the chart below, where for selected CM chondrites, you have increasing carbonate to IOM content with alteration. And this is a study that was done by results presented by McSween et al. In 2017. In addition, carbonate composition changes with alteration. The point of this is that the meteorites and Ceres really should provide a test bed to understand the different conditions under which organic matter and carbonates can form. Okay, and then one thing that everyone should be aware of is the meteorite ZAG. It's an H chondrite that contains exogenic materials in the form of halite crystals, and it turns out these halites contain organic matter, and these may have been made in hydrothermal systems very similar to that of Ceres. The bottom line is asteroid interiors can host environments suitable for prebiotic chemistry. That said, all of this places Ceres as an extremely nice looking astrobiological target. And it also falls on the spectrum of ocean worlds. You have all the elements necessary, energy and water to do prebiotic chemistry. It's really cool. So to sort of wrap things up, this is the exploration connection. The Ceres studies and future missions should provide insights into crustal processes and hydrothermal evolution of water-rich asteroids. It also provides a test bed for different concepts in astrobiology. The specific studies we were working on support Survey Trek's themes, namely use of UV to identify carbon-rich asteroids, and improving the integration of optical and nuclear remote sensing methods. And then finally, there's a potential both on Ceres and in water-rich asteroids for ISRU via extraction of water and production of propellant via methanation. And that concludes my talk. Thank you.
Thank you, Dr. Thomas. We still have 2 minutes left. So if you have any questions, feel free to ask to Dr. Thomas. Any questions from our audiences? Okay, then we'll just move on our next speaker, Dr. Umberto Campins from the University of Central Florida. Can you share your screen, Dr. Umberto?
I am trying.
Okay.
Got it.
All right. All right. And let me see if I can do the presenter mode. Are you seeing me in presenter mode?
Not yet. Yes.
Okay. So today I'm going to talk about the possibility of searching for exogenous material on asteroid Apophis when it comes by the Earth in 2029. This is work that I'm doing at the Center for Lunar and Asteroid Surface Science at the University of Central Florida in Orlando. And my co-authors are Remington Cantelas, Marcel Popescu, Eri Tatsumi, Julia de Leon, Javier Licandro, Danny de la Justina, and Hannah Kaplan. And I'm going to give you a brief outline about the detectability of exogenous material on Apophis and related findings that make that a more likely possibility and why we should look into it. The problem of surviving projectiles. Now we have detected exogenous material on at least 3 asteroids, maybe more. And until now, we thought that these projectiles would not survive the impact. Then I'll tell you more about the opportunity in 2029 and leave you with the conclusions. So exogenous material could be detectable on Apophis, and the likelihood of such detection has been increased based on several recent observations that we review in this presentation, and we review its possible implications if they do get detected. The Alma-Ata meteorite, which came from 2008 TC3, contained different meteorite types, different lithologies that came from different parent bodies. And until that meteorite fell, this had been considered an anomaly. But recent results from the Dawn mission, the Hayabusa 2 mission, and the OSIRIS-REx mission suggest that material from multiple parent asteroids is more common than had been expected. Xenoliths, in other words, material that come from a different parent body in meteorites have been detected in a number of meteorites, including the HEDA chondrites, which are associated with Vesta, and the ordinary chondrites. And the majority of the xenoliths on these meteorites are carbonaceous material. This foreign material has also been found on asteroids. The Dawn mission confirmed that carbonaceous xenoliths found on the HED meteorites were related to the dark material on Vesta. And I'll show you some images in a moment. And then on NEA's Bennu and Ryugu, the OSIRIS-REx and Hayabusa 2 missions have discovered V-type related to Vesta and S-type related to ordinary chondrite material in these asteroids, respectively. The primitive nature of Bennu and of Ryugu means that this material was not formed with them and is most probably exogenous. So we have then 3 asteroids where we have found primitive material on silicaceous asteroids and bright material on carbonaceous asteroids, respectively. So here's the example of, in the case of Vesta, from the paper of Reddy et al. 2012, and then the exogenous material on Bennu from Kaplan et al. 2019. There's a paper that is under revision by De La Justina with a lot more detail on this. Then in the case of Ryugu, the work of Sujimoto et al. 2019 indicated that these materials would be S-type, so bright boulders on a dark asteroid. In the case of Ryugu would be S-type, in the case of Bennu would be V-type, like in Vesta. So what about the survivability of these projectiles? Until now, the high mean collisional velocity, which is about 5 kilometers per second, had been used as an argument against the projectile material surviving an impact. However, they do, clearly, on Bennu, Ryugu, and on Mahatsita, and on Vesta. So modeling is underway by a group in Nice headed by Patrick Michel, and how impacts can actually yield surviving material on a rubble pile disruption. A reminder that Apophis will be coming very close to Earth in 2029. And this close approach can provide an unusual, maybe unique opportunity to obtain Earth-based and in situ observations. Such observations could reveal something similar to what was observed on Vesta, exogenous carbonaceous material on a silicate surface. So Apophis is an SQ-type NEA, which was likely delivered to the near-Earth space by the Nu 6 resonance, and it's associated with LL chondrite meteorites that contain the Krimka meteorite, which has been known to have carbonaceous xenoliths. So in the case of Apophis, which has a geometric albedo of about 25%, and the carbonaceous material that could be on its surface would have an albedo between about 3 and 10%, so it would appear dark, like dark spots on a bright surface, kind of like in Vesta. Now, the detailed surface spectra of Apophis, if it's done in situ, could also reveal material that would have a similar albedo, but a very different spectrum in the case of like a V-type spectrum as opposed to an ordinary chondrite spectrum in the 1 and 2 micron region. The implications are that the presence and amount of exogenous material on Apophis can constrain its collisional formational history. For example, exogenous material could, on Apophis could constrain the time it spent on in the inner belt before being sent to the NEA space by the Nu 6 resonance. This could be combined with cosmic ray exposure ages in an attempt to link specific meteorites to Apophis, which would be a very interesting proposition. So in conclusion, we have exogenous material now identified on asteroids Bennu, Ryugu, and Vesta by spacecraft. The close approach of Apophis in 2029 provides a unique opportunity for detailed Earth-based and in situ observations. The presence and amount of exogenous material on Apophis can constrain its collisional formation history and possibly link it to specific meteorites. Thank you. Are there any questions?
Thank you, Dr. Umberto. Is there any questions? Dr. Faith, how many times we left?
We have about 4.5 minutes left.
Good. So, I'm glad to contribute to us getting back on time, on schedule. But there seems to be something in the chat. Let me see if can you guys read what came on the chat?
All I see is one for ZU from Sean Su. For this work, we did not model the cohesion. It was a question to a previous author.
Okay.
I don't know if another one has come up or not yet. So we can go ahead and keep going and just
okay.
Because I know I've got so many questions, I keep writing them down, but in general.
I'm going to stop sharing.
Yep. Thank you very much, Umberto. And our next talk is by my co-chair, Geji Kim, and the sensitivity of 99942 hypothesis neck to resurfacing during the 2029 Earth flyby. And so whenever you choose to start, go for it.
Okay. Dr. Faith, can you see my screen?
Yes, I can. I can hear you too.
Okay. Thank you so much for introducing my talk. My name is Yeji Kim, and I'm working with Dr. Hirabayashi, Masatoshi Hirabayashi at Auburn University. So the previous speaker, Dr. Umberto, will introduce about Apophis and its 2029 Earth Encounter. So I'm just gonna start with the motivation of our study. Apophis is planning to approach the Earth around the 6 Earth radius, which is the outside of the Roche limit. As you know, the Roche limit is the maximum distance that a small body can be separated into several fragments due to the tidal force of another celestial body. So assuming that Apophis density is around 2 grams per centimeter cube, based on this equation, Apophis Roche limit is a 3.4 Earth radius.
AJ, I lost your voice.
Lesser.
I don't know if others have.
Oh, can you hear me?
Yeah, I can hear you. This is Christina. Faith, can you hear me?
Oh, yes.
Well, I think Faith may have lost signal. Go ahead and continue.
Okay. Yep, so the Apophis Roche limit is estimated 3.4 Earth radius, which is lesser than the Apophis closest distance. So based on this, we expect that Apophis will experience small changes such as the movement of surface particles or small changes in its internal structure during this encounter. So here are some earlier works that prove our expectations. These are saying that Apophis will experience spin changes during its flyby. It may also have tiny landslides at some locations or possible seismic waves inside of Apophis. So we believe that this encounter event would give us an amazing chance to observe the possible consequences of tidal stress directly, which is a non-catastrophic level. So a well-understanding of Apophis behavior earlier than this event would be necessary for any possible missions targeting Apophis. Also, a well-understanding of this asteroid at this encounter time would be eventually helpful in proposing suitable guidances for planetary defense technology. So I'm going to introduce 2 numerical models that we are using to analyze Apophis when it is impacted by the tidal effect. So the first model, it is called by dynamic model. It is developed to see how the surface of Apophis is evolved during its flyby and eventually provide us reasonable locations that may be susceptible to material flows. So the encounter event is modeled as a 2-body problem. So the Earth is assumed as a sphere, while the current radar shape model is used for modeling the Apophis. This current radar shape model hints that the Apophis probably has a contact binary shape. So these are entire equations of 2-body problem that we implemented in our numerical simulation package. So the acceleration acting on each element is computed by self-gravity, gravitational interactions force from the Earth, and the rotational force. So for this, the Apophis trajectory and its spin state are updated. So for the trajectory, we imported its orbital information from the JPL Horizon Web Interface into our model. Also, we are using Euler equations to integrate the spin state of Apophis. The initial spin period here is fixed 30.6 hours, but the spin orientation of Apophis is still an uncertain parameter here. So using Monte Carlo simulation, we conducted multiple simulation cases depending on different initial spin orientation. And the last step is to convert this converting this acceleration data into a surface slope that is technically describing how the surface element is tilted on the direction of the affected gravity. So based on the conventional theory of the angle of repose, we assumed that material flows may occur when this surface slope exceeds the angle of repose. So we simply compare this parameter with the angle of repose to estimate which locations would be sensitive to material flows. In the second model, we are using the finite element model, which named FEM, to investigate how Apophis structure is impacted by the tidal force. So FEM eventually provide us which locations would be failed during the encounter time. In this model, Apophis is considered as a continuum that has soil characteristics. And then to obtain the elastic and plastic FEM solution, we used the commercial software ANSYS Academic APDL. And the plastic solution, the yield condition of Apophis is defined by the Drucker-Plager yield criterion here. And then using this model, we perform two numerical cases. One case is when Apophis is not affected by tidal force, but only influenced by gravitational and rotational force. Another case is when it is affected by tidal force as well. So in the following result section, we're going to compare those two cases and see how the structurally failed reasons can be changed due to the tidal force. One thing I want to point out here is that our current FEM only considers a static case, which means it is ignoring the time evolving effect. So the magnitude of the tidal force applied here is only fixed at the closest flyby. So our research show one case from the dynamic model. This upper figure shows the maximum surface slope at each element, and the bottom figure shows the slope variations during the encounter. As we can see here, the slope variation reaches up to 2 degrees, which is not enough to significantly change the initial distribution of surface slope. So for example, this blue region here, I will use razor. So this blue region here won't become the unstable even if this location has the maximum surface slope variation like 2 degrees. So in this tidal encounter, we can say that the possible resurfaced region or susceptible locations to material flows would be around the initially high sloped region, which means it is highly likely to depend on the shape of Apophis. In our further analysis, we divided the Apophis shape into 3 locations: small lobe, large lobe, and neck regions, because it is a contact binary shape, and then see how the size of possible resurfaced region and slope variations changes at each location. When we look at the left figure first, the y-axis means the size of the possible resurfaced region, while the x-axis shows the case numbers. So this results tell us that only tiny regions would become unstable because it is only 1.5% of the entire region at all cases. When we separate this data into 3 different locations, then the large lobe have the largest portion of the resurfaced region, and then the neck region also has some portion of this region. This is because the initially high sloped regions are distributed in the large lobe and the neck regions in our current radar shape model. So and then in right figure, it looks a little bit complicated, but this figure eventually wants to say that the distribution of surface slope variation would be changed depending on Apophis spin orientation. Because at some cases, the maximum slope variation happens at the large lobe, but at other cases, it happens at the neck or small lobe. So the slope variation can be dependent on the orientation spin, the spin orientation of Apophis. But as I mentioned before, the slope variation maximum 2 degrees is still weak to significantly change the location of resurfaced region, even if the slope variation is strongly affected by the Apophis spin state, Apophis spin orientation. In this tidal environment, our FEM results indicate which locations would be structurally sensitive. So when we compare those two cases, one is before the encounter, another one is at the closest flyby, we can notice that only net regions have an increase in failed regions. This is because the net region in a contact binary shape is structurally weak because of its lower self-gravity than any other regions. Also, we noticed that if we want to observe the failed regions around the neck, the cohesive strength should be very weak. So our model estimates around 0.3 Pascal, which is very weak because failed regions. So from our analysis, the expected tidal force during the 2029 is very weak to cause significant or observable changes on surface or structure of apophysis, although we noticed small changes. However, we still have further work to investigate apophysis under this tidal effect condition. First, we're going to obtain the new radar model through the observations in 2021. So this is going to give more accurate estimation of resurfacing regions. Also, as I mentioned before, our FEM only considered a static case. So it is going to be ignoring time absorbing effect. So we are planning to expand this model to apply a dynamic case and expect see more noticeable changes from the advanced model. So I'm going to finish my talk here. I appreciate your attention. And we don't have much time to take any questions, right?
We have no time for questions. Can you hear
Okay.
me? Okay,
Yes, I can hear you.
good enough.
Then stop sharing. Then yeah, let's move on our next speaker.
Okay.
Yeah, let's move on our next speaker, Dr. Paul Sanchez.
Hi.
Yeah.
Some.
Can you share your screen?
Oh, let me. Okay. Can you see that?
Yes.
Yes.
Okay.
Nice.
Thank you.
Okay.
All right. Can you see the presentation?
Yes. Think so.
Okay, then I can begin. So thanks to everyone for being here. The work I'm going to present today is something we have been doing at the University of Colorado for the last few months, and it has to do with seismic waves in the asteroid environment. So these are the pictures of some of the asteroids that we have had as mission targets: Itokawa, Bennu, Ryugu, and well, in some years really, Dimorphos, the satellite of the Didymos system. And some of the things that they have in common is that they are small, they are granular in nature, and the missions require them to be in contact with the surface of the asteroid. And these contacts then should generate a seismic wave. However, little is known about the transmission in extremely low pressure environments. At least that is what I have found out. So what do we know? I'm going to be maybe fairly simplistic in this. We know that there are going to be P waves, the pressure waves, and S waves, the shear waves. And the speed of these waves depends on some of the material parameters: the shear modulus, the bulk modulus, and the density of the material. Something else that we know is that, if that is the expression for the shear modulus, this has a dependence on the square root of the overburden pressure, which means that the wave speed is going to have a p to the 1/4 dependency. Has this been observed experimentally? Well, the answer is yes. These are some old, let's say, it's from the 1990s. There's experimental results for tower sand and steel balls. And the lines you can see there, they have these 1 to the p to the 1/4 slope. And of course, for steel balls at about 35 kilopascals, we have a different slope, which is p to the 1/6. And this has not been completely explained just yet. Regardless of that, when the pressure goes to 0, the velocity of the wave should go to 0 too. And we wanted to know whether or not that's true, because if that's so, the velocity of the wave in an asteroid should be maybe just some few tens of meters per second. So we can go two routes. This is an asteroid in all its complexity and all its glory. And if we do it in simulation, we can simulate the whole thing. However, we have a problem. First thing, these are very low resolution. We cannot really have in simulation as many particles as we have in a real asteroid. And the second thing is that we are going to have a pressure gradient. It will go from 0 to something in the center. And this is not what we want to do. The other route we can choose is we are going to just sample the parameter space. We can change the overburden pressure. We can change the cohesive strength between the particles. And we can also change the velocity of an impact. And hopefully we will have an asteroid with somewhere within this parameter space. To do that, we of course need to have a small box with particles, and we will have a much higher resolution for that. So this is what we chose to do. So this is the simulation setup. At the left, I just have some of the details of the simulation. The important thing is that we're going to apply a certain pressure with a piston on top. The pressure will go from 0.1 pascals to 50,000 pascals. And we are going to start a plane wave by just giving a small kick to the particles on top. And the kick itself is going to change, to have a different velocities for different experiments. So once we do that, this is what we see. And we're going to measure the peak-to-peak time. So this is the time it takes for the peak of the wave to reach to the other side of the container. If we do these simulations with a crystalline lattice, well, this is what we find. This is just the velocity versus pressure. And as you can see, well, there's a bit of a weird behavior that because the velocity doesn't go to 0 as p goes to 0. Actually, there is a plateau. And this plateau, the extent of this plateau depends on the velocity of the impact. But we thought, well, maybe this is just a feature of crystals. Maybe this is just a numerical artifact. And so we wanted to go to the random systems. However, if we go to the random systems, we find something very similar, not exactly the same, but very similar. So what we wanted to do then is just to analyze closely one of these simulations. So we're going to take this one with an impact of 0.5 meters per second. We're going to focus on that plateau. And if we plot the energy versus height, this is what we find. Basically, this is just the wave moving through the container. However, given that this is a pressure wave, we were wondering, well, what happens with the pressure? Is it doing something similar? And well, yes, it's doing something similar. You can see how the pressure itself is traveling. The thing is, the pressure that is given by the wave is not negligible. Actually, it's a few thousands of pascals. And if we take all the simulations we have done for this specific impact speed, this is what we find. So regardless of the value of the overburden pressure, once we start the wave, the pressure of the container changes to a few thousands of pascals. So really, the pressure that controls the wave speed is the summation of the overburden pressure and the wave pressure itself. So if you have a very tiny pressure, which is negligible in comparison with the pressure given by the wave, for the same impact velocity, you will have the same wave speed. Now, what happens with energy deposition? The dots you can see in there, this is plots of just energy versus time. The small dots you can see in there, they symbolize the time of arrival of the wave to the other side of the container. And as you can see, well, by the time the wave has reached the end of the container, most of the energy has been dissipated. If we now take all the simulations we have done, what you can see here is that, well, about 90% of the energy is lost within 1 meter. And this is for every impacted speed, every pressure, and every strength we tested. If this is so, then maybe we can, I can wave my hand and write some expressions. So energy attenuation then may go as 0.1 to the R. R is just the distance from the source of the energy, meaning that every meter will be able to transmit just 10% of the energy of the impact. And if we also relate this to the 3D geometry of an actual asteroid, well, we need to divide the energy by r squared, and we can then reach the expression on the right. And now, I'm a physicist, so I'm going to make one very outrageous assumption. And it is that regardless of the shape, size distribution, packing fraction, our simulations actually do work as a proxy to asteroid regolith. I'm going to also assume that it is true for almost all possible impact speeds. What happens then? What is the implication of this for space missions? Well, for the
2 minutes.
Yes, thank you. For the Hayabusa mission, well, particles immediately surrounding the landing area could have been disrupted, but nothing else. For the Hayabusa 2 mission, the SSI impact did have an effect. Of course, there is a crater, but no particle beyond 5 or 10 meters would have been affected because they just didn't have enough energy to move. For the direct mission, the sample maneuver, which is going to be a 10 centimeters per second impact, is going to cause just little disturbance in the terrain around it. For the DART mission on Dimorphos, well, yes, there's going to be a big crater, but the seismic wave might not reach the other side of the asteroid. And this is a bonus because many times it has been said that possibly a small meteorite impacts on asteroids can trigger the Brazilian effect, and that is going to provide a way to segregate particles. And it seems that asteroids are not really going to be shaking that much because of impacts. I think this is the end of my talk. With that, I will just leave you with my conclusions. If you have any questions, please let me know. I will be happy to answer them. Thank you.
Thank you, Dr. Paul. We have one question in chat. So how well do you model results correspond to experimental data regarding influence distance dependence from confining pressure, impact speed, etc.?
Well, it seems that when I go to 1,000 pascals, 50,000 pascals, it seems to be correct. The thing is, the experiments on Earth can go, I have seen experiments down to, 10,000, but nothing below that. The reason is that you have gravity on Earth, and everything that is related to this goes up to gigapascals of pressure. So that actually does follow the theory. I haven't seen any experiment that goes down to this kind of pressure, 0.1 pascals.
Okay, yeah. Then let's move on our next speaker, Jennifer Larson. Jennifer. Her talk is about implementing the DART impact as a benchmark for the rebound ejecta dynamics package.
All right, can you guys hear me all right?
Yes.
Yes, awesome. All right, so thank you for that introduction. I'm Jenny Larson. I'm a grad student at the University of Central Florida. And I'm working on constructing a ejecta dynamics package using an n-body integrator called Rebound. And thank you, Paul, for that wonderful introduction to the double asteroid redirection mission, DART, which we will be using as a benchmark for this package. So DART, as was talked about previously, I'll give just a very, very brief overview so we can get to the fun stuff, even more fun stuff. So DART is looking at an impact into the binary component of the Didymos system, Dimorphos, to study the dynamics of a high velocity impact, as well as looking at changes in orbital period for the purpose of creating impact mitigation strategies. And so what we really want to look at, and the question we want to answer, is what should we see in the post-impact environment? And this really plays into the impact mitigation strategies. And so we are creating this rebound ejectodynamics package, which we call RED. And it serves the purpose of modeling post-impact debris dynamics in the short, mid, and long term. And we chose rebound because it allows us to calculate and create a large library of possible DART solutions in a lot less time than other n-body integrators such as Peekity-Grav. I know there have been some other preliminary studies done with Peekity-Grav as an n-body integrator. And we found that rebound actually does, since it does have the Python component, it's easier to kind of carry over from one platform to another. And it definitely has been shown to require less computational time than some of these others. And so we are trying to build this package with 5 different effects right now. So right now we have a particle velocity distribution, radiation pressure coupled with a particle size distribution. We can construct an ellipsoidal target body, which I'll go into how we do that. And we have a rotating target body and also the option for adding binary components, which of course will come in handy during the DART modeling. So for benchmarking, we really focused on testing each of the effects that we created individually. And this serves the purpose of not necessarily recreating an exact impact specifically, but more just to see if we can create an effect that works on its own. And so here we start with like the basic case of no additional effects. And as you can see from these videos, on the left we have the XY projection, on the right is the XZ projection. So on the left is looking straight down from above, and the right is looking like at it from the side. And so in all these simulations, we have about 10,000 particles, and we are focusing on an impact that occurs roughly on the equator of a spherical body that is supposedly roughly dimorphous size. That will change in the ellipsoid case, where of course we switch from a spherical body to an ellipsoid, but I'll get into that. So we can see kind of like a cone shape where there are particles closer towards the center of this cone that have a higher velocity that will then kind of loop up and around and cover the body. So when we look at the radiation pressure coupled with the particle size distribution, here in terms of the visuals, I want to note that the X denotes the initial location of the particles, and the arrow that you see that's labeled sun is actually pointing away from the sun. And so that's the direction of the radiation pressure acceleration. And so we can see that there is an effect. It's most notable in the XY projection. There is, the particles are pushed more off to the side and kind of align themselves with this acceleration. And you don't see it as much in more of the shadowed regions where the particles are behind the body. Okay, it's taking a while to load. Of course. Maybe. Okay, all right, sorry, I have to go back a few slides. Awesome. Okay, my computer really does not want to load that. We're going to try like this, just for now. Can all of you still see that? Yes. I know it's not in presenter mode.
Yes, we can see your full screen.
Okay, awesome.
You can see it.
Yeah, it was just not wanting to play in full screen. Maybe we can try again. No, it's just easier like this. All right. So here we have the ellipsoidal body case. And in this case, we aren't using a spherical body. We are just using a body where the smallest axis is 75 meters, which we're assuming to be roughly the radius in the spherical case. And so then the other axes are going to be longer. And so along this like longer lobe, the A semi-major axis, there is going to be a stronger gravitational effect. And so a lot of the particles, especially if you look up in this little upper corner, normally the particles would be kind of following off more up into the upper left corner, but they kind of try and drift back down to land closer to this X where the initial impact event, in quotes, occurred. All right. And that figure does not want to show at all. Awesome. Okay, so we have here the
2 minutes.
target body, thanks. The target body rotation that we're looking at. It's most obvious in like the 12-hour case, since the 6-hour case apparently does not want to load today. So here we have a spherical body and we can see the particles coming off the surface and rotating around, and the red is where it lands. And so they kind of just like sweep around the body. And finally, we have the binary case, which is going to be particularly interesting for the DART impact. We see as the particles go up off the surface of Dimorphos, they are gravitationally attracted towards the main body, Didymos. Here we did do the impact like on the side facing Didymos originally, and so we will be testing impacts, in quotes, starting on like different longitudes around the body and different configurations where the impact occurs like 90 degrees or 180 from the target body, to really see how the particles play into this whole system. And that, the binary component, we're still working on editing a lot of for an upcoming paper that we're about to release. And so just to kind of summarize, we have been testing these individual effects, and the hope is that by testing them individually, we can then work on fine-tuning them to later combine them into what may actually look like a more realistic system. And then we can apply this to create approximately 200 simulations for the DART impact. And this would have various combinations of effects and varying initial conditions. And this would really help give us background for what to expect. And then when we do have observations of the actual impact, we can then kind of backtrack and say, all right, what can we learn about what happened in this impact based on these observations, and how we match them up to some of these preliminary simulations that we have. So we do have a paper coming out soon, hopefully, fingers crossed, with more of these simulations and some more details. But if you would like further information, feel free to email me. My email is down here at the bottom, or stick around at some point to ask questions. I'll be around. So, thanks.
Thank you. Thank you, Jennifer Larson. If anyone has questions, please feel free to ask her. We have 1 minute left. I have a quick question to you. It's a quite straightforward question, but how efficient this benchmark RED compared to the other in-body code?
Right, so we can run one of these simulations in approximately 48 hours. And so we don't have to necessarily run one at a time. And so we can run like several at a time, which means that we could create this library of about 200 simulations in a couple months very easily. And a lot of other embody integrators tend to take longer and take sometimes up to a week to run a simulation, especially when it comes to irregularly shaped bodies, where we use an ellipsoidal gravitational calculation rather than building an irregularly shaped body out of individual particles. That really slows down the computational time because it has to kind of count for those interactions. That makes sense.
Okay, thank you. Then Dr. Faith, can we directly move on our discussion section?
I'm sorry?
Can we directly move on our discussion section?
I think so, although I do know that Greg had some announcements to make.
Yeah, hi, it's Christina's. Greg went to the other session and I hung out with you guys today. Just two quick things, because tomorrow morning we start, oh, that's a great cat, I love it. We start tomorrow in poster session, so just kind of a reminder to jump into the posters at 7:30. The time has changed from a schedule a few days ago due to Dr. Glaze and Mark Kurasich's schedules. So poster session from 7:30 to 8:30, and then we're going to jump right in with both of them. So would love everybody to come and join us for their discussion and presentations. And with that, I will thank everybody and leave it back to both of you to close out the discussion session. Thank you.
Thank you, Christine. I open the session to questions, either spoken or through the chat window. I have a couple for Darby, but I can write them down too. So. I believe this is probably pretty informal at this point.
Faith.
Yes.
Do you know if NASA has any plans for exploration of Apophis?
You mean beyond? No, I don't.
Human.
Know.
I meant human.
Human exploration. I don't think so. I don't think so at this point. But anybody else want to jump in? By all means, please do. No? Paul Abel would know, I would guess, if anybody would. But.
Hey, Faith, this is Darby. You have questions for me, but I have a question for you because you would know the answer to this. Most of the asteroid data, what energy range do they cover, or wavelength range?
I was just asking you the same question here. I was saying, Darby, what is the spectral range and dispersion per element for your spectra after you reprocess them? No, which one?
I think well, you can use the link and you can actually plot them and see yourself. Let's see, I can do that too. Yeah, almost all of them are only 0.3 to 2.5. A few go out beyond 3.5, but the problem is that the data that we use don't seem to extend that much further out. And also, of course, the meteorite data are almost all collected at Relab, and the Relab standard range doesn't go beyond 2.5.
Right. Okay. How about when you reworked them, what was your dispersion per element? You know.
What do you mean? We just resampled them.
Sorry?
I said we just resampled them to match the Relab sampling density.
Okay, that was what I was trying to figure out. What is the Relab?
Yeah.
I can check it out. All right.
And you can, in fact, on our website, resample them again if you want. And if you go to the website too, what you see is all of those are all the metadata codes. So every single spectrum has all of these metadata. And if it's an asteroid, you can obviously see that the asteroid metadata are filled in. And if it's not, if a meteorite, then the meteorite metadata are filled in. But all of them have the same exact headers, so that when you load these things, they're all the same, which is quite handy and took us literally a couple hundred hours to do. Reforming all these data was a nightmare.
Are you planning to put them into PDS?
Well, most of them are already in PDS. And of course, we didn't collect any of them ourselves. Well, except for the meteorite data. Well, back up. The meteorite data from Relab are now automatically being sent. Everything from Relab is going to PDS now. Okay. So that's easy. And then the asteroid data, we got all of them from other people. So it's not really we don't really have the right to.
Got it. Okay. So. Anybody else, or should I turn back into my cookie?
Yeah, we have one question to Paul, Dr. Paul. What materials did you use for modeling?
Oh, as I remember, the material parameters are close to basalt. It's not exactly that, but they're close enough to be basalt. Yeah.
Yeah, thank you for answering the question.
If there are no other questions, I guess we can leave it informally. You know, you can continue, but we'll close out the session. Thank you all for coming. I've already gone back informal. So.
That's awesome. Thank you all.
Yeah, thank you, Dr. Faith.
Thank you.